Center, and I'm going to be the chair of the hardware session today. It's my great pleasure to introduce Tian Zhao from Stanford University, who is a PhD student there, working with Professors Kunli Alakatan. His interests include efficient system and architecture design for machine learning and computational linguistic applications. So please take it from here.
Okay. Hi, everyone. My name is Tian. I'm a PhD student working with Professor Kunli at Stanford University. In today's talk, I plan to cover the design considerations for serving recurrent neural networks efficiently with a spatial accelerator. First, RNNs are popular data center workloads. According to the numbers showed by Google, in the year of 2017, about 29% of the in-data center machine learning workload are RNNs. A natural question to ask is how to design an efficient hardware accelerator for all the RNN kernels. Or more specifically, we care about designing such an RNN serving hardware that can achieve high performance with high efficiency measured in terms of performance per area and performance per watt. However, the hard truth is RNN is hard to serve efficiently for the following two reasons. That first, RNN kernels contain complex data flow, which is hard to serve efficiently on the modern hardware. And the second challenge is that RNN sizes can vary a lot over different problems. To get a sense of how complex a data flow within an RNN kernel would look like, here is an example of the data flow path within a long short-term memory cell, which is one flavor of the RNN kernels. This kernel contains 4 weight matrices of size D by H, where D is the number of input features and H is the number of hidden units. It also contains another set of 4 weight matrices of size H by H and 4 input vectors of size H. Oops. During execution, the RNN kernel first consumes an input vector, a hidden vector, and a memory vector. At the end, it generates 2 new memory vector and hidden vector. The execution of this data flow can be divided into 2 parts, where the first part contains 8 matrix vector multiplications, and the second part contains 13 element-wise operations. As you can see in here, the data flow of this RNN kernel is quite complex. The second challenge is that RNN sizes can vary over different problems. For example, in this table, I show 2 tasks, where the first task is a sequence classification task that uses an RNN of size 128. The second task is a speech recognition task that uses an RNN of size 2816. And as you can see in here, the large task can be 20 times bigger than the smaller one. And as a result, it is hard to find a serving platform that can achieve high hardware utilization and energy efficiency on both sizes of these RNN tasks. So in short, RNN is hard to serve efficiently since their kernels contain complex data flow and their sizes has a very large variation over different problems. To deal with this complexity, most software frameworks and hardware accelerators choose to decouple an RNN kernel into a set of basic linear algebra subprograms, or also known as the BLAS subroutines. For example, in the context of inference, the brainwave neural processing unit from Microsoft chooses to accelerate the matrix vector multiplication operation within the RNN kernel, which is at BLAS level 2. In the context of training, the tensor processing unit from Google chooses to accelerate the matrix-matrix multiplication operation, which is at BLAS level 3. Hence, a natural question to ask is if BLAS is the right ISA for accelerators. From a very high-level point of view, using BLAS abstraction enables the software developers to focus on the very high-level functionality of their applications without worrying about the actual hardware implementation. Similarly, the hardware developers can focus on implementing highly optimized BLAS kernels. However, individually optimized kernels do not guarantee globally optimized end-to-end application. Now, let's zoom in to the inefficiency introduced by using BLAS abstraction when serving an RNN kernel. First, let's look at the matrix vector multiplications in this RNN. The size of the matrix is h by h, where h is the number of hidden units, and the size of the input vector is h. A BLAS accelerator usually blocks on both dimensions of the weight matrix. In this example, I show a BLAS accelerator that can complete the matrix vector multiplication operation in 6 iterations. And as you can see in here, this BLAS accelerator is underutilized due to misalignment on both dimensions of the weight matrix. To give a more concrete example, let's say that the BLAS2 accelerator can consume a submatrix of 60 by 80 per iteration, and it is trying to serve an RNN of size 128. For this example, the utilization is only at 56%. Moreover, the intermediate result coming out of this accelerator is in the form of vectors, which needs to be buffered into on-chip Scratchpad memory. And on-chip Scratchpad memory is a very energy inefficiency component. When we zoom out and look at the overall data flow, we'll see that there are 26 paths in this data flow that requires frequent access to the on-chip Scratchpad memory. From this example, we show that BLAS abstraction would lead to hardware underutilization caused by misalignment. And alternatively, we can use a more general abstraction, which is the loop-level abstraction. The loop-level abstraction allows us to perform fine-grained tiling along one dimension of the weight matrix. As a result, the size of the intermediate result coming out of this accelerator is 1, which means that the element-wise operations that comes in the second part of the RNN kernel execution can now be fused into the matrix vector multiplications. Moreover, when executing the matrix vector multiplication operation, the accelerator that supports fine-grained tiling only suffers from hardware underutilization from one dimension of the weight matrix. If we were to reuse the same example of serving an RNN of size 128, this time the utilization can be as high as 80%. Moreover, the output can all be buffered into an on-chip register, which is more energy efficient compared to the on-chip Scratchpad memory. From a high-level point of view, the fine-grained tiling happens along the hidden unit dimension, which means that within each tile, the weight matrix is now converted into a weight vector of either size h by 1 or d by 1. And then we tile it by h times to create the output vectors. Now, with fine-grained tiling, the matrix vector multiplication operations within the original data flow graph are all converted into dot products. Moreover, the 26 paths within the original data flow graph are now only accessing on-chip registers instead of the on-chip Scratchpad memory. Overall, we find that loop abstraction enables fine-grained tiling to reduce hardware underutilization due to unalignment and to reduce the size of the intermediate buffers. Second, in this talk, we show that BLAS abstraction will lead to a heterogeneous accelerator design that would contain unbalanced pipeline when serving RNN tasks of different sizes. Let's first think of an RNN serving task from a very high level. The first part of an RNN serving task contains matrix vector multiplications that requires computation of big O of h plus d multiplied by big O of h, where h is the number of fitting units and d is the number of input features. The second part of this serving task contains element-wise operations that require big O of h computation. If we were to stick with the BLAS abstraction, when designing the accelerator, we'll need to have dedicated hardware unit to support the matrix vector multiplication subroutine from the BLAS. And we would also need to have dedicated hardware unit to run the element-wise operation. In contrast, for homogeneous accelerator, we can have, say, a pool of computation units where each computation unit can be repurposed to perform either a matrix vector multiplication or an element-wise operation. Let's look at how a heterogeneous accelerator will handle the RNN serving task. When serving the RNN task, we can overlap the matrix vector multiplication with the element-wise operations. However, for a heterogeneous accelerator, the level of parallelism that the matrix vector multiplication unit and the element-wise operation unit is fixed during runtime. And as a result, when serving a small RNN task, the matrix vector multiplication unit within the BLAS accelerator would run for fewer cycles compared to the element-wise ones. In this case, the element-wise operation unit would become the bottleneck within the whole end-to-end pipeline. When serving a large RNN, the case is flipped in the sense that the computation requirement for the matrix vector multiplication operation grows at a much faster rate compared to the computation requirement for the element-wise operation. And as a result, when the size of your RNN grows, the bottleneck, the matrix vector multiplication unit will spend more cycles to run compared to the element-wise operation unit. And in this case, the bottleneck will be shifted to the matrix vector multiplication unit. In this example, we show that a heterogeneous accelerator will have an unbalanced pipeline with respect to different problem sizes. When serving the RNNs using a homogeneous accelerator, the pipeline can dually be balanced. For example, when serving a small RNN, a homogeneous accelerator can choose to reallocate more resource for the element-wise operations in order to balance with the matrix vector multiplications. When serving a large RNN, the homogeneous accelerator can also choose to reallocate more resource for the matrix vector multiplication in order to achieve a balanced pipeline. In this example, we show that a homogeneous accelerator can always achieve a balanced pipeline regardless of the problem sizes. To evaluate the strategies that we propose in this work, we choose 3 hardware platforms. The first platform is a Tesla V100 GPU that supports programming by using TensorFlow and cuDNN. The key operation that the GPU chooses to accelerate is the matrix-matrix multiplication, which is a BLAS level 3 subroutine. The GPU is a heterogeneous accelerator. Second, we choose the brainwave overlay architecture on top of implemented on top of a Stratix 10 FPGA. It is a heterogeneous spatial accelerator that focuses on accelerating the matrix vector multiplication subroutine, which is at BLAS level 2. Lastly, we choose a homogeneous accelerator called plasticine, which is also a coarse-grained reconfigurable architecture. It supports acceleration at loop construct level. All of the three platforms possess roughly the same numbers of peak 32-bit teraflops. Moreover, the plasticine CGRA is at an older generation compared to the Tesla V100 GPU and the Stratix 10 FPGA. Comparing to the GPU and FPGA platform, the CGRA platform uses a die area of 494. The Stratix 10 FPGA uses the smallest thermal design power. We run our evaluation by implementing the RNN kernels from the deep benchmark. We implemented these kernels on Tesla V100 and on the plasticine CGRA. We collect the performance number of brainwave from their original paper. Overall, we find that homogeneous accelerator that supports more general abstraction at loop construct, such as a plasticine CGRA, can achieve very consistent and high hardware utilization across many different sizes of the RNN kernels. In contrast, a heterogeneous accelerator, such as brainwave, that supports only BLAS level abstraction can only achieve the highest hardware utilization at a particular problem size, which is at GRU 2816 in this case. We were not able to saturate the computation capacity of the Tesla V100 since the size of a serving task is very hard to saturate its DRAM bandwidth. Overall, we show that a homogeneous accelerator such as plasticine can achieve the best performance and the best efficiency measured in terms of performance per area and performance per watt comparing to the other platforms. In short, in this talk, we show that homogeneous accelerators with loop-level abstraction can achieve better hardware utilization and efficiency comparing to heterogeneous accelerators that only support BLAS abstraction. With that, I conclude my presentation. Thanks for coming, and I'm open for questions now.
We now have time for questions. When you have questions, please come to one of the microphones, introduce yourself, and ask your question.
Hi, Rick Kaye with Microsoft. Very interesting talk. I'm curious on the GPU comparison, the V100.
Let me try to.
The V100 RNN numbers. I wonder if you used the latest CUDNN.
You mean the CUDA and LSTM implementation?
That's right, where they're doing some temporal unrolling and overlap of the
Right. We actually use that implementation. And to be more precise, the CUDA and LSTM implementation tries to block on the element-wise operations within the original kernel. But then it still needs to trigger like memory transfer when you are trying to send the weights over. And in contrast, I think both Microsoft Brainwave and the CGRA that we choose, which is called plasticine, used low precision arithmetic and was able to embed all the weights on chip. And that's actually a key difference between the Tesla V100 implementation and our implementation, and of course Microsoft Brainwave's implementation. Questions?
Yusuf Clarkerman of Bloomberg. I was wondering if you tried with the V100 to do a custom CUDA kernels which did loop-based parallelization. If you think you would get better results, or?
We actually used the CUDA implementation for both the LSTM cells and the GRU cells. But I think if you look at the CUDA kernels for those two like CUDA APIs, you will find that they're the first part of the RN kernels are still implemented using a streaming gem instead of using loop construct. And whereas in contrast, our implementation can fuse the loops in the first part and the second part.
Right, but the question is, if you use CUDA to do your implementation in running it on a V100, what utilization do you think you would get?
I think we'll still get a very similar utilization as reported in here.
Thank you.
Okay, thank you.
I have a quick question as well. So the observations about LSTM are very interesting, but a lot of new workloads for machine translation start to use models like Transformer and BERT that use attention layers and essentially better fit for GPUs. So what do you think? Any of your ideas will be applicable in this domain as well?
Sure. So I have 2 points for that. The first point is, I think for at least for like the models for like general transformers, it requires to send in like more time steps, whereas in contrast for most of RNNs, it only needs one time step in order to generate the next result. And therefore, I don't really, I think it would be quite hard, at least from a hardware architecture point of view, to have a very fast and efficient serving platform for a transformer-based model. This is my first point. And the second point is that if you look at the individual like transformer cell within the overall model, it actually contains a more simple data flow comparing to the LSTM ones. For example, if you look at, say, like one individual transformer cell, it's a matrix multiplication followed by a softmax layer, where the softmax part cannot be categorized into a BLAS subroutine. And in which case, the application that we use, the strategy, the fine-grained tiling scheme that we're using here can still apply to the softmax plus the matrix multiplication part of the transformer cell, which still, enables kernel fusion and other, and achieves a better pipeline.
Okay. Thank you.
Thank you.
Thanks to the speaker again. It is my great pleasure to introduce our second speaker today, Wong-Kung Jan from Seoul National University. He's a PhD student there working with Professor Jan Ho An, and his interests include optimizing emerging applications and exploiting the characteristics of the latest and future hardware for them. Okay.
Okay, thank you for introducing. Hi, I'm Wong Kyung-jung from Seoul National University, and today I'd like to talk about restructuring batch normalization to acceleration and training. So let's begin. So why do we care about accelerating training? Because training requires high computing costs, which may take several days to weeks to train a single model. For example, in ResNet, we need 29 hours with 8 GPUs, which is quite large cost. And also, this training might be done multiple times to follow up new algorithms or new models or data set. So in this work, our focus is on reducing computing cost of the training. Then why do you care about the batch normalization? Should we concern beyond even if convolution or fully connected operations are dominating training time sometimes? So this is a chart showing execution time breakdown by layers on training differentiated models on a single machine. We see that the conv FC, convolution or fully connected layers are dominant on those shallow networks such as AlexNet or VGGNet. However, in those deep and recent networks such as ResNet or DenseNet, they become less dominant. This is because those models heavily use BN as well as conv, and also they use smaller conv filters, reducing convolution computation task, and there are also new layers supporting skip connections, such as concatenation or the element-wise operations. So for those networks, non-conv layers, which are other than conv FC, are becoming heavier, and BN, especially the blue bar, takes up a large portion among those non-convs. So interesting point here is that these non-convs are typically bounded by the memory bandwidth. So to see the memory bandwidth bottleneck of these non-convs and potential speedups without the bottleneck, we did a simple experiment modifying some codes of a framework, and we turned every main memory access of BN and ReLU into L1 cache hits, so that thereby giving infinite memory bandwidth effectively. So in that hypothetical machine with infinite bandwidth, we get large speed of about totally 60% on DenseNet. And definitely this is not possible in real hardware. We cannot provide the infinite bandwidth. So what we do instead to remove, to reduce the memory access on those non-conv layers are layer fusion technique. So what is layer fusion? Each recent model, CNN model, usually has its own repeating basic layer patterns, whatever it is called composite layer in DenseNet or the residual block in the ResNet. So here, what layer fusion does is that basically fusing the adjacent layers into a single fused layer. For example, here we can fuse the batch norm and ReLU together, making a single fused layer. So here comes the question, can we fuse all these layers together in a basic block in a training recent CNN models, so will they work well? To answer that, let's look at the basic data access patterns of a popular layer. Say, we have input feature maps having having dimensions of she channels along with height and width, and also there are n independent images, which is definitely the batch size. So let's say we have a convolution layer here. So for each weight filter in this convolution, these filters slice through the input feature maps, thereby making alpha feature maps of alpha channel. And here comes another weight filter, which also slices through the input feature maps and thereby making alpha feature maps on the different channels. So here, if we consider the total size of input and alpha feature maps of a whole batch, it does not fit into an on-chip memory typically. For example, on the right side, we have some conv layers from the DenseNet, and in each conv, the total feature maps are typically over megabytes or sometimes up to several hundreds of megabytes, requiring large off-chip memory access on these conv layers. So if we use larger batch size, for example, more than 100, which is a common case, the size could be way larger. So how to deal with that? So let's say we have another element-wise layer after convolution. For example, we can have a ReLU layer after convolution. So in this case, we can fuse them. We can fuse the convolution and ReLU together, making only one single fused layer. So here in the fused layer, we execute ReLU function as soon as an alpha comes out from the convolution. So thereby saving a lot of memory bandwidth demand on this ReLU layer, because we don't really need to read the info feature maps on this ReLU layer. So this is what they call interlayer data reuse, and this kind of layer fusion technique is so common in the modern machine learning libraries or backend vendor libraries or graph optimizers. Then what's the problem here? Let's say we have a batch norm after convolution instead of a ReLU. If this is an inference case, BN can also be fused with convolution as like in a ReLU case. So because BN in inference is element-wise operation, because as variables used in the normalization, such as mean, variance, and gamma and beta, are all constants which are trained on the training phase. So as I mentioned, this is what contemporary ML libraries are doing already. However, in the training case, such fusion is not possible. The main reason is that the BN is no more element-wise operation in the training process, because we have to compute mean and variance per channel in this BN, and also in order to compute mean and variance, as they depend on every images in a mini batch, we need to sweep the entire mini batch for multiple times before normalization. So this kind of a data dependency within a batch requires off-chip memory accesses, making naive layer fusion less effective on training BN during training. So then let's clarify the challenge of data dependency on this BN layer and our optimizations. So this is kind of a computational graph of a forward pass on a very common layer pattern in recent model. For example, here we have a conv VN activation and convolution layers. So here are feature maps, weights, and operator of a convolution. And the important here is that there are circles denoting memory readings and writings on entire input or the alpha feature maps of a batch. So after convolution, we get the mean first, reading input feature maps, and then we compute variance. So with that mean and variance, we can now get normalized alpha feature maps. And there are also following value or another convolution layer after that. So what is the challenge here? The challenge here is that strict data dependency between computing mean, variance, and the normalized alpha feature maps, each of which demands reading inputs multiple times, which become optional memory accesses, making BN hard to fuse with the convolution, the previous convolution layer. So this is our solution, what we call BN fission and fusion BNFF. The idea is very, very simple. First, in fission, we divide Batchnom algorithm into two sublayers, which is a sub-BN1 and sub-BN2. The sub-BN1 computes mean per channel and the variance per channel, while the sub-BN2 normalizes input feature maps. And after that, the fusion comes, which is fusing each sub-BN layer with its preceding or the following layers. For example, here, sub-BN1 is fused with the convolution one, while the sub-BN2 is with the following layers, ReLU and convolution 2. So let me show you the optimizations implemented here one by one. The first of all is MVF, which is mean variance fusion. Actual formula is like this. It sweeps input feature maps 2 times to compute the mean per channel and the variance per channel. However, if we exploit this simple mathematical formula, which is computing second moment instead of a variance, we can now compute mean and the second moment together, reducing one memory read on a whole batch, as the dependency between the mean and the variance is gone. So in this MVF, since we calculate the sum of the squares, it becomes more susceptible to arithmetic errors at floating point, right? So in this case, we can use the double precision only for mean and the variance storage to avoid error. However, we observed that the floating point is good enough to train models with MVF. So further to the MVF, the sub-BN1 can be now fused with its preceding layer convolution 1. So here we do this by accumulating each output of convolution to the storage for mean and the second moment. And because the mean and the second moment is they are per channel, their sizes are negligible compared to the sizes of the feature maps, we can save 2 optional memory accesses total on the whole batch by fusing sub-BN1 with the convolution 1. So after MVF, another optimization is a ReLU convolution fusion, which is very similar to the convolution ReLU fusion, but actually this was done in a reversed order. So it's like in fusing convolution and ReLU case. This also removes input and output of the memory accesses on feature maps. So with that RCF, now we can fuse the ReLU and the convolution 2 with the sub-BN2 layer, doing normalization and ReLU function and convolutional operation all together, thereby reducing 1 more memory accesses on the whole batch, totally 3 among the 6. So this is all about the forward pass. Then what about the backward pass? So backward pass is shown here, actually proceeding from the very right to the left. The main difference is that the memory accesses are not on the feature maps, but actually partial derivatives of feature maps, or gradients, what we call. So here in the backward pass, we can also apply the BNFF here, which is in a similar manner to the forward. However, for the full explanation, please refer to the paper for that because of the time constraints. So here, I just simply illustrate the reduced optimal memory accesses on a whole batch. So as fusion goes by, we save 1 read and write on partial derivatives from a sub-BN1 and the convolution 1, and 1 read more from the sub-BN2, and also gain 2 more from the ReLU and convolution 2. So although they are all different in their dimensions, roughly we can say 5 among those 9 read and writes. However, actually there are more memory accesses because we should count reading intermediate feature maps at the forward pass, and also there are memory accesses on computing derivatives of weight filters. So these are alpha. Then how did we evaluate our schemes on the modern CNNs? On those basic layer patterns in two CNN models, ResNet and DenseNet, we applied BNFF here. First, the two sub-BNs are shown in different colors. So first we apply RCF here, thereby fusing ReLU and the convolution layer together. Then after that, we apply VNFF. First, we apply fission by separating all BNs into two sub-BN layers, and then we fuse them to each neighbor, whatever it is, convolution or the L-twice layer. So this is the result. And here we see that finally one last remaining sub-BN1 in the composite layer, which can also be fused with concatenation by interconvergent fusion, what we call ICF. So this is the final figure on the two Shannon models. So this is our experimental setup. We evaluated on Skylake Xeon CPU servers having about 3 teraflops, and we also used Intercafe modifying MKLTNN, which is an open source DNN library and high performance hand optimized in assembly level for Intel products. Also, we evaluated performance on the NVIDIA GPU. We did that by fusing multiple GPU kernels together in default gem implementations. For example, we can do per thread block reduction at the very end of the gem kernels on the convolution. So to implement that, we adopted and modified NVIDIA Cutlass, which is an open source gem library from the NVIDIA. So this is a chart of execution time on training with our schemes with ImageNet dataset. So y-axis is the execution time per iteration at batch 120, which is definitely the lower is the better. And the x-axis is incremental schemes in the forward and backward pass on those two target networks, DenseNet and ResNet. So here in the baseline in DenseNet, we see a great amount of time is spent in the BN and ReLU. And this ReLU portion is gone, giving speed of around 9% with RCF ReLU convolution fusion. We see the convolution portion, the yellow bar, increased a little. This is because the ReLU function was merged into the convolution. So however, the advantage from the fusion dominates, so we can get some speed up around it. On that number, invariance fusion brings more speed ups in BN. And after that, the VNFF brings around 30% of speed ups in total, although the convolution portion increased a little, as the same reason as I mentioned. And also this could be further pushed with the intercomposite fusion, ICF, which is estimated. And what about the backward? In the backward, we can apply also the RCF fusion, ReLU convolution fusion, which brings a similar speed up to the forward case. And however, MVF is not available in the backward pass because we don't compute mean and the variance in the backward pass. There is no such fusion at the backward pass. And after that, from the following two optimizations, we get less speed ups compared to the forward pass in their numbers, because the main reason is that at the backward pass we should read multiple feature maps from the forward several times, so the memory access reduction ratio was kind of diluted. And also, this was a result from the DenseNet, and these are results from the ResNet. So the ResNet shows a similar tendency, but have less speedups compared to that of the DenseNet, because of the main reason is that the difference in the non-convolutional portions and the model differences. Also, in experiments in GPU, we have total speedups about by around 70% and 8% on those two models. Although we have the numbers, the speedups, our main focus is on resultant CPU. Why? Because the main reason is that the baseline performance of the gem implementation on the GPU is not even close to the closed source cuDNN NVIDIA library. So we think that the evaluation of our work on high performance custom CUDA kernels with the VNFF can be a future work. So to summarize, as non-conv layers are becoming more important on those deep and recent models, and the BN is especially the most heavy among them, we restructure it with our BNFF, BN fission and fusion, by dividing BN algorithm and fusing them into its neighbors, so that we complement existing layer fusion techniques, reducing memory bottleneck problem on BN in training. And so finally, we achieved speed of about 25% and 60% on each of DenseNet and ResNet on a CPU-based platform. So this is the end of my presentation. Thank you for listening.
Okay, go ahead.
Yeah, Min-Sik from IBM. So essentially, you made a trade-off between like a space complexity and then execution complexity.
Sorry, trade-off between what?
Space complexity and execution complexity. So essentially, you will increase the memory footprint here, right?
No. Actually, the memory footprint is not increased.
But don't you need to compute x and then x square, and then keep them both at the same time?
At the sorry. At what?
At the same time, you need to keep.
Yeah. The key
right?
idea, yeah.
So essentially, at the moment, your memory footprint will be increased.
No.
So my question is, so by using this technology, I'm curious if I need to reduce my maximum batch size. And then if I need to reduce my maximum batch size, at the end of the day, it will hurt the throughput per device. So just I'm curious whether you have observed any change in the memory footprint.
That's an interesting question. So you're basically asking about the memory footprint on the MVF while we compute.
Yeah, for example, GPU has a 16 gigabyte, and then by somehow, if you increase your memory footprint, you have to reduce your maximum batch size from, let's say, that from 100 to, let's say, the 60. So if that's the case, actual throughput per device may be decreased.
Actually, the mean and the variance, storage for the mean and the variance is quite large because it is per channel, so their size is negligible compared to the feature maps. So I don't think that that could be a problem in our MVF.
Go ahead.
Leon Colon from McKinsey. Have you considered how this method might impact internal covariate shift down the line by fusing these layers together? And if not, how do you think it might change?
Sorry, could you speak slowly?
Sorry. Have you considered how fusing batch normalization with the convolutional layer might impact internal covariate shift? And if not, I mean, how do you think it might change?
Actually, the covariant, we don't change the algorithm itself. We just give a little difference in the order they are computed. So I think that the covariance shift or something might be the same as before and after from our techniques.
Thanks.
Go ahead.
Hi, my name is Takeo Imai from National Institute of Informatics in Japan. Thank you for your interesting talk. My question is that is this technique effective also in inference phase? And did you try the speed up the inference phase?
Inference?
Yeah.
As I said, in the inference case, as the batch normalization is the element-wise operation, which can be fused with the convolution or the other layers which are already done in the modern ML libraries or graph optimizers. So our focus is on targeting the training. As
So maybe sometimes we want to fuse the networks and in training, both in training and inference. And so can I reuse the fuse the network in training and also in inference?
I mean that the fusion, this kind of a layer fusion, the existing layer fusion exists in the modern ML libraries or the graph optimizers, whatever it is, training or the inference. However, we extend it on the BN while training, so that's the key part of our talk. So I think inference already in the inference already BAS norm has no problem in that fusing with the other layers.
Thank you.
Yeah,
Okay, thank you.
Yeah.
Let's thank the speaker again. Our third speaker today is Asaf Eisenman from Stanford University. He's a final year PhD student here, and his research interests include cloud computing and storage systems.
Thank you. So I'll talk today about Bandana, a system that uses non-volatile memory for storing deep learning models. And this is joint work with colleagues from Facebook and Stanford. In this talk, I'll focus on recommender systems. So before we dive into the details, let me give you some background on how these systems work and why they need so much storage. So let's take, for example, the case of matching a user with the most relevant posts. Imagine that the user logs in, and then we compare the user with multiple posts, and we try to predict the probability of a click for each post. The idea is eventually to show the user the posts that are most relevant for the user. And the question is, how do we generate this prediction? So we do it based on the past activity of the user, for example, the pages liked by the user, and we do it based on the main characteristics of each post. For instance, the main words in the post. In general, we call these features. We then feed these features into the neural network, and the neural network will generate us the probability of a click. Now the question is, how do we represent this feature? What exactly do we provide the neural network? So let's take, for example, the feature that represents the pages liked by the user. And let's imagine that these pages are movies. And the straightforward way would be to just assign a unique ID per movie. And if a user, for example, like the movies Shrek and The Incredibles, the feature vector would just look like this, 1, 0, 0, 1, 0, and so on. The problem with this kind of representation is that we don't know much about the relationship between the movies. So if we have lots of information about Shrek, but not so much information about The Incredibles, we don't know whether we can apply information from one movie to the other. So what if we add another dimension? And the two dimensions that we use that can represent different things, for example, whether it's a children's movie and whether it's blockbuster. And now we see that Shrek and The Incredibles, they share some things in common because both of them are children's movies and blockbusters. And what if we add even more dimensions and keep an entire vector per movie? And the elements in these vectors, they can have different meanings. And these vectors is what we call the embedding vectors. And the table containing them is what we call the embedding table. So you can tell that these embedding tables may become very, very large, because here we see that we have a separate vector for each possible page. And of course, we keep a separate table for each feature. So one table will represent all pages, and the separate embedding table would represent all possible words. So in general, the embedding table may consume very high capacity. So let's go back to our example of matching the user with the most relevant posts. So we look at the past activity of the user and the main characteristics of each post, and then we load the corresponding embedding vectors for each feature. We then feed these embedding vectors into the neural network and get the probability of a click. So you can see that the embedding vectors are right in the critical path, because the neural network can't generate any probability of a click before we provide it with all the embedding vectors. And that's why the embedding vectors are usually stored in DRAM, because they are very performance sensitive in terms of latency and in terms of throughput. Let's talk more specifically about the embedding vectors in our workload from Facebook. So the embedding vectors in Facebook are actually much larger, and they can contain 64 elements or 128 bytes. They are stored in DRAM for performance, And in Facebook, there are thousands of servers that are only dedicated for storing and loading these embedding vectors in DRAM. And these servers are DRAM capacity bounded. As we saw, recommender system can require a very large amount of DRAM for storing their embedding tables, and the model sizes are only expected to increase in the future. Because DRAM is becoming prohibitively expensive, our goal was to design a cost-effective storage by storing the embedding tables in the NVM instead of DRAM. And why NVM? So first, NVM is cheaper than DRAM, but it also has better performance than Flash, with up to 10 times better read latency, and its endurance is also about 6 times better than the typical TLC Flash. And when I say NVM, it may be confusing because NVM has two different form factors. So one is byte addressable, that is based on DIMMs, and the other one is block addressable, that is based on PCI Express. The byte addressable NVM is faster, but it is also more expensive, and that's why we chose to use the block addressable NVM, which is not as fast, but still faster than Flash and not as expensive as the byte addressable NVM. Just to give you an idea about what I mean by replacing DRAM with NVM, so the idea is instead of storing all the embedding tables in DRAM, to only keep a very small layer of DRAM as a cache, and then store the embedding table in the NVM. The first naive policy we considered, which we call the baseline policy, is to simply cache the vectors one by one. So the lines that we see here represent the embedding vectors, and the squares inside the NVM represent the NVM blocks. So if a user liked a content that is associated with these 3 green embedding vectors, we first make room for them in the cache by evicting other vectors, and then we simply read these 3 vectors and allocate them to the cache. The problem with this policy is that even though we only read one vector out of each NVM block, we still have to read the entire NVM block because the NVM device is block addressable. So if the block is 4 kilobytes, we only use 128 bytes out of it. The read utilization is very low. We use the term effective bandwidth to describe the percentage of the bandwidth that is read by the application. And we see here the average NP99 latencies as a function of the application request throughput. And this is for the ideal case where the effective bandwidth is 100%. Unfortunately, as we just saw, in the baseline policy, this is not the case. And the effective bandwidth is much lower because we only use 128 bytes out of the 4 kilobyte blocks. And the latencies for the baseline policy, they look like that. So they explode very fast because we saturate the read bandwidth. So our general problem is how can we effectively store fine-grained data on a block device? Or in other words, how can we maximize the effective bandwidth? Another approach is instead of fetching the vectors one by one, to prefetch the entire block that belongs to the vectors that we are interested to read. And in theory, we get it for free because we have to read the entire block anyway. But unfortunately, this performed very badly and actually reduces the effective bandwidth by 90%. And the reason is that most of these prefetched vectors are never read, and the only thing they do is to trigger the eviction of more useful vectors. And that leads us to our first goal, which is storage partitioning, or in other words, how can we store vectors that are likely to be accessed together in the same physical location, in the same NVM block. The first partitioning strategy we explored is based on the values of the vectors. The intuition is that similar vectors might also be accessed together. For example, if a user liked the Incredibles 1, there is a very high chance that the same user also liked the movie Incredibles 2. So these two movies will be accessed together, and they share very similar embedding vectors. And for this kind of semantic partitioning, we can simply use a clustering algorithm like K-means. So imagine that these are the vectors, and we run k-means to cluster them into k clusters, and then we use these clusters to partition them into NVM blocks. These are the results after we partition the vectors using k-means. So the y-axis here is the effective bandwidth increase, the x-axis is the number of k-mean clusters, and the different lines represent different embedding tables or different features. So you can see that some tables get up to 3 times better effective bandwidth, and in general, the effective bandwidth increases with the number of clusters. But unfortunately, the runtime also increases exponentially with the number of clusters, and that's a problem. In the paper, we show that we ran k-means also in a more efficient version where we run it recursively in 2 stages, and it was much more efficient, but still, eventually we reached the conclusion that while k-means can provide significant bandwidth benefits for some embedding tables, in general, similar values do not guarantee a similar access pattern, and for other tables, we didn't see any benefits at all. In addition, embedding vectors are frequently changed. In Facebook, it can happen every hour, and that means we will have to rerun k-means very often. So another approach is, instead of using semantic partitioning, to use the past accesses to predict which vectors will be accessed together. And for this approach, we use an algorithm called the social hash partitioner. Let's see how it works. We keep a list of the past queries, which are the squares here, and the circles represent the embedding vectors that are associated with these queries. And the objective is to minimize the number of blocks that satisfy each query, what we call fan-out. The first step is to initialize 2 buckets randomly, and then we try to find a pair of vectors which we can swap to reduce the fan-out. Let's see an example. So you can see that these 2 queries access both buckets, but if we look at vectors 4 and 7, we can swap them like that, and now each query accesses only 1 bucket. So we were able to reduce the fan-out. So we do this iteratively for all possible pair of vectors until we don't find any vectors to swap. And then we just split the buckets again and run the algorithm recursively until the bucket size reaches the size of the NVM block. These are the results after running social hash partitioner when we have unlimited cache, so no evictions yet. You can see on the left side that the effective bandwidth increases by up to 6 times for some embedding tables. On the right side, you can see that the runtime is less than 7 minutes for all the embedding tables, which is very reasonable because we intend to run it offline after training. But unfortunately, DRAM is not unlimited, and it is actually very limited. So that brings us again to the question, if we read 1 vector out of an entire NVM block, what should we do with all the other vectors? We saw earlier that without partitioning the vectors, if we just prefetch all the vectors, we decrease the effective bandwidth by 90%. So now, if we use the social hash partitioner, and then prefetch all the vectors, it doesn't look as bad, but it still improves by only 1%, which is basically nothing. So that brings us to the second question, or the second goal, which is to design an effective cache policy that can maximize the vector hit rate in the DRAM cache. We tried several techniques in the paper, and the one technique that had the biggest impact is setting a threshold on prefetched vectors, or in other words, to only cache prefetched vectors that were read 3 times in the past. Here, for example, we see the effective bandwidth increase as a function of the access threshold for 2 different cache sizes, the yellow and the blue. The important takeaway here is that for different cache sizes and also for different embedding tables, we have different optimal threshold. you can see that for the yellow cache, the optimal threshold is 5, and for the blue cache, the optimal threshold is 10. The question is, how can we choose the optimal threshold? Ideally, we would want to experiment multiple thresholds, multiple configurations, but of course, this is very expensive. So instead, what we do is to run cache simulations. So we only sample a very small portion of the requests, like 0.1% of the traffic. And then we use these samples, these cache simulations, to create a very low overhead estimate of the hit rate curve as a function of the threshold. And apparently, this is a very good approximation of the right threshold we should use. So let's look at some end-to-end results. Here we see the effective bandwidth increase for different embedding tables, different features. And the different columns here represent different sampling rate. So you can see that these are the sampling rates that we use for choosing the prefetch threshold. And you can see that even when sampling only 0.1% of the request, we still get a very similar effective bandwidth increase to when we use the full cache, which is like an oracle in our case. Here we see the effective bandwidth increase as a function of the total cache size. Again, the different lines here represent different embedding tables or different features. And it is not surprising that larger cache provides better effective bandwidth because it has more room for prefetches and evictions are less expensive in this case. So to summarize, to our knowledge, Bandana is the first system to leverage non-volatile memory for storing deep learning models. Our main takeaways are partitioning the embedding vectors based on the past access pattern, prefetching the embedding vectors based on the number of past accesses, and using mini simulations to determine how aggressively to cache the prefetched vectors. Thank you, and I'm happy to take questions.
Okay, go ahead.
Hi, I'm Rosamund Daya from Spotify. You mentioned that the vectors can change like hourly, and I would guess that if you want to do like a rollback or something like that to use previous vectors, that's something that happens sometimes at least. How does that affect like your partitioning strategy and how that interacts with any kind of secondary storage where you keep historic vectors for rollbacks?
So it's correct that it may be changed every 1 hour, and for k-means it is more meaningful because k-mean is actually based on the value of the vectors. For the social hash partitioner, we don't take these online trainings into account, so we only run it once in a while when we do, let's call it a larger training. So we don't run it every hour.
Hi, this is Alex from Google. I'm curious, when you were clustering the embeddings, why did you cluster them based on content instead of access pattern? Like the set of queries that have each embedding active or something like that?
So I'm not sure if I got your question correctly. So the first approach that we used was using the values of the embedding vectors. But then the second approach, which is the one that we use,
like
we don't use
when you were clustering the embeddings, which was the first approach.
Yeah, in the first approach.
Why did you cluster them based on the values instead of clustering them based on their co-occurrence patterns with queries? Because if you go, that would be actually robust.
So how do you suggest to do it?
You LSH?
With
there are
k-means
lots of ways of...
No, so I think what you describe is similar to what we do in the second approach, right? Which is based on the access pattern.
Hi, Leon from McKinsey. You mentioned that you moved away from k-means because of the scalability issue, right? Did you consider choosing something non-parametric, like a Dirichlet process instead, where you don't have to define a priori?
So scalability was actually not the reason we decided to move out from k-means, because I didn't show it here, but in the paper we showed that we ran k-means in a more efficient version where we kind of solved the scalability problem. We ran it recursively in 2 stages, and that solved the runtime problem. We chose the other approach because we realized that K-means doesn't work for all the embedding tables, for all the features. For some of them, the values don't mean that the vectors will be accessed together.
But how do you define like K? How do you make this optimal choice? Is it defined in your
for the K? For the K?
Yeah.
So it's a good question. We didn't come with an optimal K, but we also, again, we show in the paper that I think we cannot. I also showed one of the graphs here that you don't need a very large K in order to get to the saturation point when you don't get better performance with a larger K.
Go ahead.
Hey, Ash from Unity. I had a quick question on, in your social hash partitioner, how do you handle the problem of an embedding vector just never appearing, never having an access pattern, so a cold start?
Yeah, so it's a good question. Hopefully it shouldn't happen, but it may happen. So that's one of the things that we are trying to solve in the second part, where we use the number of past accesses to decide whether we should prefetch this vector at all or not. So in the social hash partitioner, if it was never accessed, it would just randomly be positioned somewhere. And then we hopefully will not prefetch it, because we will see that we don't have any past accesses, and then it will just never be prefetched.
So have you run experiments to see if this affects performance in practice? Because it's getting accessed, and that removes the advantage of loading a block at one time?
So I'm not sure what you mean. You mean that if... So we know that we can't like partition the vectors with 100% utilization. That's exactly what we're trying to solve, again, by setting a threshold for the prefetch that for the vectors that we prefetch. It's not, we can't like reach the 100% utilization, but we're trying to maximize it as much as we can.
Agreed. I guess what I'm trying to understand is at what point does it break down? Say there is a scenario where there is an X percentage of cold start vectors. Assuming that you're less than X, it works fine and that you can load blocks and it's super efficient. You don't have that many cache misses. But then I'm assuming there is some sort of you go beyond X and you'd have to rework the assumptions you're making.
So maybe we'll take it offline. I'm not sure exactly.
In the interest of time, let's take it offline. Yeah. Okay, let's thank the speaker again. Our next speaker is Sanguk Lim, who is a fourth-year PhD candidate from UT Austin. Before joining Austin, he worked at SK Hynix for 8 years. Currently, his research interests are memory system architecture and both the accelerator architecture and algorithms for machine learning acceleration.
Thank you for the introduction. Good morning, everyone. I'm very excited to talk about our work, mini-batch serialization, CNN training with Intel Air data reuse. As one of the speakers actually mentioned, training a modern CNN is a challenging problem. Well, it's mainly because it's already large and ever-growing data set size and the high complexity of network model. To accelerate such complex CNN training, a cluster of expensive accelerators with luxurious object memory system is actually used. So in this work, we actually challenge the need of expensive high bandwidth memory system for CNN training. So before that, let me talk about the data reuse opportunity in CNN training. So in forward propagation, the features extracted by convolution layers are getting feed-forwarded and reused between layers. And they are stored to option memory to be reused in the backpropagation to calculate the local gradient. And then in the backpropagation, the loss calculated at the end of the network actually getting backpropagated and reused between layers. And the convolution layer in the backpropagation has two phases, and their inputs are reused between the phases. And those normalization layers in forward and backward propagation actually use their inputs multiple times to calculate mean, variance, normalize, and also calculate their gradients. So in short, CNN training shows abundant data reuse opportunity between layers. However, capturing such interlayer locality in CNN training seems to be kind of challenging because of the conventional CNN training mechanism. Or mini-batch stochastic gradient descent is a very commonly used CNN training algorithm, and they have following benefits. Using a large mini-batch can increase the data parallelism at each layer in the network and reduce the number of model updates per training epoch, and then also it improves the stability of model updates. However, it also linearly increases the data footprint of each layer, so actually makes the reusing the interlayer data interlayer data is kind of difficult. And this graph here shows the size of interlayer data, which will be the features, and then the parameters per each layer used in RegNet 50. And here I use 32 samples per accelerator and floating point 16. So as you can see here, since their interlayer data size is too big, even using about 10 megabyte on-chip buffer space, we can only capture about 9% of interlayer data locality, which causes lots of expensive option memory traffic. So we can think of serializing a mini-batch as an easy solution. So we can propagate one or more samples, which I call like a sub-batch, through the whole layers, which here the size of sub-batch is actually fit on the on-chip buffer for all the layers in the networks. Even though we can capture the interlayer locality for all the layers in the network, this causes a problem because it reduces the data parallelism at each layer. It can actually affect the processing element utilization in the hardware. And also it actually requires many weight and weight gradient refetches because they are actually used between the different sub-batches. So our proposed mini-batch serialization mechanism, which I call MBS, actually partially serializes the mini-batch by adapting the size of sub-batch for different layer context. This is based on the fact that CNN has many downsampling layers. So basically, the later layers actually have a small volume of feature maps. So we basically increase the size of sub-batch for the later layers. So this actually can increase the data parallelism and also the intra-layer weight reuse for the later layers. So let me talk about how MBS works. So we first calculate the on-chip buffer space requirement for one sample for all the layers in the network. Here I use RegNet 50 as an example. So as I said earlier, since the later layers have smaller feature volume, their on-chip space buffer requirement is actually smaller. And next, using this information, we calculate the minimum number of sub-batch iterations, which is actually the opposite of the maximum sub-batch size we can actually use for different layers. So later layers can use much bigger sub-batch, so they can need to iterate a small number of times. And now we merge those layers with same number of sub-batch iterations into one layer group. So within each layer group, the same sub-batch is propagated and iterated. Even though this approach actually can maximize the data parallelism and also intra-layer data reuse for all the layers without actually refetching the data, interlayer data from the option memory, they actually have some problem because their first layer in each layer group has to fetch their inputs from the option memory. So we rather actually merge those layer groups into a bigger ones by forming a bigger layer groups by using a greedy search. How it works is like, so we basically estimate the memory traffic cost of merging two adjacent layer groups, and we only merge them when the actually cost goes down. So eventually, for RegNet 50, we have 4 groups, and this MBS mechanism actually balances the interlayer and intralayer data reuse. So let me use another figure to actually better describe how MBS reconfigures a training graph. So the graph on top is the conventional mini-batch-wise data propagation. Since their on-chip buffers, since their on-chip buffer space requirement for propagating all 32 samples is too big, they actually cause lots of data fetches from the option memory, which is indicated by the red arrows. And after byte reconfiguration by MBS, now we have 4 layer groups, And within layer group, the same sub-batch is actually getting forward propagated and iterated. And there's only option memory accesses for the rows, the data, at every first layer of each layer group. If we zoom in those like residual module in RegNet, it looks more obvious. In case of the original graph, we basically have to fetch the inputs for all the layer from the option memory. But instead, in MBS, we only fetch the inputs for the very first layer in the very first layer group, removing lots of option memory traffic. And in backpropagation, we don't need to store their outputs to the option memory, so it actually removes more memory traffic, and then it actually slightly has a different grouping configuration compared to the forward propagation, because their data reuse pattern is slightly different. And MBS also further saves the memory traffic by reusing the data between branches. As modern CNNs have many multi-branch modules, such as residual module and inception module. And as you can see here, between branches, they actually share the same node. So between branches, they have to fetch their inputs or outputs. And since MBS can serialize the mini batch, and then they can easily allocate additional space on chip to store those shared data, so we can remove those traffic and further saves the option memory traffic. Although it looks good, it has two major challenges to realize MBS. The first thing is the feature normalization. The most commonly used batch normalization requires to propagate all the samples in a lock step. So it basically adds synchronization points across all mini batch. And also, even though we actually can use bigger sub-batch for later layers, still the early layers has to use a small sub-batch because of their large feature volume. So first, instead of using batch normalization, we actually use group normalization along with MBS. And unlike batch normalization, which actually normalizes the feature data across the batch dimension, group normalization normalizes the data within a group of channels, which is conventionally used for the object detection networks, which has a huge feature data, a feature map size, but we actually adopt them to the context of MBS here. To use them on MBS, it requires additional operations, which is reducing the per channel group normalization parameters across sub-batches. But since their size is very small, it adds very negligible performance and memory traffic overhead. We also evaluated their training accuracy using batch normalization and group normalization MBS, and they show very comparable validation accuracy. And before getting to the problem of the parallelism issue, so let me briefly describe the baseline computing core that we actually used for MBS. So we use 128 by 128 2D historic array for high data reuse, which is the same configuration of recent TPUs. And each processing element, this historic array, actually use mixed precision, floating point multiplication and add operation. We first convert the small convolutions into a GEM, which is a general matrix and matrix multiplication, for efficient execution on data parallel architecture, such as historic array, using image to column. So here we have two input matrices for the GEM, which is filters and features, and their configurations, their dimensions, M and K, are constructed by all convolution configurations. Then we tile the GEM to process on the historic array, here I show this toy historic array figure here. And then we use a weight stationary data flow in case of forward propagation. And how it works is so we first preload the weight onto each processing element in this historic array by shifting them vertically down. And when they are fully loaded, now we ship the feature data across the historic array. And then I call them a historic wave. So within each processing element, they actually conduct mixed precision multiplication and accumulation, and their outputs are merged by shifting them to downward all the way to the bottom of this historic array. And at the bottom of this historic array, there is an accumulation buffer. It actually accumulates the partial sum of the previous historic wave to the current wave. So now getting back to the parallelism issue of early layers, which has to use a small sub-batch. So if the bottom line is that if one of the GEM configuration, MNK, is smaller than the size of historic array, then the processing elements are hugely underutilized. But it seems like using MBS along with the GEM convolution is a pretty good match, because as the table shows, all gem M and K dimensions for forward propagation and the 2 convolution phases in backward propagation. The red text, which shows the dimension using the sub-batch size, actually effectively multiply by large feature maps for the early layers. So basically, they create a large number of systoric array entities maintaining high processing unit utilization. And then I told you that we use weight stationary data flow for the forward propagation in case. But it seems like it actually causes idling of many processing elements because it requires preloading matching weights for each systoric wave. As the figure here shows, the waves which coming from the top to the down to the systoric array is actually matching weight for the following systoric wave, but it can only shift it into the systoric array after the current systoric wave finishes its operation. So basically, there is a systoric array height number of idle cycles between waves. So we basically add additional register to double buffer the weights for the current wave and the following wave, and then we use additional register selection signals for weights and then features. So now in the new figure on the right shows that the weight for the following wave can be actually shifted into the systoric array even before current wave is fully processed. So it basically removes all the gap between 2 systoric waves. So I so far described systoric array cores to build wave core accelerator to efficiently execute mini-batch serialization. And I use 2 of those cores to linked by NOC, and I use global buffer size of 10 megabytes using 32 banks to avoid the bank conflicts. And then I double buffer both the input buffers of the feature map and also the feature filters. And then I triple buffer the accumulation buffer to actually concurrently execute some additional operation required for MBS. And I use HBM2, which has maximum throughput of 300 gigabyte per sec as a baseline memory system, which is a little slower, but because MBS doesn't require that much of object memory traffic. And I placed the vector computing array right next to the global buffer to fully utilize their bandwidth. So I estimated their area using 32 nanometer technology, and then it shows like 524 millimeters square, and the maximum throughput is 45 teraflops. So I evaluate our proposed idea using our developed simulator, and then we use mini-batch size per processor is 32 and floating point 16. And we evaluate them for 3 popular networks and using ImageNet. And then these are 5 configurations we evaluated compared to the baseline. PE double buffering does the bubble buffer the weight, so to remove the inter-wave P idling. And naive interlayer data reuse, basically reuse the interlayer data only when the entire mini-batch can actually fit on the on-chip buffer. And full serialization propagate the same sub-batch across the whole layers, which I talk about as a naive mini-batch serialization. And MBS is our proposed mechanism. So this graph shows the DRAM traffic per training iterations in gigabytes and for different networks and configurations. And the line graph shows the normalized memory traffic. And since I mentioned earlier, naive interlayer data reuse only can reduce the memory traffic by 0.8x because most of the layers, their interlayer data cannot really fit on the on-chip buffer. And full serialization further improves the memory traffic by 2.3x, and our proposed mechanism achieves about 4x memory traffic reduction. And this shows the per training iteration execution time in milliseconds for different network and configurations. And those 2 line graphs shows the normalized speed up compared to the baseline and the P double buffering. And P double buffering improves the performance by 0.15x by removing the gap between 2 waves. And then the full serialization improves the performance by 1.28 compared to the P double buffering, and MBS achieves further by 1.5x compared to P double buffering. And if you look at closely to the result for inception V3 and V4 for full serialization, their speed up is much lower than the LegendNet case because they have to propagate much small number of sub-batch at a time, and then they actually cause more number of weight and weight gradient refetches, which affects the performance. And lastly, I show the energy comparison. And this shows the energy per training iteration in joule. And then, unlike the other configuration, MBS achieves about 36% energy reduction. The region is actually smaller compared to the other ones. It like still does all the computation required for the training iteration. And its major gain comes from the reduced traffic and the reduced static energy. I also evaluate our proposed ideas on different buffer size. So here, this graph shows the execution time and memory traffic for three different configurations using 5 different on-chip buffer size. So compared to the other configurations, which actually show much bigger degradation in performance and also memory traffic, MBS shows very stable number, even using small on-chip buffer space of 5 megabytes. So this carries the important message that MBS can be actually enabled using the interlayer data reuse, interlayer locality, even using a very small on-chip buffer space. And next, we also evaluate our ideas to different memory bandwidths. So here, I use 3 different memory types, HBM2 and GDDR5 and LPDDR4. I just vary their number of chips to match their capacity. And the memory bandwidth of a GDDR5 and FDDR4 compared to HBM is about like 60% and 40% respectively. And their relative cost is like this. And the graph here shows the per training iteration execution time in milliseconds for 4 different configurations and 3 different memory types. And the line graph here is relative speed up. And compared to the other configurations, which actually shows a huge degradation in performance using smaller on-chip buffer, the op-chip memory bandwidths, MBS shows very small gap and variance between different memory bandwidths. And as you can see here, even using LPDDR4 with MBS still can perform better than P double buffering and shows a very comparable performance with naive interlayer data reuse. So this makes this actually says that MBS can enable using cheaper but much more bigger memory for CNN training. So let me conclude my talk. So basically, I introduced MBS here to enable the CNN training with interlayer data reuse, with small on-chip buffer and much cheaper but larger op-chip memory space to enable using much bigger batch size. And we do that by balancing inter and intra-layer data reuse using MBS. And we also introduced a wave core accelerator to efficiently execute the MBS graph. And it achieves 4x memory traffic reduction and 1.5x performance improvement. So as a high-level message, well, I think as a collaboration of algorithm scheduling and architecture can actually make DNM training more efficient. Thank you. And I can open for the questions.
Okay, go ahead. Hi, I'm Sharath from Expedera. I was wondering how does this analysis applies to RNN or maybe MLPs?
So talking about the RNNs, their interlayer data is a lot smaller than their model size. So benefit actually is a lot smaller. Yeah, that's actually evaluated, yeah.
Okay, and another follow-up would be, instead of using systolic array, if you actually consider any SIMD architectures, how would that look like GPUs?
So compared to SIMD, the reason I actually chose historic array is a more tricky problem because they have much bigger data, parallelism, right? So that's why I thought MBS can affect much more severely to the, computing unit utilization. That's why I chose it. But SIMD will be much. I guess that in case of SIMD, the problem will be also a little bit alleviated than this.
Thank you.
So Jung Ho Won from Seoul National University. Thank you for a nice talk. My understanding is that you change the definition or use a different kind of type of batch normalization, right?
Oh yeah, I chose different normalization technique,
different
right?
Did you use that different normalization for entire ResNet or the only kind of some part of the ResNet?
Entire ResNet.
Entire ResNet.
Yes.
Then can you apply your idea to existing CPU and GPU and achieve some, not similar, but some degree of improvement? You suggested new architecture and it's not real yet, right?
Yeah, I think the mechanism that I use is basically blocking the on-chip buffer space to the size of the, blocking the, the interlayer data buffering to the size of one-chip buffer. So as far as we know how much space we have in CPU, but the problem is like CPU is actually cache, right? So we cannot actually program. As far as we can program, we perfectly, the buffer them. But if CPU can provide the programmability on the buffers, then I think it's going to be more straightforward to apply them.
Hi, Cliff Young from Google. Excellent talk. I think you really put your finger on one of the fundamental issues we worry about in terms of getting the most out of these accelerators. I thought I'd ask about balance in design. It seems to me like your technique is great about trading off HBM usage versus on-chip memory size versus the speed of the compute units on the machine. But you didn't go meta. You didn't have a sense for what's the marginal return on having more on-chip SRAM, or if you could have a magic HBM that was twice the capacity or twice the bandwidth, or those sorts of trade-offs. Where do you think the limits are when we, 20 years from now, look back at building a perfectly balanced accelerator? Where should we be going for that?
Okay, that's a very high-level question. So I think there are many available, the papers actually showing the good match between the computation throughput and the memory capacity and the bandwidth. I think they probably just look at the conventional approach of CNN training or like RNN training. So in our approach, basically, we just try to just trigger a little bit to avoid that kind of requirement. But I probably have to think about it, but I haven't really thought about how we can actually extrapolate the requirement for this for future work. Yeah.
Thanks.
Okay, let's thank the speaker again. And this talk concludes this session, so we have a 30 minutes break now. Thank you.
Yes, I was gonna. Sorry, Marty. Nice to meet you. What was your name? Sarah.
Okay, everyone, if you could please take a seat, we need to get started with the next session. Okay, this session continues our previous hardware session, and it's focused on hardware and debugging. And our first talk is by Junwook Choi, and he's from IBM Research, and basically has research interests in high performance and energy efficient deep learning accelerator design. So let's give a round of applause to our first speaker.
Hi, I'm Jungwook from IBM Research AI. It's an honor to be here to present our recent work on accurate and efficient 2-bit quantized neural network with Swagas, Vijay, Kailash, and others. Here's an overview of my talk. I will start with the motivation of why we are focused on quantized neural net. Then I will present our QNN strategy, parameterized clipping activation for activation quantization, statistics-aware weight binning for weight quantization, and quantization in the presence of shortcut connections. Then I will explain how much system-level performance we can gain using our proposed schemes. Then I will conclude. We've been witnessing breakthrough in AI that starts to achieve human-level intelligence. Recently, IBM Watson and Google AlphaGo have surprised people with their outstanding performance on Jeopardy quiz show and Go Play. But this success is at the cost of intensive energy consumption. If we compare their energy savings, energy efficiencies with the human brain, there is still a huge gap. So to truly achieve human-level performance, the current AI needs to be more energy efficient. The conventional way of improving performance and energy efficiency is by scaling down the transistor size. But as the Moore's law is ending, the progress there has been slowed down. Instead, in IBM, we have focused on precision scaling with the rule of thumb that the reduction in bit precision results in quadratic energy savings. So starting with the first demonstration of 16-bit DNN training in 2015, we reduced the bit precision down to 8-bit for training and 4-bit for inference. And today, I will share our recent achievement of 2-bit DNN inference using quantized neural network. So quantized neural network is to train a model that can exploit precision reduced activation and weight. The overall training procedure is the same, but the key difference is that the impact of quantization is incorporated in the training, so that the network can adapt to the quantization error and become robust. There has been extensive work on quantized QNN, but most of them focused on expensive quantization schemes that results in slow training procedure and inefficient arithmetic unit. And some of the work tried to compensate the accuracy degradation by enlarging the network size, but that results in increased computational complexity. In our work, we focused on accurate and efficient quantization schemes so that we can truly take advantage of the system level QNN for the system level performance. So there are 3 schemes I'm gonna present. First is activation quantization, which automatically tune the clipping level to balance clipping and quantization error. and weight quantization, which exploit weight statistics to better capture the shape of the weight, and quantization in the presence of shortcut connection, which enhance gradient flow of training by not quantizing the shortcut. So let's start with activation quantization. So the challenge in activation quantization is that there is a trade-off in activation functions when we apply quantization. So output activation after ReLU tends to have large dynamic range. As you know, ReLU is the most popular activation function in CNNs, but if you directly apply quantization, then you will suffer large quantization error. As an alternative, a static clipping function has been proposed, like ReLU6, which take the large magnitude value be clipped by a fixed threshold, so that you can reduce the quantization error, but there is some information loss when the large magnitude activation is clipped. So there is some. So if you don't quantize, the ReLU works best. But once quantized, ReLU, the network with ReLU failed the convergence. Clipping function works better, but still there is a significant accuracy gap. So we can empirically show that there is a trade-off between clipping error and quantization error as the clipping level changes. But it's really hard to find this sweet spot because this is different for different layers and changes over training time. So our idea is to auto-tune, automatically find this sweet spot by training. So we propose a new activation function called parameterized clipping activation, PACT. In PACT, clipping level alpha is trainable parameter so that it's auto-tuned by the backpropagation. So this figure shows the function in the 4 paths and the gradient. So as you can see, if your clipping level is lower than some proper output activation, then it is guided to be increased. So we initialize alpha as a large value to emulate the emulate ReLU, but we regularize alpha with the L2 regularization so that it converges quickly to the small value. As you can see, there are different alphas for different layers, which is very different from the static clipping function. So we can empirically show that PAC could find the sweet spot that achieves lowest error. Let's move on to weight quantization. In weight quantization, the goal is to find the quantization scale alpha W that minimizes the difference between the true W and the quantized one. The previous approach uses mean at the first moment of W, which is the represented value for this distribution. For example, XNOR uses this first moment to come up with the analytic solution as a function of mean. But the drawback is that the first moment cannot capture the shape of the distribution well. So we needed to find a way to better characterize the weight distribution. The idea was to employ not only the first moment, but also the second moment, so that we can capture the overall shape as well. We conjectured that by having these two statistics, we can characterize alpha as a function of the linear function of the sort of standard deviation and mean. To validate this idea, we find alpha, the best alpha, for different 6 for 6 different representative distributions and plot it together in a one plot. Surprisingly, we observed that they are all aligned well with the line, indicating that alpha can be almost fully characterized by these 2 statistics. So by linear regression, we can find this coefficient, and using it during the QNN training, we just need to compute mean and standard deviation and come up with the alpha for quantization. This slide just to show how general our approach is. So we can extend our weight quantization scheme for multi-bits. And you can see that in all cases, the optimal alpha aligns well with our heuristics. And we can empirically show that compared to the optimal scale, our heuristics can achieve equally accurate quantization. So as the last point, let me explain the quantization in the presence of shortcut. We observed that when we apply quantization to fit-for network like VGG, it was quite robust. But when we apply quantization to the network that has shortcut, like ResNet, there was huge degradation. After thorough investigation, we found that the shortcut is very sensitive to the quantization. The shortcut is the path to flow the gradient in the backprop, but once it's quantized, then it suffers diminishing gradient problem. So as you can see, if we measure the magnitude of the gradient, when shortcut is quantized, its magnitude becomes so low. So we propose not to quantize shortcut, and the good thing about it is that its computational overhead is just 1%, so that it's negligible in terms of overhead. So by not quantizing shortcut, we could recover the magnitude of the gradient so that we could train the quantized neural net better. So all things together, we could achieve less than 1% degradation for CFAR10 ResNet with different depths. And also we could achieve like one of the lowest accuracy degradation and one of the highest absolute accuracy for both CFAR10 dataset and ImageNet dataset. So for CFAR10 dataset, we tried ResNet 20 as well as VGG. And also for ImageNet dataset, we tried AlexNet, ResNet 18, and ResNet 50. So these accuracy number was higher than the accuracy number reported to date. So far we covered our quantization schemes. The question then is how much performance we can really get from the system out of this quantization. We can always say that in high level there will be significant gain, but given the constraint on bandwidth, on-chip memory, and area, there's some limitation in the gain as well. So to better understand the overall performance impact, we employ a bandwidth-centric performance estimation model, which consists of set of cores, each of which is equipped with 2D systolic array with the fixed point MAG unit inside. The goal is to estimate effective throughput given area and on-chip memory and off-chip bandwidth constraints. And since the total area is fixed, the peak throughput is determined by the max per area, which can be increased as we reduce the bit precision. So we compare we compare the inference speed for ResNet 50 with varying bit precision. And for the large bandwidth scenario, we could achieve almost linear speedup for bit reduction. And for extreme case, there's some inefficiency in data mapping because there are so many data items when we reduce the bit precision to 2-bit. But this is the case when the bandwidth is very large, so that getting the data from the object memory is not that costly. But when we reduce the bandwidth to 32 gigabyte, we can observe interesting scenario where for the reduced precision case, we can achieve a super linear speedup. This is because the lower the bit precision, the more items can be fit into the on-chip memory, so that it can increase the data reuse. So from this work, we could conclude that our quantization scheme can improve not only throughput, but also data reuse to achieve high speedup. So one thing to note is that our quantization scheme does not increase the computation of the network to compensate the error. So compared to the case when which relies on such an enlarged network for a robust accuracy, we could further achieve 2 to 3 times speedup. So in conclusion, we discussed that quantizing activation and weights is critical for high performance and energy efficient DNN inference. So we proposed novel quantization techniques, both weight and activation. For parameterized clipping activation, we explained that we can tune the clipping level by training to find the sweet spot automatically between the quantization error and the clipping error. For weight quantization, we propose statistic-aware weight binning, which exploits the first and second movement of weight to better capture its distribution and reduce the quantization error. And also, we further propose full precision shortcut so that we can maintain the efficiency in training convergence. So we demonstrate accuracy and system performance gain on for the proposed QNN schemes, which improves the throughput and data reuse and achieve 2 to 3 times speed up over state-of-the-art QNN scheme. So that's all for my talk. I will happy to get any questions. Thank you.
Okay, we have a couple minutes for questions.
Harris Teague from Qualcomm. Can you say a little bit more about PACT and how the alpha is chosen, how you make it differentiable for training it as a parameter?
Sure. So our PACT function is a composition of this absolute function, and we take. Oh, sorry. So we use state-through estimator for the backpropagation. So the derivative for this quantization can be estimated. And further, the derivative over alpha can be defined like this. So when the output activation was larger than alpha, then the gradient is 1, otherwise it's 0. And there is initialization and the regularization to make it work better. So, yeah, no problem.
Hi, Rick Kaye with Microsoft. Just curious, have you applied this technique to already compressed networks, or do you have an intuition around, if you applied it to SqueezeNet or ENet or something like that?
So there's some ongoing work of applying these techniques to other networks, like MobileNet and DenseNet, and I think we don't cover SqueezeNet, but and LSTMs as well. And we hope that we can have more progress on there and publish to the conference again.
Okay, great. Let's thank our speaker again. Okay, our next talk is from Max Galoob, who is a software engineer at Mercedes-Benz Research and Development, and before that he did his master's at UBC working on, I think, the work we're going to hear about.
Mm-hmm. All right, so I'm going to talk about how to do neural network pruning while you're training without requiring a retraining step and letting you reduce the amount of memory you're going to need during training in the future. So I'm going to talk about on-device training in the present day. So on-device training in the present day is pretty limited. You have to have really small hand-tuned models to be able to fit that model onto your device, be able to retrain it, save all your weights and activations, and update it. And one of the two major reasons for this is you have limited memory bandwidth and you have limited power, especially compared to a GPU that's used for training today. So for example, if you compare the Apple A11 SoC to an NVIDIA 1080, you have a power budget of 150 watts on that 1080 and just 5 watts on the iPhone. And then for memory, you have the same story, where you have 320 gigabytes a second of memory bandwidth, but only 26 gigabytes a second of bandwidth on the iPhone. So we have to work with just 5 watts and 26 gigabytes a second. So how are we going to reduce the memory bandwidth during training? Well, we have two targets. We have weights and we have activations. So typically these are reduced after training. It's really hard to reduce them during training. And what people have done after training, there's a couple things that are out there. So you have pruning, of course, where you remove some of the weights, neurons, reduce the number of connections in your network. This also helps sparsify your activations, which you can take advantage of. Then you have teacher-student networks, which is a little bit of a different technique, where you have a big teacher network train a smaller, lighter, faster student network, which is used, for example, for Face ID. And then you can fit that on a device pretty nicely. Then you have quantization, which we just heard about. And that actually can be applied during training. You can train quantized networks if your accelerator supports it, for example, the V100 with FP16. And then, of course, you have sparse activations that can be taken advantage of with an accelerator like EIE. So just to be clear, we're going to focus on weights in this talk. We don't address activations in this work. But reducing weights is definitely the first really important step. And we have a wish list for doing this. We want to reduce the number of weights by an order of magnitude, preferably. We really want to preserve accuracy. It's not going to be very useful if we're going to take a drastic drop in accuracy to reduce the memory bandwidth requirement of these networks. And then finally, we also want to preserve the time to convergence. And the reason for this is if it takes 10 times longer to train your network on device, well, that's also going to end up using more energy than training it on a 1080 and then putting it onto the device. So the question becomes, how are we going to apply pruning to training? Which weights do we remove? So we went and looked at the literature and said, well, why don't we try magnitude-based pruning? It's the simplest technique. It's really easy to apply. And it's very basic. You just remove the low magnitude weights and set the remove weights to 0. So we tried this. We applied it from the very first iteration of training. And as you can imagine, this didn't work very well. We only got a 2x weight reduction on MNIST, which, of course, everyone knows is not very good. And the reason for this is basically vanishing gradients. It's basically like initializing 10% of the weights. So you have this random initialization, you set 90% of your network to 0, and now you can't learn anything. If you go above 2x compression, it doesn't converge at all, because again, the vanishing gradients. So the question becomes, what do we do instead? Well, that kind of leads us to our first insight that we had. Weights are a combination of two separate things, right? They're a combination of that initial randomly generated value and the accumulated gradient over time, which we say it really does represent the learning. How far you move that weight over training tells you how important that weight is to the network, how wrong that initial guess was. And what we found is most weights learn very little. So you see here, this is in a 90,000 parameter network trained on MNIST. Almost 35,000 of these weights barely move from their initial values at all. And then we have a few weights that account for all of the learning on either side here. Those weights move very far from their initial values, which could be 0 or it could be a really high number going towards 0. Both are valid things that we want to keep. So the key takeaway from this is that we want to keep the weights that learn the most. Those are the weights that we're going to save, and we can forget about everything else. So what do we do once we selected those weights? What if we set them back to 0? Because that'd be really nice. We get some computational sparsity with our memory sparsity. Well, unfortunately, this doesn't work either for pretty much the same reason as before. If you do that from the first iteration, it's really hard to learn anything. You can only really go down to about 2x weight reduction on MNIST. So what if we set them back to their initial values? Since we set them to their initial values from that first iteration, that works really well for training. Why don't we set things we're going to forget about, things we're going to prune, back to their initial values? Well, then the question is, how do we store the initial values? Do we put them in memory? Well, then we're just going to use the same amount of memory as storing all the weights anyway. It's not going to be very useful. So, at least to our second insight, is that the initial values are drawn from a random distribution anyway. So they're generated via a pseudo-random number generator feeding into a distribution, depending on what distribution you use to initialize. And the nice thing about this is you can seed that pseudo-random number generator and make it deterministic. Use the same seed, get the same result for each weight value. And now we've just removed that need to store any of the initial weights. We don't need any storage for the initial weights. Choosing the initial random number generator is also important. You don't want to choose a really expensive pseudo-random number generator. So we went with one called ZORShift. Which is basically consists of 3 shifts and 3 ZORs. So it's super cheap to do even on x86. On actual hardware like an FPGA or an ASIC, it's going to be extremely cheap. So for example, it only takes 10 clock cycles on x86. And then we calculated if each operation's worth like 1 floating point add, which is an overestimation, it'd only be about approximately 6 picojoules to generate one random number at 45 nanometers. Versus accessing a single 32-bit value from DRAM, which is 640 picojoules. So you save a lot by doing this. So the key takeaways from this is that we want to focus on the gradients and not the weights to select what to prune. And we want to regenerate those initial values so we don't have to store them. So now I'm going to talk a little bit about how dropback differs from training a standard, or the standard stochastic gradient descent process. So first, we generate those weights. We don't have to load them in from memory. Of course, we still have to save the activations during the forward pass of our training loop, calculate the error, as usual. And now we start our backwards pass, and we're going to generate those weights again. Calculate the gradients, which we can do incrementally, so you don't have to materialize the full gradient array. You don't have to store that anywhere. And then you update the track set, and the track set is where we're going to put those weight indexes and accumulated gradient values to access later on our next training loop. And to kind of make this a little bit more clear, I have another example on just a simple 3-neuron network, 6 total weights, 2 inputs, 1 output. And you notice down at the bottom here, we have our track set that we're going to fill up during our backwards pass. And so things that are going to be in green are going to be things that are generated. Things that are in red are stuff we still have to save back to memory. So starting with our input, our first layer, we generate weight 0, weight 1, weight 2, and weight 3 from our pseudo-random number generator. And we save those outputs because we're going to use them during the backwards pass. And then we move on to the output layer, generate weights 4 and weight 5, calculate our error, and now we can start our backwards pass. So in our backwards pass, this is where things get interesting, right? So we see the update to weight 4, 0. We're never going to track an update of 0. It's just not going to be important. And then you see that the update to weight 5, we've put that into our track set now. Next time we do our forwards pass, we're going to generate that initial weight 5 value, and then we're going to go do a lookup in our track set and say, hey, we have a value here, and we're going to add it to weight 5 to get the full updated weight value. Same story for weight 0. Next time we use weight 0, we're going to look in the set, see that we have an update for it, and use that to create the full weight value. Now we've filled our track set, and weights 1, weights 2, and weight 3 have updates, but they're not higher magnitude updates than anything else in the track set. So we're not going to put them in our track set. These are less important than the other weights. Next time we use them, we're just going to drop them back to their initial values, see that they're not in the track set, and continue on from there. So how does this work? Before we even get to using this on a real network, we wanted to look if this followed basically standard stochastic gradient descent to a good level. So we measured this using something called weight diffusion, which is basically how far the weights moved over time during training. And you measure this diffusion using the L2 distance of your parameter vector between each iteration. And the interesting thing about weight diffusion is that you want just the right amount. You want to follow stochastic gradient descent diffusion. If you have too high diffusion, you've modified your training a lot, you move your weight values very quickly, it's going to fail to converge in a lot of cases because you've gone off to some deep end. And then with low diffusion, this is less bad, it's just slow to learn now. And remember, we wanted to converge at the same rate as standard stochastic gradient descent. So we compared this to that first technique we talked about, just applying magnitude-based pruning to training. And we saw that that had really low diffusion, as well as really bad compression results. So it's really slow to train. It took a really long time to train that way, which makes sense. You set so much of the network to 0, now you have a much harder training problem. We also looked at variational dropout, which is another really good pruning technique. That's train with pruning, get a pruned network after type. And that had really high diffusion. So you think it learns really quickly, and that's true for MNIST. But what we actually found when we were trying to replicate the results on C410 and ResNet is that we were unable to ever get variational dropout to converge. At least without, we tried tweaking some things, we still couldn't get it to converge. And then you look at dropback comparing to the baseline, and we have a really similar diffusion profile compared to the standard stochastic gradient descent. Your initial values start at exactly the same place, and as you update them over time, they track the L2 distance very closely. So now let's look at some actual results. So ResNet 18, probably the most interesting network to you guys. We trained this on ImageNet, and we got 11x weight reduction and matched the baseline accuracy of our chainer ResNet 18 network. So the key takeaway is we can reduce the number of weights in ResNet 18 by 11 times. Great, we've reduced the weights by an order of magnitude. We can also go a little bit higher. Say you have a really small device. You really want to reduce the network and maybe some accuracy loss is acceptable. Now we can get 23x weight reduction, 60% accuracy, and you only have to track 500,000 parameters out of the 11 million parameters in our ResNet 18 network. And again, going back to that convergence rate, for most versions or most track set sizes, we really closely follow the convergence rate of standard stochastic gradient descent. It doesn't take any longer to train with dropback compared to standard stochastic gradient descent. This is really nice. So, just to recap, we've reduced the number of weights by an order of magnitude, we've preserved the accuracy compared to standard stochastic gradient descent, and we've also preserved the time to convergence. We also tested this on a bunch of C410 networks. We tested on a modified VGG16 network that has much smaller fully connected layers and one less fully connected layer as well. DenseNet, which is a really parameter restricted network with lots of activations, and then WRN2810, which is a really high parameter network and it's really wide and lots of skip connections. And the really key thing to note here is that these numbers, these weight reduction numbers, 4.5 times for DenseNet and 7.2 times for WRN2810, to our knowledge, this is a state-of-the-art result, just even reducing the number of weights in these networks, period, with any technique. And we can do this wide training without needing a retraining step or without requiring more memory during training. So in summary, dropback tracks a subset of the weights, reconstructs their initial values, and rebuilds the full weights from the tracked and initial values. So some of you might be thinking, well, how does that track set change during training? Maybe that's an interesting question. Maybe we can get a little bit more performance out of that by looking at if there's any thing we can do there. And so what we saw is that the weight selection actually stabilizes really quickly. The things that you're putting into that track set locks down really, really quickly. Your first iterations, you're swapping in 2,000, 1,500 things, 1,000 things. And this, for this example, we're tracking 2,000 things total out of 90,000 parameters. But once you get to iteration 10, iteration 25, iteration 50, you've really settled down to only swapping in the back part of that set, the really small things that are a little bit less important than the things that you've put at the front of that set, the really high value updates. So let's freeze that track set, because this is going to further reduce our writes to memory. We don't have to do any kind of partitioning or sorting or updating our data structure to keep that track set in order. We can just focus on updating the values internally. So let's freeze at iteration 50, for example. And then, all we have to do is update the values. We don't have to do any more sorting or anything. So what we found is we tested this on our reduced VGG16 network. which has a total of, I think, 14 million parameters. And then what we found is that lower compression ratios, this works really well. Freezing early is fine, which makes sense. You have a lot of track parameters, so that bottom part of your track set is just inherently less important. However, the story changes at high compression ratios. Freezing early results in a pretty significant drop in accuracy. Again, makes sense. Now we have a much harder problem selecting those parameters that are going to be in that, say 500K track set, 1 million parameter track set. That's really important to get exactly the right parameters. So you don't really want to freeze in this case, or you want to freeze in epic, 100, 200 instead of epic 5 out of 300. So, in summary, dropback prunes by training, and it will enable memory footprint reduction in the future with custom accelerators, and it will open up training on edge devices. And of course, the next step to the other part of this is that we have to address activation compression as well, which we're working on.
Great, we have plenty of time for questions.
Yeah, Min-Sik Cho from IBM. So I don't know whether you're aware of the paper from Uber last year, like intrinsic dimension, intrinsic dimension.
Yes, I remember reading
So in the
it.
paper, they are claiming that actually we don't need to track weights. I mean, just like as long as you select like enough number of random weights, it will converge, and then they can. I mean, they show that like it can achieve amazing compression as well. So why do you? I mean, considering the paper, why do you want to track here when they're claiming that you don't need to track, just like randomly selecting enough number of weight is okay?
If I remember that paper correctly, it has been a while since I read it. That paper was focused on basically, again, figuring out the intrinsic dimension, exactly how many parameters you need to have in a network. It wasn't really focused on enabling you to train with reduced memory, which is what we're aiming for with this technique, if that answers your question.
Other questions?
Have you tried this outside of the extremely constrained case and look at sort of the, like, taking the existing big hardware and training something even bigger with it?
Not yet, and that's something we're currently looking at, definitely.
Thanks.
Yeah. Okay, let's thank our speaker again. Okay, so I want everyone to wake up a little bit here. I know we're kind of in that middle 2/3 through the conference. A lot of things going on in your head, but we have plenty of time for questions, so let's think of some for this next talk. Anyway, so our next talk is by Cedric Rengley, and he's a PhD candidate in the systems group at ETH, and his research interests include sort of human interactions in machine learning and also optimization techniques for distributed machine learning algorithms.
Thank you very much. Hi everyone, welcome to my presentation. My name is Cedric. I'm a PhD student at the Systems Group at ETH Zurich. I'm going to present to you our first steps towards building a continuous integration engine for machine learning models. Research in machine learning and systems mainly focused on two aspects in the last decade. The first one is speed. Researchers tried to tackle the question on how to train large-scale models with a huge amount of data faster and more efficiently by fully utilizing the underlying hardware. The second aspect is automation. Many leading tech companies released their AutoML system in the last few years. We in our group developed two small prototypes to tackle both problems for our users in academia and industry. With machine learning systems becoming faster and more automatic, we asked ourselves, is this enough for our users, especially those with little or no computer science background, to use the systems fully by themselves? We made a key observation there, and that is that for some of the users, if they're not really careful, they have nothing else than a more powerful overfitting machine. So in order to prevent this, we wanted to provide some guidelines for the proper machine learning system usage. SysML CI is a first step in that direction. Our system is a continuous integration engine for machine learning models. You can think of it as being very similar to continuous integration engines known for traditional software engineering, such as Travis CI. In our context, we have a bunch of developers. They access a local development set in order to gain some insights and do some error analysis. We also have a shared repository where the current model active in production is stored. On this repository, there is a test set which is not accessible to the developers. Developers will then engineer and train a new model they want to push into production. In order to do so, they commit it to the repository. Our system will then make use of the test set in order to check whether the new model satisfies some requirement given in an additional file. After evaluating, either the requirements are fulfilled or not. If not, the system will return a failing signal and reject the new model. If the requirements are fulfilled, the system will return a passing signal and replace the current model in production. So what is hard about this? Well, there are two main challenges. The first one is we want to give rigorous guarantees but remain as cheap as possible. What do I mean by that? Our test set is used as a statistical estimator for the unknown underlying distribution. In order to have a high accuracy of this estimator, we would need a large test set. So we want both to have a high accuracy, but the test set should remain as small as possible. The second challenge is, even though developers have no access to the test set, returning a pass or failing signal on the requirements leaks information about the test set, and eventually developers will overfit to it. This is commonly known as adaptive analytics, and this is the main technical component of our system. The core results are statistically sound estimators to reduce the sample complexity by 1 or 2 orders of magnitude. Let me give you a more detailed overview over our system. We have two bunch of actors. On the one hand, we have developers which task only consists of engineer and train new, better models. The managers deal directly with the end user's need and specify the requirement every new model needs to have in order to become active in production. They both have access to a shared repository. Managers provide the test set in an encrypted, protected way. The training and validation data is made available publicly. So first, managers need to specify the requirements every new model needs to fulfill. Such a requirement could be, for instance, that all models checked in should have an accuracy higher than 80%. Remember that our test set is a statistical estimator, so we need to define the epsilon delta approximation we want to achieve. Developers' task consists of committing a stream of T model, and after every commit, they will get back a pass or failing signal. After T iterations, or when the test set loses its statistical power, the system will ask managers to provide N new test labels and downgrade the current test sets to be available for developers. As I said, managers need to specify the requirement in a given file. We currently support various types of requirements. One could be, for instance, that every new model needs to be better than the old model by at least 1% with high probability. We can also bound the difference in predictions between the new and the old model, or even have a simpler requirement where we only query the accuracy of the new model and ignore the accuracy of the current model active in production. We can also combine multiple requirements. Developer may only focus on engineering and training new, better models, and once they have one, they will commit it to the system. System will then evaluate and sometimes return a failing signal. Based on that insight, developers can re-engineer and come up with a better model and recommit. Eventually, they will hopefully get back a passing signal. As I said before, the core technical component of our work is adaptive statistical queries. This part of our work is inspired by seminal work given by the Ladder paper in 2015 by Blumenthal and by differential privacy work given by DeWork. What is adaptive statistical queries? Well, in adaptive analytics, you have an IID sample data points from an unknown distribution X. Developers have no access to that data. Initially, developers will commit the function f1, which can be seen as a function used to evaluate the accuracy or the difference in prediction. The system will then make use of that function, apply function g, and return its value to the user. This function g, in our case, is the binary signal of passing or failing the requirements. Based on that result, developers will come up with a new function f2. The system will reapply the function g and return the value to the developer. This goes on for capital T steps. The contract between the system and the developer is given by this epsilon delta approximation. Epsilon defines the size of the confidence interval, and 1 minus delta is the probability of falling inside this confidence interval. So the question we ask is, given epsilon delta and t, how large does our test set need to be? And can we decrease the dependency of n on epsilon delta and t as much as possible? For a single step, there's a simple solution in order to lower bound the number of samples we need. Hafting's inequality. If we define this probability to be equal to delta, we can simply rearrange and get a lower bound on n. For multiple steps, it's not that easy, but there are two main work which I will quickly mention here. The first one is our baseline approach, which basically resamples at every iteration and applies Hafting every single step. The second one is given by the Ladder paper, but it constrains on how G can evolve over time in order to apply those optimization techniques. To show you why this is not really feasible in our setting, let me give you an example for epsilon, delta, and t values which are reasonable in our context. Epsilon is set to be 0.01, the probability is 99.9%, and we set t to be equal to 32. I will stick with this number 32 throughout the entire presentation. Why 32? Well, if you think that developers commit a new model every single day, we will get the number of samples we need for an entire month. So the baseline approach would need roughly 1.7 million samples in our test set. And breaking it down to the number of samples per day, this is simply too expensive. The Ladder approach would be more feasible, but we cannot apply their optimization technique because in our case, G is non-monotonic. For the sake of completeness, I have to mention that there are other related work in adaptive analytics inspired by differential privacy. Nevertheless, we don't really know how to add noise to our G function in CI, so this will be future work. So our goal is basically to optimize the sample complexity for specific regimes that our system cares about. To this end, we provide a bunch of optimization techniques, and I will focus on the first and the third and the fourth technique in my talk. So the first observation is that the most trivial approach is usually not that bad. What do I mean by that? Well, in our setting, we know that our function g returns a binary signal. Based on that, we know the number of possible functions for t iterations is upper bounded by 2 to the power of t. So we can simply apply union bound to all possible functions. In terms of formula, we see that we get rid of the log t term, but we're still linear in t. This is not a big issue for us because we're not dealing with too large values for t. For the same numbers for epsilon, delta, and t as before, we know the baseline needs 1.7 million samples. We can reduce this by 1 order of magnitude by applying this trick. For the second observation, I focus on those type of conditions, which are the most popularly seen amongst our users. That condition has two parts. The second part bounds the difference in predictions between the new and the old model, and the first part requires new model to be better than the old model in terms of accuracy by at least 1 percentage points. While the first part is quite natural as a requirement, the second part ensures some quality and prevents undesired behavior when the end user uses the new model. We have two sub-observations here. The first one is, in order to determine the difference in predictions, we don't need labels at all. I will come back to that. And the second one is that conditioned on d smaller than 10%, we know that n minus o must have a small variance. We can make use of that fact by applying another well-known concentration inequality called Bennett's. By applying Bennett, we basically can reduce the 1 over epsilon squared dependency compared to Hafting. Again, with our set of parameters, the baseline now needs 7.5 million samples. Why is it more than before? Well, our condition is much more complicated, so we need samples to evaluate every part of the condition. With union bound, we can lower this by 1 order of magnitude, and applying Bennett's, we can lower it by a second order of magnitude compared to the baseline. So the last observation is that usually not all labels are useful. We've seen this for bounding the difference in prediction, but we can also apply this to bound the difference in accuracy. Let me show you an example. In this setting, we have 5 data points in a binary classification problem, which are unlabeled. The old model makes those predictions, and the new model predicts those values. So we see that the same predictions are not useful at all in order to estimate the difference in accuracy. So the question we ask is, if the new model and old model are only different in the prediction with certain probability, how many savings in terms of labels, not samples, can we have? And what we've seen is that if this probability is of order square root epsilon, the amount of labels we need is 1 over epsilon, compared to 1 over epsilon squared, the order of Hafting. So for a single signal, Hafting would need 15,000 samples, and having a probability of difference being equal to 10%, we would only need 2.2 thousand samples per signal, assuming that unlabeled data points are free. To give you an overview over actual numbers we can achieve, let me again look at the number of labels we need to provide for 32 models. We compare our baseline against the best optimization we can achieve in SysML. In the popular use case, we set epsilon to be rather small. For the most commonly used condition, we can decrease the number of labels needed by 2 orders of magnitude. And if you think about what 41,000 labels for 32 model means, breaking it down, this represents 1.3 thousand labels a day, which is not really much in order to get rigorous guarantees. For a simpler condition, the baseline requires less samples, but SysML is only able to achieve 1 order of magnitude saving, because we cannot apply all the optimization techniques here. If you're willing to increase your confidence interval size, the same conditions as above drastically decrease the number of labels we need. But we still have 2 order of magnitude saving for the most popular used condition, and 1 order of magnitude for the simpler condition. To give you a rough idea about how much 330 samples per day is, assume you have an engineer which is able to label a data point in 10 seconds. So this engineer would need to label data less than 1 hour per day in order to get those 330 labels per month. So I've presented to you SysML, our first approach to build a continuous integration engine for machine learning models. We are currently also working on a sister project, SysML Meter, which which monitors the degree of overfitting on your local development set. Both systems are planned to be released this summer. Let me conclude by saying to you that we in our group think that if machine learning is truly software 2.0, it is time to define principles in software engineering 2.0. And we as a group hope that we can benefit from the SysML community in order to reach that goal. I thank you for your attention.
Questions? So I have a question. You said you have this system. Are people using it now, or it's not released yet? You haven't.
It's not released yet. It's going to be released in summer. We currently have it for our own users, but it's more of a prototype currently.
Hi, Julio Zhao from Carnegie Mellon University. So I'm wondering if you had some thoughts on how some of these statistical techniques would generalize to more structured output spaces, like say object detection, or doing translations, or producing kind of masks, or basically things that are not categorical labels?
Yeah, so currently we focus on binary classification, that's true. We have ways to adapt this to multi-class classification, but adapting it to regression problem is still ongoing research.
Okay, thanks.
Thank you.
Hello. Thank you for this. This is absolutely wonderful. It's like an implementation of concepts, that I'm trying to communicate in my current project. So I plan to use it immediately. I'm wondering about the data sets, actually, for checking the models. Are you planning, how far into the future are you planning to support just one data set? And is that just, am I interpreting that correctly? In past implementations, because I've had to do this by hand, I've used numerous data sets, so I designed the systems to prevent regression problems. I'll have numerous data sets. So would that be something in the future to support?
Okay, so your question is basically, can we share the same data set for multiple models?
Yeah, and over time, I'm collecting.
Yeah. So currently we focus on one model which is currently active in production, and developers provide a new model, which goal is to replace the current model, and we want to use that data set for those two models. So extending it to multiple models or different tasks is not something we have done yet, but it's definitely something we're thinking of.
Cool.
Hi, Evan from Quantum Black. I have a question from the examples you've shown there. It seems that you've put the data with the repository, like from the data sets.
Yeah.
Do you plan to have a way that you can have the data set in another system that's not accessible, or maybe you don't need to commit it in the...
So the only requirement is that the developer has no access to the data set, but our system, we plan to implement it as a service, similar to Travis CI, needs to access the data set and the committed model in order to do inference and predict the labels.
So essentially you would have a place to host the data set, and the data set will not be in the repository.
Yeah, yeah.
Okay. Thank you.
Thank you.
Okay, let's thank our speaker again. Okay, our last talk in this session is Martin Zinkovich, and Martin is a research scientist at Google, and prior to that was at Yahoo and did his PhD at CMU.
Thank you. All right. What's going on? So is this, can you switch it over to the USB-C port here? So I plugged it in, but it's not, is that power or is that, oh. Oh, wait, is this? Ah, there we go. Okay, good. Sorry about that. My apologies. Okay. And extending the screen. Oh, there we go. I just didn't need to wiggle a bit. Okay, good. Swoop. Swoop. Thanks. Sorry about that. All right. I'm choosing to believe that it's not that you're hungry that you haven't been asking as many questions, but you were really excited about hearing this talk. So I'm looking forward to giving it to you. So thank you. First of all, this is joint work with a lot of people from the Datum team and Eric Breck at Google and Stephen, who's since moved on to KAIST. All right. The motivation for this work is from the rules of machine learning. So specifically, oh goodness, hold on, I'm just realizing that that's in your way. The rules of machine learning, and specifically one of them, which was watch for silent failures. So imagine you're in a very different world and you're building an email system, right? And so one of your users sends an email to another user, but it vanishes into the ether. So what happens? Well, Alice asks, hey, did you get my email? And then Bob replies, what email? And then they actually figure out that your system is broken, they complain to you, and it gets fixed. This is a very different situation than what we face in machine learning. Our machine learning algorithms tend not to be smart enough to realize that the data that they're getting is garbage. They can't identify that the training data is not the same as the data that you're getting at inference time. These are all very difficult to do. So in particular, we should be watching for silent data failures. But how do we do that? And that's what this talk is all about. So as a motivating example, I want to talk about Google Play. So Google Play does some awesome machine learning, and they're launching multiple models every year. But then one time with one model, they did some statistical analysis, and they just realized that they had this very simple mistake where they were missing features at inference time, right? When they were trying to make classifications. And so then they fixed it, and then they got a 2% lift, which was way better than any of the fancy models that they've been launching that had improved the system. So just simple fixes can do amazing things for your system, okay? Now, here's a hypothetical nightmare. Imagine that you have a bug where your label is broken. Now, model validation, if you're actually doing any type of offline analysis, all that stuff that you was just described in that last talk, well, if the label is actually incorrect, it's all meaningless. All the statistics doesn't matter, right? So that's absolutely critical that label be correct. And without it, we have no safeguards whatsoever. So let's just do it. What's the problem? Well, we're balancing the safety and security of the system with basically the intention of our users who would much rather be building models. So one common case is that users, after building the system, after initial check through the data to look at what they're going to do with it, they don't look at it anymore ever again, and the data could keep coming in. Or you can imagine another extreme case where it's extremely secure, where they're checking it every day. Now, of course, we can't be as secure as if the users are checking the data every day, and we can't be as easy to use as not doing anything at all. So, but we want to do almost as well as both in each dimension. Does that make sense? Great. So, data expectations and a prescriptive schema are core to the system. What I mean by a prescriptive schema is it's something that describes the data. It does not describe the data. It describes what the data should be like. It tells it gives hopes for what the data should be. And that's in comparison to, say, the data statistics, which actually describe the data, and the trainer needs, which represent what actually needs to be true for the data to actually work for the trainer. And one thing that we have to recognize if we're building this is we can't just write a schema at the beginning and hope to extend it, it'll last forever. There's new features being added, there's features that break and we have to remove from the system, or we just don't find as valuable as they used to be. So we imagine that these are going to co-evolve all three of these aspects, okay? So how do we design a system that treats users' time and attention as a valuable resource? This is the key issue here. We want to automate what can be automated. We want to ask the right questions at the right time. For example, during development, when we have that machine learning expert in the room, and not late at night when we have the person, whoever's on call and is watching over 15 models, and has to deal with a problem. We want to unify the system. We want all these different components to work together, and we want to understand how users are using our system. So this is part of a larger ecosystem, TFX, which is a production ML platform for everyone. We've recently been open sourcing parts of this, and hundreds of teams use it throughout Alphabet. And today I will describe some of the safety measures in that system. So as Scully pointed out before, the machine learning requires much more than training. That ML code is a teeny bit in this larger view. And today I'm going to be talking about data verification, analysis tools, and monitoring. And specifically, I'm talking about model unit testing. And if you don't know what model unit testing is, I'll talk to you about that right now. So next I'm going to talk about the life of a schema, model unit testing, inter-batch agreement, how to deal with changes over time and differences between inference and training data. I'm going to talk about the telemetry that we've gathered over those hundreds of teams who are using the system, and then I'm going to conclude. So beginning with the life of a schema. Before I talk to you about what our schema is, I want to talk to you a little bit about what TensorFlow data looks like. So specifically, we have the number of visits. For instance, we have this protocol buffer, which looks a lot like a JSON object. And for each feature, there's a key, which says which feature it is, and then there's a value, for example, which is either an integer array, or it's a bytes array, or a string array, basically, or a float array, okay? And notice that if we have a single value, we don't know that it's a single value, but it's just an array of length 1. So, what kind of schema do we use to describe that data? Well, first of all, we say what kind of object it is. We say the value count, and then we give some presence constraints. Like for instance, is it always present? Then we say the min fraction is 1.0. And how do we make sure that everyone has a schema for their data? Well, it's a very simple answer to that. If you don't have a schema, we'll generate one for you. Now, we have to keep in mind that if we generated a schema for somebody, it was somebody who didn't want to provide us with a schema of their own, and so therefore we should be a little bit more conservative in the kinds of anomalies that we are going to throw. So, but this actually does start to connect the data. So when you have the data, we can automatically generate a schema, and once we have that schema, we can validate the data. So here's the first kind of schema that we can, or type of feature we can generate. Here we automatically infer the data type. That's unlikely to change. If there's only one value per example, that's incredibly useful for a modeler, so we throw that in there. And it's also very unlikely to change. And finally, if it's always present, then we throw in a min fraction of 1.0. Right? So these are the kinds of simple checks. But as I pointed out, a lot of times the feature is just completely missing. That's the kind of anomaly you're facing. So these kinds of simple checks are very useful and powerful. Another kind of thing that we do that's helpful for people building models is we identify that it says it's a bytes value, but in fact, if you look at all the values, it looks like it's probably representing a Boolean because it's set and clear, or true and false, or a string of 1 and then 0. You get the idea. And then finally, if there's a small number of string values, then we represent it as a string domain. So this is very useful information, not just for data validation, but also for the system as a whole, when you're thinking about how to transform these features, how you're going to use them in your model, and so forth. So now, auto-generated schemas can be edited. So if you have some user who's just really excited about putting everything, checking everything, and having lots of anomalies fire, then you can handle that. So for example, they might add the int domain to have a min of 0. And then making sure that there's known visits is always positive or always non-negative. Now, suppose that there's a problem with the schema or a problem with the data. And specifically what I mean by that is the schema says that the min fraction present must be 1.0. But the stats say that the fraction present is actually 0.9. So what's wrong? So we're not sure if the data is bad or if we need to fix the schema. Now, if the data is bad, there's a long, drawn-out process that we'll have to go through. But if the user just looks at this and says, you know what, I don't really care that the min fraction is 1.0, I'm just going to fix the schema. That's something that we can do very easily. So when we're fixing the, whenever there's an anomaly, one thing we provide the user immediately is a modification to the schema that just makes the anomaly go away. And this is incredibly important because if you don't make it really easy to deal with your mistakes, then users won't use your system. And so we have to make the system very usable. Negative values, if the domain is violated, we just provide a new, we fix the schema so that it includes that data. And multivalency, similarly. And if it's completely missing in the data, or for instance, if it used to be an int type and now it's a string type, we just mark it as deprecated. And then we're forcing the user to say, all right, either you don't care about this feature, or you're going to go back and fix it. All right? And so this completes the story of the connection between the data statistics and the data expectations in our schema. And by anomalies that are when they occur, are represented as schema updates that can then be directly applied to the schema. So everything is we're unifying the entire system. So the next aspect is model unit testing. So in particular, when you have, we're doing this co-evolution, we're focusing on the data statistics and we're making sure that we're not firing too many anomalies. But then how do we know that we're firing enough, right? How do we know that, like for instance, maybe the data won't actually work with the trainer. Maybe there's a num visits of 0 and the trainer has a log num visits, and that's going to cause us serious problems. Well, if that happens during development, it's not a big deal. We'll just fix it, right? We'll add 1 or whatever to the num visits. However, if it happens during development, then doesn't happen during development, but it happens in production when there's somebody else late at night and they have to deal with it, that's a problem. And moreover, it's a very serious problem because they don't know whether or not your trainer is broken or the new data is broken, which makes it an incredibly difficult problem to solve. So our solution here is that when you're developing the model, we do model unit testing where we take the schema that you've generated and then we generate data that satisfies that schema and then we feed it into the trainer. And so in an ideal scenario, the current data is a subset of like all the data that you're going to see in the future. And it's a subset, and that is of course a subset of all the valid data based upon the schema. And that is a subset of all the data the trainer can handle. Now, if we do fuzz testing, we're going to generate a whole bunch of examples that are valid data based upon the schema. And they should all be data the trainer can handle. And if they're not, we get some examples where the trainer can't work. So in particular here, we have, if the num visits is 0, well that looks like a perfectly valid example. We need to fix our trainer. But if we said num visits is -2, oh, okay, well now we actually have to fix the schema and add a constraint. So we can basically go through with this, and now we have a better schema. So if we do, in development, have an error, if it violates the schema, then we know that we have a problem with the data. Or if it passes the schema, then we know we have a problem with the trainer. At least that's where we want to start looking, and we have a lot more confidence in how we start our debugging process. So this is basically our co-evolution of data statistics and the schema and the trainer. And basically there's all these connections and the system is unified and things are automated when they need to be automated. It's a very easy system to use. And in particular, they fit into the larger TFX ecosystem where And so now I'm going to talk a little bit about inter-batch agreement. So suppose that you have, you get training data and it's arriving over time. And you have the training data from yesterday and the training data from today. And you don't want it to change too much. Moreover, you have your inference data as well, the data that you might be drawing directly from as you're doing inference. So you want to make sure that inference and training are the same, right? Just like practice like you play. However, it's not always possible. So for instance, there's an inherent skew in ranking problems where you just can't get the label of all the examples that you need to perform inference on. So we have to allow for some difference. Moreover, yesterday and today, if you think about yesterday and today, one natural thing to do would be to say, today was generated from the same distribution as yesterday. And if you have like maybe 100 examples coming a day, you might be able to make that assumption and not be able to invalidate the null hypothesis. However, let's suppose you have 100 million examples coming every day. And there's a very small change between yesterday and today, which is completely reasonable. Maybe there's 10,000 examples that change their norm from 2 or from 1 to 2. Well, then you're going to invalidate the null hypothesis. You're going to say, oh, there's something wrong here. And when we tried this with real data sets too, using chi-squared test, we got the same results, that you would invalidate the null hypothesis all the time. So you can't use this as an assumption. So here's a solution. We bound the L infinity distance from yesterday to today. So specifically, we look at the distributions and we just use the L infinity distance as a metric. This has a variety of practical advantages. So for instance, keep in mind that the scientist who designs the anomaly detection system is not necessarily the same person who has to deal with the anomaly as it arrives. So the L infinity distance doesn't just give you a distance, it also gives you a witness. So here you're seeing the country that all the examples are coming from, and you see a 3% increase in India, and so you're asking yourself, well, here's the witness. The India changed by 3%. That's why I'm getting this anomaly. Is that okay? And so somebody who's a little familiar with the data might be able to handle that. They don't have to necessarily be a machine learning expert to be able to understand that kind of anomaly. So now for the fun stuff that you're all waiting to hear before you go over to lunch. So changes to the schema. So are people actually using this thing? Well, almost a little less than half of our users take the original schema that's either automatically created or they've manually inserted, and they just leave it with that, and they don't ever change it, right? But then many of our users do make edits and changes to the schema. Moreover, the anomalies that occur, they do fire. Like in a month, in a period of a month, like maybe 10% of the new feature column anomalies fired, and then when they did fire, like about 2/3 of the time they were getting fixed. So if you'll notice, most of these anomalies that are firing are feature churn, because that's a very common thing. It's a part of a natural, healthy environment that features are going to be added and removed. But that doesn't mean that you don't want to check when a feature suddenly disappears that it was supposed to disappear. Out of domain values is another common one. So if you're listing all the values for a particular feature, you're going to have an anomaly anytime a new feature, a new value occurs. All right. So so I think a big picture here is people are dealing with the system, they're handling the anomalies, but they're not handling all the anomalies. So we could improve the system and make it easier to use and have people handle more of these anomalies. So in conclusion, there's a bunch of open questions, like for instance, but I think the most important one here is this. If we want people to deal with anomalies, we have to justify why they're dealing with anomalies. So how do we estimate the return on investment of fixing a problem before it's fixed, before we've actually asked the user to fix it? I think this is fairly straightforward for things like missing features, but if you think of more general or of more specific types of anomalies, it's a lot harder. And some other future work, time series anomalies, like taking the more important parameters of the system and tracking them using a time series and making sure that they're what we expect. Extending fuzz testing to inference. We've done some work on that internally and hope to make it available. Automatically tune the schema during fuzz testing. Automatically infer semantic types. Deeper understanding of feature usage in training and inference, not just black box texting. So in general, remember, watching for silent data failures is something that you don't have to think about a lot if you're building an email system, but if you're building a machine learning system, it can give you huge wins. And we have to design a system that treats users' time and attention as a valuable resource. So we have open source software. Feel free to take a photo of this page if you like, or just search TensorFlow data validation. It'll get you to where you need to be on your favorite search engine, of course. If there are any questions, I also have more case studies if you'd like to hear about them.
Okay, we have time for a few questions.
Hi, I'm Hua Zhang from Netflix. I actually have two questions. The first question is, actually after we obtain the data, there are a lot of transformations, data transformation, feature transformation. All those transformers can be faulty too. So where do you think we should put the probe on? You know, right before the trainer or right after data acquisition or somewhere in between?
Yes. So you should put it before the trainer. I think that's an important part. I think you also want to, so for instance, keep in mind, one of the things that really messes with you is when the trainer, when the data itself is wrong. If you won't necessarily have the right idea, there's no way for a new model to compensate for that. But on the other hand, yeah, you want to make sure that your model itself is doing as well as it could. So you can put anomaly detection there as well. Another nice thing about having the post-transform anomaly detection is that it's much easier to sort of, like I was talking about the ROI, it's much easier to estimate the ROI if I know the statistics right before the data goes into the model. So specifically, if you're doing something like flattening the data, right, and then you know that this feature is in 10% of or it's in 90% of the data, and then it suddenly goes to 2% of the data, that's a very important information to have. And internally we do have both of those types of anomaly detection available. Did you have a second question, or was that, have I not heard that?
The second question would be, in your paper you say you got this schema from some heuristics. Why don't you train a simple model for that? Say a very simple LR model for better ROI. I don't know.
So I think this allows me to say one of my favorite things about machine learning. It's like, well, what is the actual objective of that model, right? So how do you weigh off false positives? There's all sorts of questions. I mean, I think that telemetry is a beginning to get there, but I think I would love to hear from you or other people. What is the right objective there? It's hard to quantify, but we have an idea of simple things that are easy to. And how do you quantify easy to understand objectives, right?
All right. Thank you very much.
Thank you.
Hi there, Nikos from Quantum Black. Thanks for the talk. Two questions. A quick one is this protobuf specific? Does it work with Pandas, PySpark data frames?
So one thing no, it is not protobuf specific. It is, so there's I mentioned this in the coevolution, there's data statistics. So we take our original data and calculate statistics. So we have ability to calculate statistics for CSV and the TensorFlow example. If you can calculate the statistics for whatever data you have, then you can run this system on that. So I mean, it's just there'd be more work obviously, but yeah, there's nothing protobuf specific. If I remember correctly, the kind of thrift data formats look similar to the TensorFlow example formats that we have.
Cool. And the second one, you touched briefly upon generating mock data for unit testing models. It's easy to generate this kind of data if you have simple predicates like min, max, nulls, distinct values, etc. Are you aware of any tools, or do you have anything in here for more advanced mock data generation, like specific distributions, correlations, time series, things like that?
I'll have to get back to you on that one. I'm not sure, but I mean, I think primarily we're focusing on the thresholds and stuff like that. Because it's keep in mind also that we're not necessarily trying to calculate the performance of the model. We're trying to see whether or not that model will the data will go through the trainer and will go through the model. If you were trying to do, I think that kind of analysis and that kind of those kinds of distributions would be more important if we were trying to actually do. Trying to actually see how the model would perform.
Musa from Quantum Black. Are you also trying to easily quantify the performance difference based on distributional changes in features?
Sorry, can you say the question?
Changes in distribution of features, easily quantifying performance difference because of those distributional changes in features?
I mean, so I think that you're getting to that open question there, which is we have a schema that we've generated and we see if the data satisfies it. We can check and see if the model can work on the data that is specified in the schema. We do not necessarily, we're not checking the performance of the model. You can look at, so there's another team in the TFX umbrella that works on they have a product called TFMA, and you can look at that. I don't know whether or not they handle that, what you just described. But the TensorFlow model analysis would be where I would look.
Okay, let's thank our speaker again, and now we have a lunch break.
Let me just type in the password. Okay, has network connection problem. Yeah, I guess this.
So which one you have?
Oh, yeah. I don't need this I just want HDMI.
Uh-oh. Hi.
Speaking after lunch.
Yeah, see Gregory? No. Just checking. I'm Adam. Yeah.
So I have a preview back there that I can see the same thing. So as soon as you plug in and go full screen, then I'll switch it up to here.
Okay. Do you know if what's on this monitor will end up showing on that monitor? Or-
What you see there is going to be what's up here.
Okay.
Yep.
That's fine.
Cool. Do you have any videos or anything with sound from the computer?
Nope.
Okay. Cool. So I don't know. I haven't seen two of these people before you, so I don't know what they're going to be using. But if this isn't connected already, then you can just plug in HDMI as well.
Cool. Looks great.
Great. And the timer will go down.
Mhm.
You got 18 minutes for the talk.
Wow, this is the best speaker setup I've seen.
Cool.
Thank you.
Where do you turn it on? Oh, this one. Okay.
Hi, everyone. So we are having an informal discussion on artifact evaluation in the Fisher Conference Center right there. So if you're interested to discuss, reproducibility of their systems and ML artifacts, please join us. So it's starting right now. It's right there across the corridor.
USB-C.
Okay. Do you have the HDMI output?
I have this kind of output, USB-C. Oh, sorry,
Okay.
no, it's a Mac. Yeah, sorry, it's the new
Okay,
Mac.
USB-C.
Yeah. So it's this guy?
Yep.
Okay. And I brought a power cord. Do you guys have one? Should I just plug my own power cord in?
There is power here if you want to plug it in.
Let's do that. So it's good. Sorry about it. Okay. Do I need to do anything?
Is it PDF or PowerPoint?
PDF?
Okay. We'll probably want to mirror that because this is shown next to the display right now.
Okay. So let's do full screen mode and see if where that gets us.
I think we need to set up mirroring so it shows the same thing here.
Oh, okay. Yeah, I'm a bit new to the whole Mac thing, as you can tell by the fact that I forgot I had a Mac.
Yeah, no problem.
System preferences, Finder. Do you remember where we go? We go to settings, right?
If you go to the Apple.
Apple, okay. Oh, there we go, okay.
Display.
Okay.
Click on arrangement. Compare displays. Now it'll just show the same thing.
Okay. And full screen mode. That's going to work. Okay, great.
Good. So I have this preview here. I can see back there as well.
Yeah,
So, as
so
soon
if
as
that
you
works,
plug in
everything
and go
works?
full screen, then I'll make sure it goes up here too. Or actually,
Okay.
since there's nobody before you.
Yeah, I'm just gonna leave this alone. Yeah, hope no one runs off with their laptop.
Yeah, if you need to take it out before then.
There's one for you, there's one for me. I don't know where yours is. I hid mine.
What do you mean there's one for you? I thought there was like a, I don't know, like a hand.
I have this one. Yeah, there's one for you.
Hello? All right, hey everybody. So it's a pleasure to introduce our keynote speaker for this afternoon, Maya Gupta. She's a principal scientist at Google AI, and she leads the Glassbox machine learning R&D team. In a previous life, she was a professor at UW, but has been at Google for the past several years, doing some really cool things that she'll tell us about today. She also, in her ample spare time, has founded a jigsaw puzzle company, which is pretty cool. But with that, let's thank Maya. Thanks.
Okay, great. And thanks to the organizers for having me out. I come to the title of this talk very humbly. This is a question, not that it's for you and I'm going to answer, but this is a question for all of us to be figuring out. How do we make AI fair? And as we know, so many people will talk about like AI is coming. No, AI is here, and it's affecting all of our lives. And as we think about, for example, my little nephew here, it's going to affect a lot of things in his life. It's going to affect which books he gets recommended to read. It's going to affect what music he listens to in his culture. It's going to affect what news he reads. It may also affect the drivers on the road. It may affect what job interviews, what college admissions, all sorts of things about our lives. And what's making people a little uncomfortable about how awesome that is that it's pretty confusing as to who's making all those decisions. So in the old days, like with newspapers, you'd send in a letter to the editor, and there'd be an editor of that newspaper who would decide if that got published, who'd decide what went on the front page, and if you didn't like it, you knew who you could complain to, and you knew who was running things. And there were many different newspapers in the country who were making separate independent decisions, right? But now that sort of has changed. If AI is making the decisions about what news you're seeing, and if more of us are going to the same news sites, all of that scale is happening, and all of that sort of decision-making is being hidden a little bit. And when I first started working at Google, I sort of saw myself as developing tools, ML tools and algorithms that other people would use, and that they would sort of make the decisions about how to use. And I didn't really see myself as being responsible for worrying about things like fairness per se. But what I've realized as a technologist and building ML systems is that we are all responsible. This is a joint problem, because so many of the aspects are things that we control. And there's so many aspects that go into this, and I'm going to get into some of these. Clearly, of course, the training data and how you're selecting and specifying the training data, how you're logging, what you're logging, all this stuff is being controlled by technologists, by engineers, as well as by higher level people. And of course, the inputs that you're using, how you're testing these systems, our loss functions. I'm going to make a case that even the function class you use turns out to be very important to issues of fairness. We'll talk a bit about constraints and how we can use constraints to make models more fair. And of course, just what metrics are we using? What tests are we running before we launch these systems? Okay, so is everyone pro-fairness? I'm pro-fair, everybody pro-fairness? Okay, hopefully, right? So good, we all agree, this is easy. Oh, but wait, you know, it's not really easy. What the heck do we even mean, right? It's really easy to rally behind that big word, but then as we get into the details of what does fairness mean, we end up with a really complicated mess. And a mess that humans have been arguing about and thinking about for thousands of years, dating back to our Greek philosophers who had a lot to say about this. But also, there's societal issues that change what we think is fair. And then this is really an issue of psychology as well. So one of the things that philosophy gives us on this issue is principles and ways of thinking about what might be fair. And a lot of those, as I said, go back to the Greeks. But I'm going to actually talk about a recent principle from John Rawls, his veil of ignorance idea. You know, surprisingly recent as philosophy goes, right? This is recent work here in 1971. And it's sort of a middle principle that says a good moral principle is one where if you're not born yet and you have to like pick your society and you're like picking your rules, which rules do you want to see that society have before you get to choose who you get to be in that society? Okay, so this is great and that sounds good to me. Okay, but then how do we use this? So there might still be a lot of disagreement about what's fair. Maybe we would all agree using this principle that, well, okay, maybe we want equal pay for equal work and that it shouldn't depend on the color of your skin or what gender you are. But now, how do we actually do that algorithmically? How do we actually impose that principle on our systems? So one aspect is maybe we say, okay, let's just make sure that there's no inputs about these features. Sort of this called fairness through unawareness. And as you might expect, this sort of just isn't strong enough, right? There's going to be a lot of correlated features in the housing market that we talk about redlining by zip codes and stuff that just make this hard. You know, I may not know how old you are, but if I know what music you like, I bet I can guess a lot about your age. And the training data labels that we work with may be explicitly biased. So if we're like worrying about how much to pay people, if we just reflect the training data, maybe it's already sort of too late. And even when they're not explicitly biased, there may be implicit biases. In some groundmark work by Cote and Laurie back in 1993, they point out that if you pay people less for a job, they may do a less good job. So if you've got two groups, one a group who you're systematically underpaying, they may be systematically underperforming as well, because they're like, oh, I'm not getting the big bucks, why should I put in the effort? So all of this confuses our notion of training data. Okay, so that's some of the stuff that philosophy's bringing to the table, but I also want to emphasize how complicated fairness is from a psychological perspective. And starting back again with philosopher David Hume, he pointed out that different people have different moral sensitivities. Some of us literally feel injustice more strongly than others. And not only is injustice something that we feel, we may have different notions of what we mean by fairness. And Jonathan Haidt, in his 2012 book, sort of sketches out sort of 5 to 7 distinct moral dimensions that you might feel injustice about. Some of them are simple things like, hey, it's not okay to harm other people. But a couple of them have to do sort of more directly with fairness. And at least 2 distinct ones are sort of, do we care about equal outcomes? Should everybody have an equal likelihood of getting a free lunch? Or do we care about equal opportunity? Everybody should have a fair chance to fish for their lunch. Now, from a statistical point of view, we'll sort of think of that as, okay, if we have some different groups, are we worried about, say, in a classification setting, making sure that the probability that people get a positive class is equivalent across the different groups? Or do we want to condition that on whether or not they deserved to have a positive label? So equally deserving people from different groups are getting positive labels. And one of the things I'll keep coming back to is you'll notice that the second criteria here, equal opportunity, is conditioned on the training label. So now how good our training labels are becomes a really important part of this question. So if we're starting with already biased or incorrect or poorly sampled training labels and training data, we may already be too late to apply that principle. Okay, and we can think about sort of those 2 fairness issues in a different way as well, if we think about how they relate to reality. So one principle is, hey, when we build AI systems, they shouldn't distort reality. So for example, if you search for coffee near Stanford, one of the things that we try to do on maps is not just serve you the big chains which is really easy for us to do, but try to find the local coffee shops that are high quality coffee shops as well, because local businesses also should be having a shot at being shown, and that's reality, right? There's local businesses, and that's only fair. So this sounds pretty good, and for a long time I was like, yeah, we shouldn't distort reality, that's just how it goes. But the counter argument is that, reality isn't fair. AI is very powerful, it's changing our world, and we have a chance to change the world for the better. We have a chance to think through all of these issues and try to make sure that our AI systems are making the world a better place, whether that's making it more consistent with law or policy or justice. But again, these words, justice, equality, the law, they're very easy to say. They're much harder to execute the details of in technical systems and to agree on the details. Okay, so we've talked a bit about what does fairness mean, finding the right policy. I don't have any good answers for you other than, hey, it's really complicated and you need to think really hard and you want to get information and opinions from a lot of stakeholders about what might be considered fair or what might be issues in your system. And of course, the most important thing you can do is get great training data and worry about the quality of your training data and whether it reflects what you're looking for. And then what's perhaps a little surprising to people is that there's a lot more we can do on the machine learning side apart from the data to help make things fair in general. Okay, so at this point you might be thinking, okay, this is all really interesting and I'm glad that someone else is worrying about these things, but it's not going to be a problem for me. I'm just going to get fairly sample data, I'm going to do this problem, everything's going to be fine. So let's just highlight a few of the ways in which just even really simple systems can go badly. And I'm being a little too vague here by saying bad classifiers, but how good people can train classifiers that don't really work as well as they might expect in some simple ways. And this is just going to be an incomplete sort of version of 3 or 4 of the things to watch out for. So our first one here is just data disparity. So if I want to predict if you like an artist, it's much easier to predict if you like Van Gogh than it is to predict if you like the Japanese artist Bokuyo. I just don't have as much data about whether people like Bokuyo as I do about Van Gogh. So it's just much easier to be accurate and to do higher quality job with majority classes. Okay, so that sort of suggests that all we need to do is make sure that we sample minority classes more. But even if we do equal sampling, and even if we put equal effort into building good classification systems, we may not get equal outcomes, in part because different problems are just harder or easier than each other. And we have to be real about that and investigate that. As one example of that from Google, we'd like our Google mapping systems to work equally well around the world. But we have to put a lot of effort into getting them to work well in India because India doesn't have a formal address system. So when you want to go to this temple, the address on the books is its opposite Red Fort. That's a very, very vague notion. So it's just a harder problem, and that means more work has to go in order to make it as accurate as the rest of the system. Okay, for this next one, we need some audience participation. Can anybody tell what animal this is? Okay, I'm hearing a lot of dolphins. This poor creature washed up in Moss Beach in the Fitzgerald Marine Reserve. This is us helping a ranger drag it off. And it is not a dolphin. It is a porpoise, which is my point. Labelers are often less good at labeling minority classes or minority labels that they don't have much experience with. Now, to really hit this point home, do you know how this dolphin died, or how this porpoise died? Exactly. So this porpoise was killed by a dolphin. So, here we're just dealing with sea creatures, but if we'd been dealing with like labeling people and we mistaken someone for their murder, we'd be very unhappy. Okay, but so this is a problem that the quality of your labels may really differ and may really vary across your different classes, even if you've worked hard to get good labels. Okay, then transitioning from thinking about the data to thinking more about the modeling, of course we need the right features, and different subgroups or different classes may need different kinds of features to do a good job, and they might need different expressibility, they might need different feature interactions, or different flexibility to the model. Okay, so what else can we do here? So we have the training data, and that's usually how we control machine learning algorithms. But our team has done a lot of work in sort of saying, well, what else can we do to take policy goals, translate them into math, and take them into the training algorithm? And one set of these kind of goals is to constrain the output statistics. And we foreshadowed that a little earlier in this talk. We'll call these rate constraints. One example of that is we might say, for example, I'm going to train a classifier. It's got to work everywhere in the world, and I'd like it to be roughly as accurate in India as it is in the US. So how might we do that? Well, we can set that up as a constrained training problem. So we might minimize our classification errors, and we might just add a constraint on the accuracy on the one subgroup compared to the accuracy in the other subgroup. Okay, so that sounds great, but what if what my classifier is doing is giving out free lunches? Then the people in India and the US might not feel this is strong enough. They might really want equal benefits, and they might feel that that's a better notion of fairness, is that they're more likely to get positive classification labels at the same rates. They may not really care if my classifier is accurate. They want the free lunches. And we might feel, well, that's not really fair. Really, we should only worry about, are we giving equal lunches or free lunches equally to people who deserve them, to the ones labeled positive in each of the countries. But there again, we have this challenge of, did we get good training data? Can we trust that those labels are right in the first place? And then lastly, one of the things that we see a lot in practice is that these types of constraints may be a bit too difficult to do, but we may at least be able to make sure that people are not losing out. Because usually decisions are already being made, whether it's by an AI system or in the real world, and we can say, let's launch a new decision-making system. Let's make sure that people are not losing benefits or that the system is not less accurate for them. Right? We want things to help everyone. Maybe some people are going to get a bigger improvement than others, but let's not make things worse for some subgroup. Okay, so we now have 4 different statistical definitions. These are constraints on the output of our classifier. They contradict each other. They may not have they may not even be feasible. So this is all sort of just to emphasize the complexity of it's not always clear what you want to do or what is going to be the right thing. However, the good news is, algorithmically, these are all sort of the same beast, or they're at least similar beasts, which is we can write them all mathematically somewhat the same. So they're all constraints on the classifier's rates. We can write all of those issues as whether it's a positive rate on a data set D or the negative rate of the classifier on the data set D. So just for example, if I wanted to constrain the recall in India, I can just say that the positive rate on the class of India has to be greater than or equal to 70%. And in fact, any of those different fairness notions I was telling you about, we can write in this form here, which is a linear combination of positive and negative rates. So this is nice from the algorithmic and mathematical point of view, because we can now sort of just set up one general type of problem and figure out how to solve it, which is that we want to take our usual structural risk minimization problem and add in rate constraints to impose whatever these kind of fairness constraints are that you'd like to have. Okay, we could talk a lot about why that's hard and why it's interesting. I'm just going to point you to a couple papers. There's been a bunch of research groups working in this area. I'm selfishly going to point you to our most recent paper, which does survey a lot of that related work as well. This is a journal paper. It's on archive now. It'll appear in JMLR. And part of the trick here is that these are non-differentiable constraints. And there's a lot of theory to getting this to work right. This actually, the theory paper here won the best paper award at ALT. And there's a TensorFlow library, so you can play around with this yourself if you just want to give this stuff a try or use it as a base for your own research. Okay, so wow, that sounds great. We've totally solved this. All you have to do is pick your fairness policy, pick your groups, and we're done, right? Of course not. Okay, so a lot of challenges with this as a solution. So let me just go through some of them. The first challenge is if you have small groups. So maybe you have 1 million people in your training set, but now you want to make a constraint about Alaskans. Suddenly we don't have so many people. We're going to have statistical significance problems. We're going to have feasibility problems. And if you start doing intersectional groups and you worry about the Alaskan women over 80, this is also going to get pretty hard. You're now trying to make a constraint on 5 examples. And just because you satisfy these constraints in your training data, might not really pass, might not generalize to your test data. Just so we have generalization problems in machine learning, we're going to have generalization problems with these constraints. And then lastly, I haven't really handled how do you handle things that are continuous, things like age, et cetera. Okay, well those are just some of the statistical and algorithmic challenges. Bigger challenges, we may not have the data to do this at all, right? Maybe I want to make sure that my system works equally well for cat lovers and dog lovers, and I don't know who likes cats or dogs. Maybe my system doesn't store any information about race or gender, and I don't want to go near it. All sorts of problems can happen there. We've done a little bit of work trying to look at correlated groups and saying, well, we'd like to make sure the system is fair for age, so maybe we can make it fair for people who like different kinds of music and see if that transitions over. A lot of interesting questions there to see if that can really work well. But I think the biggest problem with this rate constraint approach is that it's about sort of categories and about groups and about distilling us down to one feature or a few number of features. And really we're individuals, and fairness is about sort of our individual experience. I mean, it's nice if my people, however you define that, are getting an average statistically good experience, but I personally want fairness for me, right? So what does that even mean, and how do we impose that? So we can look at that as well. So one of the first principles to get some traction in the machine learning literature was from Dwork, suggesting that we should make sure that similar individuals do get similar outcomes from our systems. And of course, if you have a binary classifier, you're like, well, there's going to be a decision boundary. But this kind of does imply that mathematically, one of the things we can do is prefer smoother function classes and prefer smoothness regularizers, that if we're not sacrificing too much accuracy, we can at least make sure that things are a little bit smoother out there for individual experiences. This next policy, I'm going to dig a little bit more deeply into, which is that sometimes there's inputs that we shouldn't be rewarding or penalizing. So let's look at an example of that. So yeah, do people feel like one of these classifiers is fair? Let's pretend we're trying to do college admissions. We'll leave out the input of how much money your parents give to. Okay, what do people think? How many people like the classifier of this one on the right, fair, or decision tree classifier? And I've got this classifier on the left, some nonlinear algorithm. This is a toy example, but pretend it could be a DNN. Okay. So what if I showed you two individuals, X1 here in green and X2 in red, who's not getting admitted to this college? Does this feel fair to them? No, X2 is getting penalized for having a higher SAT score, even though he's got the same GPA. So that's a pretty bad individual experience. And this is a very easy thing for algorithms and for our models to do, is overfit in this way that basically violates basic monotonicity constraints that we would think of as fair. So here's an example of the same thing, but with some data from a UCI data set. This is for credit scoring. Here we've got 24,000 examples in 2 dimensions. I'm just going to look at 2 features here. Are you single or married, and how long has it been since you paid your bills? So 24,000 examples, this is plenty of data. I shouldn't have any problems with overfitting, right? But what happens is, what we're seeing here, is the mean and the variance, or the confidence intervals of the data. Most people pay their bills pretty fast, so that data has pretty good confidence. But there's not many people out here who haven't paid their bills for a long time, so we're getting very noisy data in that part of the space. So even though we have lots of training data, this is a big data scenario, once you start looking at small parts of the space, it still ends up sparse. We have the same problems we've been having for 50 years, which is we don't have enough data, and we're going to get overfitting. In fact, if we fit a model to this, and we fit just a nonlinear model, it's very likely we'll get something like this. And what is this model doing? It's saying, hey, we were going to give you a pretty good, predict your default rate as pretty high if you didn't pay your bill for 3 months, but if you just wait longer to pay your bills, your default prediction rate will go down. Awesome, yeah. I don't want to live in this society, right? That doesn't feel very fair. So what can we do? Well, we can impose constraints on our models. And one thing we can do is impose monotonicity constraints. And this requires us to look at our features and think a little carefully about whether that makes sense or not. In this case, I think it would make sense. And if you do this, you don't really gain or lose any test accuracy in this case. You gain a little bit of test accuracy, but not much because there's not many examples out there. But it's about guaranteeing that your model is behaving fairly throughout the space. And more generally, we can use these sort of monotonicity constraints to make sure that we don't penalize or reward inputs in ways that don't make sense from a fairness perspective. And usually these constraints are done in a way where if you only hold all the other inputs fixed. And this might seem familiar to some people. This is an old idea in the statistics literature, just as a matter of regularization. People may be familiar with isotonic regression, which is an algorithm for doing this in 1D. There's also been a lot of work in monotonic neural networks. And our team has done a lot of work in monotonic lattice models. This work by Velikova in 2010 sort of points out that monotonic neural networks really lose a lot of expressibility and have some theoretical problems. And so we've been working on a different kind of modeling using lattice models. There's a series of papers on that, but I'll just point you to one of the more recent ones, deep lattice networks. And there's a TensorFlow package that lets you play with these models. And I'll talk about this for a couple minutes. In order to make this work and to be able to get those kind of shape constraints, like monotonicity, underneath the toolbox, the layers are using interpolated lookup tables rather than using, say, ReLU layers. So a 1D interpolated lookup table is just a piecewise linear function you see in the back of your math textbooks. A multidimensional lookup table just spans the space, and again, you can interpolate and get a function that looks like that. And the toolbox lets you sort of go the whole span of flexibility, from linear models to generalized additive models, all the way to these sort of deep lattice networks, and you can plug and play with other layers in TensorFlow. Okay, so apart from letting you have these monotonicity guarantees, which may in some cases be useful for fairness, these models also provide some smoothness. And this one's a little harder and a little more subtle. But if we now just look at these two algorithms, so I've got a decision tree in the one case and a linear model in the other, which society do you want to live in? Which society do you think is a fair or better society? So I think we could and maybe should disagree on this. Personally, I would rather live in this society over here because I feel like it continues to reward people for hard work. That if you get a higher GPA, you don't have to do quite as well as your SAT. Whereas this society kind of suggests that, well, just do the minimum and you'll be fine. And that doesn't seem fair to the hard workers and the people who put in the extra effort. But that's sort of a second order subtle effect compared to the, wow, one guy's getting penalized for having a higher SAT, where it's like an obvious, I think, a badness. Okay, so yeah, we've talked about just how complicated these policy goals are, but I think there is stuff we can do and there's stuff we can agree on and we can find ways to make society better. We do need to most and foremost worry about having the right data, but we can do a lot when we worry about our algorithms and our algorithm choices as well on top of that. And I've only touched on just a small set of aspects here. There's been a vibrant machine learning fairness community that's been working and raising awareness about these problems for a few years, and you can find a lot of literature. It's sort of like Mad Libs, you know, you pick your name and you pick fair and put it into scholar.google, and you'll probably find some papers of some people trying to think through these problems, and encourage you to think through them as well. One specific thing you can do if you want to get involved is check out this new Kaggle competition run by Google's Conversation AI team, where we're challenging people to help identify toxic comments. This contest just started. The deadline's in 3 months, so you still have plenty of time. You're not behind if you wanted to jump in and give this a try or just play with the data. And to conclude, we really do have a huge opportunity here. I think a lot of people are worried about AI. They're worried about the risks. But on the flip side, I'm excited about AI. I'm excited about the possibilities. We really can sort of bring fairness at scale. We can move society faster in good directions. But that said, it's really complicated, and we need different viewpoints because don't expect everyone to agree on some of these issues and about how to execute them. And lastly, it's really up to us. This isn't something that someone else is going to take care of. This isn't something that the business person or the VP or the program manager does. This is something that our decisions and our research and our minor choices does end up affecting. Okay, thank you.
Thanks. We have time for a few questions. If you want to ask any questions, just line up behind the microphone.
Hi, Marco Canini from KAUST. So this was a very sensational talk. Thank you very much. My question is regarding essentially what we intend by AI today, which seems to be fairly conflated with machine learning, given all the recent successes. Do you think that there is something beyond basically this notion of AI equal to machine learning when it comes down to fairness, in particular with regard to the more traditional AI techniques that made use of logic and rules and so on? And would that perhaps be also an approach that is worth pursuing, because at that point there is a more interpretable, more explainable way of understanding what the decisions are being taken by AI?
I think that's a great question, but a very hard one. And you're right, I have conflated AI with machine learning in many ways because it's what we know how to do. And the problems are already really difficult for machine learning. As we move to more complicated AI systems, I think they get even harder. One of the things I would say is that when you have more of an end-to-end system or a system with many repeated plays, then that does change the notion of what makes the system fair and how do we deal with that. There's been just the start of some research in that area that I can't remember quite the reference on, but people are just starting to look at what happens in these larger, more complicated end-to-end systems for fairness.
Thank you.
Hi, Michael from Amazon. Thank you for your talk today. I was curious what you would say as AI is becoming more popular, and I think even at this conference, there are people talking about ML as a service, being able to offer kind of AI in a boxed way or as a service. Just curious, how do you think about or the concerns for fairness in that model?
I think it's a real challenge. So I do work for Google, and we try to build products for everyone. A lot of startups and smaller companies don't have that same responsibility or expectation, and they may be building products that are specifically only designed to work for a small set of people. So the assumptions there about how well does your product need to work and for what large a group may be different. But I think that, well, it's easy to worry that as we have everybody using AI, that not everyone will use it wisely because it's such a powerful tool. But I think we can attempt to just educate ourselves and demand from just socially from our peers that we're worrying about these issues and that we're at least thinking them through and being honest about them with ourselves.
Sure. Let me clarify the question now that you've answered that well. Do you think the responsibility, if you had to pick a side, do you think the responsibility falls more on the service provider or the user whose training models may be providing data but not aware of the internals?
Okay, so I think you're saying, well, if we're giving AI as a service and people are using it, what happens? I think with many questions about AI, it's not that different to things we already have. For example, if you're already providing cloud services and you're providing compute power, how responsible are you for how that's being used, right? If you're, and some of this comes down to, if you have a dog and the dog bites a man, how responsible for you use this? So I don't know all the details there, but I do think that making analogies to problems that we already have and legal solutions we already have is probably the best way forward for society because it'll be easiest for us all to agree if we can rely on precedent.
Thank you so much.
Okay, maybe, one last question.
You kind of started to touch on the fact that there's, I'm Roseman from Spotify. You started to touch on the fact that there's some literature around this idea, but how do you reason about this idea of monotonicity when you have like very complex features like embedding vectors and things like that?
Yeah, so definitely monotonicity is easiest if you have semantically meaningful inputs, like how long since they paid their bills, and then you can constrain the output to have that relationship. If instead you have very sparse inputs like zip codes and you throw it into an embedding, yeah, your life is hard. And I don't have great solutions for that. So as I said, this is a humble talk here in terms of how do we make AI fair. I think we have some partial solutions and some good ideas and some stuff that works sometimes, and we're just going to need more work.
All right, great. Let's thank our speaker one more time.
Hi, everyone. So 2 sessions to go. My name is Gregory Fursen. I will be chairing the next session on efficient training and inference. Just before starting, if the authors of the 4th paper, can you come to me during the talks, please? And I would like to introduce the first speaker, Sijan Ma. He's a PhD candidate in the Computer Science and Engineering Department at Ohio State University, and his main research interest is to automate and accelerate large-scale model training. And today he will present kernel machines that adapt to GPUs for effective large batch training. Please.
All right, thanks for the introduction. So today I would like to provide you some new insights into large batch training and show how to apply these insights and to improve the training on modern hardware. So what's the modern hardware I'm talking about? It's typically something like accelerators, GPUs, TPUs, and like computing clouds, like computing clusters. So all this hardware, commonly have a huge or massive computing parallelism. So with the access to this strong, powerful computing resource, the central problem of modern machine learning practice is about how to effectively use the parallelism for modern training. Okay, here the training I'm talking about is basically stochastic gradient descent, right? So if you take a look here, there's one iteration of stochastic gradient descent. You just first subsample a mini batch of training data, let's say size of m, and then you calculate corresponding gradient. And then you rescale this component by the step size adder and apply this to update your parameters. Okay, the best practice to apply this SGD iteration on modern hardware to effectively utilize the parallelism is basically starts with choosing a very large batch size. So by doing so, normally you are able to fully utilize the underlying hardware, and it allows you to possibly minimize the training time. Well, in reality, this practice is not enough. It's not enough to just choose a large batch size. So what we normally do is we also need to apply the so-called linear scaling rule. So instead of just choosing large batch size, we also need to scale the learning rate accordingly. So this rule says, like, when we multiply or increase the batch size by a factor of k, we should also increase the step size or learning rate by a factor of k. Okay, so, but why do we want to apply this? So this rule allows you to really train the model with a much larger batch size, but still converge in nearly the same number of epochs or equivalent computation. However, many empirical evidence has shown like there is an upper limit for this rule. Like there's a limit of linear scaling, which we just call it M star. And in our recent paper, we show like analytically we can calculate this M star from a formula, and also the training time, the walk-off training time has this correlation with the batch size. So when you choose a batch size M that's smaller or equal to M star, your training time is going to be almost linear to 1 over M, which implies that when you double your batch size, you can almost half your training time. This is assuming you have enough computing resource. But when you choose any batch size that's larger than M star, the training time is almost a constant by a small factor. Okay. So in this talk, I would like to move one step forward. So not just to calculate or identify this limit of linear scaling. I would like to really extend the linear scaling to match the parallelism of the computing hardware. So it allows us to further minimize the training time. So I would like to present the first principle solution that extends the linear scaling to effectively utilize the parallelism. And this idea is really demonstrated on a class of kernel machines. And we easily achieve like a 10 to 100 times speed up on a single GPU over the state-of-the-art other kernel methods. And we also fully automate the parameter selection during the training. Okay, before I talk about like how we're extending the linear scaling, let's first take a look how can we minimize the training time for a standard SGD. But it's in fact turns out to be very simple. We just need to choose the optimal step size, learning rate, and the batch size. And in our recent work, we show like we can calculate the optimal step size for a given batch size explicitly. So now the problem becomes simpler, right? We just want to choose a batch size M to minimize the training time. And before we talk about how to do the minimization, let's break the training time into two parts. The first part is the number of epochs you need to converge to certain training loss. And second part is just the walk-up time to train one epoch. So the second part really depends on hardware and your model architecture. Okay, it turns out like this correlation is very simple. So this curve, the x-axis is batch size, and the y-axis is the number of epochs for convergence. So it basically captures the linear scaling rule, right? So here M star is the limit of linear scaling. We calculated it explicitly. And if you choose a batch size before M star, so the number of epochs you need is almost a constant by a small difference, like 10%. And when you go beyond M star, it turns out you need a much more number of epochs to converge to the same training loss. So the number of epochs after M star is almost linear to the batch size M. Okay. And we have a similar relationship between the batch size M and the time to train one epoch. So it's even easier. It's if you increase your batch size M, right? The computation for one iteration, there is more parallelism inside. So you are able to have a higher utilization of the computing resource. So which translates just like a smaller time, like a less time to train one epoch. And here we identify a special point. It's called mGPU. It's it's basically the smallest batch size that allows you to fully utilize your computing resource. Okay, now we are able to really show you how the training time, the walkout training time is changing with the change of the batch size. It's very simple, just do a multiplication. And here you can see like Normally, you want to choose a batch size. In order to minimize the training time, you want to choose a batch size between this M star and M GPU. Okay, so it's simple. But there's a fundamental problem with this kind of best practice. And let's first just identify two regions in the training time figure. So the red region of this figure is what we call effective computation region. So if you choose a batch size here, you're able to converge in the minimum number of epochs. And this blue region, we call this full utilization region. So if you choose a batch size here, you're able to fully utilize your computing resource. Well, I mean, in practice, we normally have M star that is smaller than M GPU. The reason is like you probably do not just have one single GPU, you can have 10 GPU, 100 GPU, or 1,000 GPUs. So your computing parallelism could be much higher. And that ends up like we have to choose a batch size in this white region to minimize the training time. Well, that directly leads to underutilized computing resource, right? So we are unable to fully utilize the resource. Well, ideally, what we really want is something like M star that is larger or equal to M GPU. So in this case, these two regions will overlap. Right? So if you choose a batch size in between this overlapped region, you're able to converge in the minimum number of epochs and still fully utilize your computing resource. Okay, so here comes our idea. So we want to always have this desired situation. And our solution is very straightforward. We just increase the M star to be as large as M GPU. So the limit of linear scaling could be always larger than the computing parallelism provided by the hardware. So we implemented this idea for a class of kernel machines. And the kernel machine we consider here, you can think it's like a linear model with some nonlinear activation function. So alpha is like the model parameter you're trying to learn. And to apply this idea, what we do is we simply learn an adaptive kernel by spectrum modifying the original kernel. So, but more specifically, what kind of kernel we're trying to learn? So we want to learn a kernel that allows us to have the exact same optimization, optimal solution as the original one, but extending the linear scaling to something much larger. So the approach, again, is a spectrum modification. And the limit of linear scaling for the original kernel here is simply 1 over lambda 1. So what is lambda 1? It's essentially the top eigenvalue of the original kernel matrix, which can be shown in this blue curve. So the blue curve is essentially the eigenspectrum of the original kernel matrix. And so what we want to do is we want to do a spectrum modification of that kernel function. So its spectrum becomes this orange curve. So it's like a flatten of the eigenspectrum. And by doing so, the new kernel will have a different corresponding limit of linear scaling, which is just 1 over lambda q plus 1. And it implies a directly increase of the M star by a factor of lambda 1 over lambda q plus 1. So in the older paper like by our group, we show like this lambda 1 over lambda q plus 1 can be super polynomial in regard to q. So it's a huge. With like a few tens q, like this eigenspectrum flattening, you can have a few thousand increase in largest mini batch size you can achieve. Okay, but so what does this affect? How does this affect the final training time? And ideally, it's basically showing this cartoon, and you can see this dotted line is about the original kernel. Again, this x-axis is the batch size, and the y-axis is the training time for convergence. So for the original kernel, you can decrease your training time by increase your batch size up to this M star, which is, we know is small. And the new kernel simply will just extend this linear scaling region. You can keep increase your batch size until like M GPU. So your new limit of linear scaling is as large as an M GPU. So you can further drive down the training time. But how does this work in practice? So here we just show you a simple example with for the speech recognition task. So this blue curve, again, is from the original kernel. And here, again, the x-axis is batch size, y-axis is the training time for convergence. And we can see, like, for the original kernel, the optimal batch size is around 16. Right? But for a new kernel here, we can drive down this optimal batch size to around 6,000. So this directly provides us on a single GPU like 30 times speed up. And let's take another look in this curve. So basically, we see like we reach the full utilization of the GPU at around the millibatch size of 256. But our MSTAR now is around 6,000. So which implies we can probably utilize 20 GPUs at the same time and achieve another 20 times speed up. Okay, we package the entire this algorithm and this implementation in this pipeline. The nice thing about this pipeline is it is fully automatic. So all you need is, as a user, is to input this training data. The kernel function you select, which is basically a model architecture, and some information about the hardware you're using, like a memory size or the computing cores you have. So this pipeline will just automatically construct a new kernel and apply it for training. So it allows you to automatically extend the linear scaling to MGPU. And what's even moreover, it has a negligible overhead. So in our experiments, the overhead is like 2 or 3%, which is totally negligible. Okay. So here we show you another set of experiments on some small data set. And we call this interactive training. Because on this data set around 100,000 samples, we are able to finish the training in just 10 seconds, around 15 seconds really. So in comparison, we compare our result to other libSVM and a GPU implementation of libSVM. We see like at least 10 to 20 times speed up. So these experiments on GPU are, so for Sunday SVM is an implementation of libSVM on GPU. So we do this experiment on the same GPU. So this interactive training allows us to try different kernel functions and different kernel parameters quickly, right? So it somehow achieves the same effect as the AutoML. Okay, I also compare our results like to other state-of-the-art kernel methods on some larger data sets. So overall, we are able to improve the training time from like hundreds of thousands of CPU computation hours to like minutes of GPU computation. So I want to highlight like the result with the ImageNet. So we train a full ImageNet on a single GPU in around 40 minutes. So we also compare like results with a block called in the descent, which is a kind of a strong result. So we see like we are able to finish training on a single GPU in 80 minutes. In comparison, their method will take a few thousand hours. So what's more interesting is we are able to achieve a slightly higher test accuracy. Okay, so here I would like to talk about the take-home message. So we have the first principle solution to extend linear scaling. I think that's the original people didn't realize this. Like we just want to identify the limit of linear scaling by experiments or by some heuristics. But in fact, now I show like we can really extend it to something like much larger. In this case, in our experiments, we extend the linear scaling around 1,000 times. So it will allow us to effectively utilize the massive parallelism in the computing resource. Of course, this will translate to like a significantly reduction in training time. So our method is only demonstrated on these kernel machines, but in fact, it's more general. But on these kernels, these classical kernel machines, we're able to scale the kernel models to very large resource. And this was not possible with kernel models when applying like a mini-batch STD. So it also allows us to rapidly do this parameter selection. So nowadays, like we basically choose all the kernel functions and parameters automatically in our experiments. I also would like to propose, like when we do the research in optimization, this kernel model should be like a sanity check, because it's the simplest modern model that has a very nice performance. And it's in fact very comparable to neural networks. So first of all, it's over-parameterized, And secondly, it has many theoretical connections to the generalization performance of different kinds of neural networks. Okay, that's the end of my talk. Okay.
Thank you. Questions, please? Don't forget to say your name and affiliation. Questions? Yeah, please.
Yeah. My name is Yokoyama from NEC Corporation. Hi. I'm wondering the accuracy comparison between your method and LibSMM or standard SVM, because LibSMM is implemented by the different optimization method called the SMO. So
yes. Yes, yeah, they were doing SML, so it's kind of, it's not for comparison, it's more like a reference.
Reference?
Yeah.
In your paper?
No, what I mean is like they implemented SMO, so for standard SVM, and we implement really SGD. So these are two different methods, that's true.
So get to the, compared to the different accuracy, right? Or same?
Oh yeah, that's a question, yeah. So it's the same accuracy on a training loss, and we in fact have a very comparable testing accuracy as well.
Okay, thank you.
Hi, this is Gauri Joshi from Carnegie Mellon. Really nice talk. My question is that you're using these methods to increase the optimal mini batch size where we can operate. So are you also then using a much higher learning rate, proportionally larger learning rate for the experiments that you showed?
Okay, so the question is like, do we change the learning rate when we change the batch size? So yes, so we essentially just, this is essentially like extending the linear scaling. So we apply the same linear scaling. So when we increase the batch size by a factor of, let's say 100 times, we also increase the learning rate by a factor of 100 times.
Okay. I think that makes it very clear. So that's why I think you're getting such big speed up. But the key thing is making the mini batch size bigger.
Yeah, exactly. But like before, if you don't apply our method, you cannot really increase your learning rate because it will diverge.
Yes, I understand. Thank you.
Yeah, thanks.
Great. So let's thank the speaker again. So the next talk will be by Dibakar Gop, and he's a senior research engineer at ARM, and he works for machine learning team in research. Before joining ARM, he received a PhD from University of Wisconsin-Madison in 2017. And his presentation will be on ternary hybrid neural tree networks for highly constrained IoT applications. Please.
Yeah, thanks for this introduction. I'm Dibakar. Good afternoon to all of you. Today I'll be presenting some of the work that I've been doing at ARM Research. And this is a joint work with a couple of my colleagues at ARM. So I'll start with an executive summary. So as we all know, machine learning based applications nowadays are increasingly deployed in IoT devices, such as those based on the BBC microbit or LPC 1125, having an ARM Cortex M0 microcontroller with either 16 kilobyte to 8 kilobyte of writable memory. The storage and power constraints of these devices make it particularly challenging to run model neural networks on them, limiting the number of new IoT applications that can be deployed on such a constrained IoT system. Because of these constraints, reducing the model complexity of the ML algorithms of such IoT applications is of paramount importance in order to target the severely constrained microcontrollers or to deploy a wide range of applications on such constrained IoT devices. In this work, we propose a hybrid neural tree network to improve the state-of-the-art neural-only network for popular IoT applications and achieve significant benefit pretty much in all the fronts, albeit with a small loss in model accuracy. So as I said, reducing the computational complexity and model size of IoT applications will not only enable us to target the severely constrained microcontrollers, but also will help us to make a wide range of new IoT applications available on such constrained IoT devices. In recent years, numerous research efforts have been devoted to compressing neural networks for deployment on such constrained IoT devices through the use of either different architectural optimization techniques or different model compression techniques such as pruning, quantization, lowering factorization of weights and activation matrices of neural networks. One particularly effective technique in the domain of architectural optimizations has been the use of depth-wise separable convolution layers. Depth-wise separable convolution layers are primarily dominated with 1x1 convolution kernel as opposed to 3x3 or 5x5 convolution kernel that you have heard of. And because of the presence of this 1x1 convolution kernels, depth-wise separable convolution layers are supremely compute efficient when compared to convolution layers with 3x3 or 5x5 convolution kernels. While such depth-wise separable convolution layers have been transformative, further compression of such layers is definitely valuable. Recent works indicate that further compression of such depth-wise separable convolution layers is possible through the use of other model compression techniques such as pruning or quantization on them. More specifically, binary or ternary quantization like technique reduce the high precision model parameters to low precision binary or ternary values, thus reducing the multiplications in a neural network with additions and reducing the model size considerably. However, often that comes at the cost of modest to significant drop in the prediction accuracy of quantized model when compared to their full precision counterparts. And the same trend holds true when you apply such quantization and pruning-like technique to a popular IoT application dominated with depth-wise separable convolution layers. Recent work on Strassen nets presents a mathematically promising way to approximate matrix multiplication using Strassen's algorithm. It essentially shows the potential to achieve over 99% reduction in multiplications for neural networks with 3x3 convolutions using mostly ternary weights and few full precision weights while preserving the accuracy of a full precision model. Inspired by the success of Strassen nets in achieving such a massive reduction in multiplication and the resultant model size, we decide to apply these Strassen nets to a popular IoT application already compressed with compute efficient depth-wise separable convolution layers to reduce its model complexity even further. So in the next couple of slides, I'll give a brief overview of Strassen nets, describe why does it look that promising, and show it limitations that we observe when we apply to a popular IoT application dominated with depth-wise separable convolution layers. So now let's see how does Strassen net achieve such a massive reduction in multiplication and the resultant model size. So as we all know, in order to perform a matrix multiplication with two 2x2 matrices, you require 8 multiplications and 8 additions. However, instead if you follow Strassen's matrix multiplication algorithm, you can perform the same job using 7 multiplications. Now the question arises, how can you perform that same matrix multiplication job using 7 multiplications? In order to do that, Strassen's matrix multiplication algorithm begins with computing 7 Strassen intermediate terms, which we name as P terms in this slide. Computation of each of those Strassen intermediate terms require 1 multiplication and combining the elements of these 2 matrices in few specific ways through additions. So for example, computation of the first Strassen intermediate term, that is P1 term, required the addition of A and D elements of matrix A, E and H element of matrix B in conjunction with an element-wise multiplication between the 2 added terms. Later, combining the Strassen intermediate terms in few other specific ways through additions or subtractions generate the first element of this product matrix C. And similarly, we can generate the other elements of this product matrix C by combining those Strassen intermediate terms in few other specific ways through addition or subtractions. And this is everything the Strassen's matrix multiplication algorithm is all about. However, if you want to perform that same matrix multiplication job using fewer than 7 multiplications, that is fewer than 7 Strassen intermediate terms, then you can still do that. However, you will end up with an approximate version of the matrix multiplication result. And the Strassen networks that came out in 2018 and exploits this Strassen's matrix multiplication algorithm is all about that. It essentially offers you flexibility to tune the number of multiplication in Strassen's algorithm and let you observe different accuracy versus model complexity trade-offs. As in the context, as CNN DNNs are primarily dominated with matrix multiplication, so in the context of CNN DNN, you can basically associate one of those matrices in Strassen's algorithm with weights or filters and other matrices with input feature maps or input activations. So now the question arises, how does Strassen nets behave when applied to a representative IoT application? So for representative IoT application, in this work we consider keyword spotting, as keyword spotting is an important component for enabling speech-based user interaction on smart IoT devices. Depth-wise separable convolution-based model DSCNN, consisting of 1 standard convolution layer and 4 depth-wise separable convolution layer, has obtained state-of-the-art accuracy for keyword spotting application. The success of Strassen nets in achieving such a massive reduction in multiplications for neural networks with 3x3 convolutions and increasing visibility of such depth-wise separable convolution layers in keyword spotting like popular IoT applications essentially inspired us to apply these Strassen nets over this compute efficient state-of-the-art DSCN network to reduce its model complexity even further. So here is the pictorial representation of this baseline DSCN network. Each of its convolution layer in this network is replaced using a Strassen convolution. So as I said before, computation of each of the Strassen intermediate term require a multiplication and combining the elements of the input activations and weights through addition or subtraction in few specific ways. And later combining the different Strassen intermediates term through addition or subtraction generate the different element of the output activations. In the context of Strassen's algorithm, the count of intermediate terms is also called the width of hidden layer. So as we apply this Strassen nets over this state-of-the-art DSCN network, we explore its potential using different width of the hidden layer in Strassen's algorithm. And as you can expect, different width of the hidden layer in Strassen's algorithm will offer you different accuracy versus computational complexity trade-off. So we observe that while Strassen net is effective in achieving a massive reduction in multiplication and modest saving in model size for this keyword spotting application, however, that comes at the cost of significant increase in the number of editions. So the two figures in this slide shows the impact on accuracy, model size, and number of operations as we experiment with increasing width of hidden layer in Strassen's algorithm. So the different green dots shows the performance with different width of hidden layer in the Strassen's algorithm. So as you can see in the left figure that Strassen nets achieve modest saving in model size, while in the right figure you can see that in order to achieve an accuracy comparable to the baseline DSCN network, the width of the hidden layer in the Strassen's network required to be significantly wider. Although such wide hidden layers offers a modest saving in model size, however, that comes at the cost of about 50% increase in the number of editions. So now the question arises, how can we exploit the compute efficiency of depth-wise separable convolution layers and model size reduction ability of Strassen nets while maintaining an acceptable or no increase in the number of editions? Since recent tree-based learning techniques, for example bonsai decision trees, exhibits accuracy on par with neural models while requiring significantly fewer compute operations for some IoT-like applications, this essentially shifted our focus towards looking into those promising tree-based learning technique in order to address this increase in editions using Strassen nets. So as a brief recap, so as you all know, the standard decision trees can only learn axis parallel decision boundaries as shown in the leftmost figure, and because of the presence of those axis parallel decision boundaries, standard decision trees often cannot achieve accuracy comparable to their neural counterparts. So this bonsai tree that came out last year, it essentially brought in two things. First of all, it ensured the decision boundaries learned by a decision tree is no longer axis parallel. On top of that, bonsai computes non-linear prediction score in each of its tree nodes, thus resulting in decision boundaries that are neither axis parallel nor linear as well, as shown in the rightmost figure. However, when applied to this keyword spotting application, we observe that this bonsai tree observes very poor accuracy for this application. So the two figures in this slide shows the impact on accuracy, model size, and number of operations as we experiment with the different configurations of the bonsai tree. So the different blue dots in these two figures shows the performance with different configurations of this bonsai decision tree. So as you can see in the left figure that the accuracy of the bonsai tree saturates at about 84 to 85%. Even when the tree architecture is significantly scaled up with many internal and leaf nodes, causing a huge increase in the model size. The poor accuracy of this bonsai tree is primarily attributed to its inability to extract rich meaningful features from the keyword spotting application. However, an important point to note here that although bonsai occupies a large model size, its computational cost is significantly lower when compared to this baseline DSCN network. So based on all these results that we have seen so far, we can conclude that while Strassen nets and bonsai trees are effective in reducing the model complexity for some models as described in their original work, however, they have limitations when applied to an popular IT application already compressed with compute-efficient depth-wise separable convolution layers. So in one hand, Strassen nets can reduce the model size modestly, however, it increases the computational cost significantly. On the other hand, bonsai tree can reduce the computational cost, however, it cannot achieve the intended accuracy even when the tree architecture is significantly scaled up, causing a significant increase in model size. So all these observations so far essentially motivate us for the development of a hybrid neural tree network model for this keyword spotting application that can extract minimal set of rich, meaningful features using a shallower convolution layer consisting of few depth-wise separable convolution layers, and then can feed those extracted local features to a compute-efficient bonsai tree to perform the required classification. Use of a shallower convolution network in conjunction with an compute-efficient bonsai tree should ensure low computational cost for the overall network. Later, Strassen nets is applied over the overall network to reduce its model size, thus generating a compact as well as a compute-efficient architecture at the same time for this keyword spotting application. To be precise, we develop a hybrid neural tree network model for this keyword spotting application that leverages 3 convolution layers instead of 5 layers in the baseline DSCN network to extract the minimal set of rich, meaningful features from the keyword spotting dataset, and then relies on a depth to bonsai tree to perform any global correlation between those extracted local features and to perform the required classification. Use of fewer convolution layer in conjunction with a depth to bonsai tree ensures lower computational cost for the overall network. Furthermore, since the overall hybrid network has 3 convolution layers, as a result, when the whole network is Strassenified in order to reduce the multiplication and the resultant model size, the computational cost around additions does go down significantly when compared to Strassenifying the baseline DSCN network with 5 convolution layers that we have seen before. So here are some of the results that we observe with this hybrid network. So the 2 figures in this slide shows the impact on accuracy, number of operations, model size using hybrid network, and compare that against the baseline DSCN network. X-axis shows the number of operations or the model size, Y-axis shows the accuracy. So as you can see that this hybrid network observes about 11% reduction in operations and 52% reduction in model size with no loss in accuracy. As in this work, since we consider MAC, addition and multiplication all as individual operations, as a result, this 11% reduction in operations primarily comes from 98% reduction in multiplications and 12% reduction in additions when compared to all the MAC operations in the baseline DSCN network. Furthermore, it is important to note here that the operations in the hybrid network now is primarily dominated with area and energy efficient additions when compared to the energy hungry MAC operations in the baseline DSCN network. Furthermore, as you all know that it is not only important to take care of the model size, but the size of the intermediate activations that a resultant network requires to deal with. So in order to better understand the impact of this hybrid network over the overall memory footprint, we quantize its activation to 8-bit fixed point format throughout all the layers. So this slide essentially captures some of those results. So as you can see, this hybrid network with fully 8-bit activations observes about 31% improvement memory footprint when compared to the baseline DSCN network. However, that comes at the cost of negligible loss in accuracy. And this 0.27% loss in accuracy is primarily attributed to the high sensitivity of few Strassenified layers towards 8-bit quantized activation, which you can recover if you use 16-bit activations for those few Strassenified layers and 8-bit activations for the rest of the layers in that hybrid network. I'll encourage you to look into our paper for more details on that. So in conclusion, I'll say the known compression techniques come with their own trade-offs. In this work, we propose hybrid neural tree network for this keyword spotting application, which essentially combines the strengths of neural and tree-based learning techniques in conjunction with ternary quantization and achieve about achieve modest benefit in pretty much in all the fronts, albeit with small loss in model accuracy. So thank you, and with that, I'm open for questions.
Great, thank you. Please, questions.
Jungkook from IBM. Thanks for the talk. I think all these optimization techniques are very interesting, but also it's not trivial to come up with. So I think this model is really tuned for a certain application, but how general this design methodology would be for?
Yes. So the question is how general all these techniques are, because we have make it very hard tuned for one of those applications. The thing is that, yeah, that is true to some extent. Right now we are trying it out on other more generalized networks like mobile nets and those things to make this kind of technique more sort of applicable to a whole set of applications. Yeah, this is all I can say at this point. Yeah, we have made it hard tuned for one of those applications in this work. But the expectation is as more of these applications, the IoT applications will start using this compute efficient depth-wise separable convolution layers. So this type of technique will be more handy then. So
thank you.
More questions? No. Let's thank the speaker. Thank you. So next talk is by Zhihao Jia, and he's a PhD student at Stanford working with Matej Zaharia and Alex Syken. And for his talk, he will be presenting some of the recent work on optimizing DNN computations by using relaxed graph substitutions. Actually, well, I'll present the title. So the title is Optimizing DNN Computation with Relaxed Graph Substitution. Please.
Thank you. Hi, my name is Zhihao Jia, and I'm a PhD student at Stanford working with Matej Zaharia and Alex Syken. So today I would like to talk about one of our recent work on optimizing DNN computations by using relaxed graph substitutions. Today's DNN computation graphs are becoming increasingly more complex and diverse, so different operators and different graph structures has been proposed for different learning tasks. So from a system perspective, this actually brings a very interesting research problem. So how can we systematically optimize DNN computation graphs on today's modern hardware platforms? So existing framework have been using heuristic approaches to optimize DNN computation graphs. So they perform a number of graph transformations that are manually designed by domain experts to optimize the performance of a DNN computation graph. For example, commonly used operator fusion could be fusing a convolution and a ReLU into a single convolution plus ReLU operator, because we know heuristically this fused operator will be faster than performing the two operators separately. And applying this graph transformation is very simple. Because these graph transformations are designed to optimize your performance, so you can directly apply them whenever possible on your input graph, and this will give you an optimized graph in existing frameworks. So we found there are actually several limitations with this heuristic approach. The first is robustness, because these graph transformations are designed based on experts' heuristics on common graph and architectures, so they may not apply to all models and hardwares. So as a result, you can find people on GitHub or Stack Overflow complaining that if I use XLA, which is TensorFlow's graph optimizer, why my graph is slower instead of faster than without using any graph optimization. So the second limitation is scalability, because today's DNN model keeps introducing new operators and also new graph structures to achieve new model accuracy. But so this all require a significant amount of new graph transformations to optimize these new operators and new graph structures. So the third limitation is performance issue, because existing graph transformations are designed for common graph structures, so they may miss some subtle optimizations for specific graphs. So let me show you the example of a missing optimization in existing framework. So this figure is the optimized computation graph by existing framework. And I will show you one missing optimization, and of course we found that in this paper. So maybe I should stop for a few seconds to let you think if you can transform this graph, if you can manually transform this graph to a more optimized form. So this is a non-trivial optimization, so I will just tell you the answer. So consider we have this 1-by-1 convolution, right? We can just change it to a 3-by-3 convolution by enlarging the convolution kernel. So this is possible because you can just set the extra weights to 0, so that mathematically the 3-by-3 convolution will compute the same result as this 1-by-1 convolution, right? So after that, you can fuse these two 3-by-3 convolution by concatenating the output channels of the two 3-by-3 convolution. So this is an optimization because on the new graph, you only have to access the input tensor once, compared to the original graph where you have to access the input tensor twice. And finally, you can also fuse the convolution and the following addition and ReLU to a single convolution plus ReLU operator. So we found that this final graph is 1.3 times faster on V100 GPU, but 10% slower on K8 GPUs. So maybe I should do a test. So how many of you can manually figure out this optimization by looking at the input graph? It's very hard, right? So, and also, this is a non-trivial optimization because it does not constantly improve performance. It only makes your performance better on particular hardware. So this also indicates that when we are trying to design our graph optimizations, we really need to consider the exact hardware we are trying to run our graph on. So let me show you how we can automatically find this optimization. So we propose a search-based approach. So first, instead of just considering graph transformations that optimize your performance, we consider arbitrary graph optimization, graph substitutions, as long as it preserves your computation. And second, we define a search algorithm to explore the space of potential computation graphs. And combining these two techniques, we can find optimized DN computation graphs. So we implement this idea in a system we call Metaflow. So this slide shows an overview of Metaflow. So we take as input an computation graph and also a list of potential graph substitutions. So Metaflow, a search-based graph optimizer, will automatically explore the space of all candidate graphs that are generated by different combination of your graph substitutions. So all candidate graphs in this space are equivalent, so they can compute the same output, but they have very different runtime performance. So the graph optimizer will explore that search space and generate an optimized computation graph. So we found there are two challenges in exploring the search space of candidate graphs. One is that we have many graph substitutions are irreversible. For example, you can change a 1-by-1 convolution to a 3-by-3 convolution, but you cannot change it back, right? That means if you apply some substitution and get a new graph, you may never get back to the original graph by performing other substitutions. So to solve this problem, we propose a cost-based backtracking search so that we can backtrack our search path and be able to reverse and undo some substitutions whenever possible. And the second challenge is that for today's deep neural networks, the search space is too large to directly search for. So our solution is we propose a flow-based graph splitting algorithm to partition the large graphs to multiple small subgraphs. So the bottom figure shows a data flow of our approach. So for any arbitrary input computation graph, we first perform a flow-based graph splitting to split the original graph into multiple individual subgraphs. Then we can concurrently run our search algorithm on different subgraphs and get optimized subgraphs. And we can construct an optimal computation graph by using the optimized subgraph as basic building blocks. So first, let me show you our flow-based recursive graph splitting algorithm. The problem here is that even very good search algorithms are too expensive for large graphs. So we need a way to break your entire graph to small subgraphs. So when we are trying to break it into subgraphs, our goal is to minimize the lost substitutions. We would like to preserve as many substitutions as possible. So we formulate this problem to a max-flow min-cut problem. So we define the capacity of each operator to be the number of substitutions that will use this operator. For example, this is an input computation graph, and each color shows a different substitution. And you can count the number of substitutions that will be disabled if we split along this operator. And in this case, you can find, in this case, the min cut of the graph will give you a natural splitting point to split a original graph to subgraphs. And we can recursively run this graph splitting algorithm to partition a large graph to smaller graphs with reasonable sizes. So once we have individual subgraphs, our next task is to optimize different subgraphs. So we use a cost-based backtracking search. So in our cost model, it estimates the cost of the original computation graph as the summation of individual operator costs. And we measure the cost of each distinct operator by running them on hardware. So this measurement is very similar to our FlexFlow work I presented yesterday. So we decided to use backtracking search to explore irreversible substitutions. And so we can concurrently perform our cost-based backtracking search on subgraphs. And this will give us optimized subgraphs. And after that, we can perform a second round of backtracking search along the boundary between different subgraphs to see if we can further optimize the boundary. And after the second round of the optimization, we can get an end-to-end computation graph. Okay. All right. So we have evaluated compare our idea with several existing baselines. One is TensorFlow, the second is TensorFlow XLA, and the third one is TensorRT. So these are existing DN graph optimizers for GPU. And we consider 5 DN benchmarks, 3 for image classifications and 2 for language tasks. And so this table shows a statistic of our graph substitutions. So we consider 8 performance decreasing substitutions. So we consider substitutions that will temporarily decrease your runtime performance, but will transform your graph to a new format. And we also consider operator fusions that has been widely used in existing frameworks. And third, we also consider some algebraic identity transformations, such as we think A plus B is equal to B plus A, and A times B is equal to B times A. So we can also consider these substitutions. So in total, 22 substitutions are considered in our evaluation. And because Metaflow is pluggable, so you can also add future substitutions into our search engine. So the first question I would like to answer in our evaluation is, can Metaflow improve end-to-end performance? So we compare Metaflow with the best among the existing baseline, and this table shows the relative speedup. So we can achieve 1.1 to 1.6 times speedup compared to the best existing baseline. And one thing I would like to point out is that our improvement is achieved without any loss of model accuracy because we preserve computation. So you can almost achieve this our optimization almost for free because you didn't have to worry about your accuracy loss at all. So we think this is a very nice property of Metaflow. And the second question in our evaluation is, can Metaflow be used within other frameworks beyond our Metaflow own runtime? So to validate this, we run the original graph and Metaflow optimized graph on TensorRT runtime and see if our optimized graph is faster than the original input graph on TensorRT. So this table shows the relative speedup. And as you can see that our Metaflow optimized graph is also faster than the original graph, even on TensorFlow, even on TensorRT engine. And this also indicates that our graph optimizations are general and can also be applied to other frameworks. And our next task problem in evaluation is training. Can Metaflow also be used to improve training? Because previously we have shown that it works for inference. So in Metaflow, training and inference are defined as just as different computation graphs. So the bottom figure shows an example inference graph and this cross-bounding training graph. The difference is that, so you can see that there are more data dependencies in the training graph. And Metaflow can use the same pipeline to optimize both graphs. So this table shows our training performance comparison. So we run the original graph and Metaflow's optimized graph on TensorFlow engine. And we observed 1.1 to 1.2 times speed up on different data sets. And we also observed that our speed up on training is smaller than our speed up for inference. And this is because for training, there are the additional data dependencies for training will limit the substitutions that can be applied. So as a result, we only achieve smaller speed up for training. And we also found that Metaflow can automatically find a different optimized graph on different hardware. So the left figure shows an inception modular, and the right figure shows the cross-bounding optimized graph for V100 GPU and K80 GPU. And the shadowed rectangle highlights the graph optimizations that are performed on different GPUs. And as you can see that different optimizations are performed on different GPUs. This also means that you really need to consider what hardware you're trying to use when you are doing graph optimizations. So for future work, we are actively working on Metaflow, and one of our future work is to support automated substitution generation. So this table figure shows existing overview of Metaflow. So we rely on users to define potential graph substitutions and try to search how to optimize by using existing substitutions. And our future work is to design an automatic substitution generator that will look at the input computation graph, analyze the operators and structures in the input computation graph, and automatically generating cross-bounding graph substitutions. And this will be also fit to our search-based graph optimizer. So to conclude, I have presented a search-based approach to automatically optimize DN computation graphs. And we show that our approach is able to outperform state-of-the-art approach by up to 1.6 times. And all our code is available online. And feel free to use it to optimize your own graph on your hardware. Thank you.
Thank you. Questions? Yeah, Minsik from IBM, very interesting work. So,
thank you.
Do you have any runtime information on like DZ graph optimization?
What do you mean by runtime information?
I mean, you need to spend time to transform the graph, right?
Right.
So can you comment on, let's say, then how long it would take, let's say, that for resident 50, and then let's say that how long would it take without any graph partitioning?
Oh, right. So we have some numbers in our paper. So if we didn't do any graph partitioning, directly train on the original graph, then it may take hours, even for some small graph with only 20 or 30 operators. The end-to-end search will take hours or even days. Okay. So that's why it's too large to directly search. So we need some way to partition the graph.
But have you compared your quality without any of those, let's say, the graph partitioning? I mean, did you see any, let's say, the difference in terms of quality with and without partitioning approaches?
Right. So we measure on some small graphs that we can exhaustively enumerate all potential subgraphs, and we are able to find the same optimized graph with and without graph partitioning.
All right, thank you.
Thank you.
This is Lin Yuan from Amazon. So in your talk, nice work, first of all. So in your talk, your search strategy, basically you search mapping the graph into a different combination of nodes. Have you explored the dimension of mapping the nodes to different hardware? For example, running certain nodes on certain hardware and then the rest of the nodes on GPU or CPU or something like that?
Yeah, this is a very interesting question. So the question is, have we tried to map graph onto different hardwares? So we haven't tried that, but that would be a very interesting future work direction. And I think that would be because different operators have different preference in terms of hardware. So GPU is good at something, CPU is good at some other thing, and FPGA is, I mean, each accelerator has its advantages. So it's interesting to explore the space of how to combine the advantage of different hardware accelerators.
Thank you.
Thank you.
Hi, I'm Takeo Imai from NII in Japan. My question is that I wonder how to give the cost or cost model in your, I might miss your words, but I don't understand.
All right, so we assume that the cost of the graph is the summation of cost of individual operators. So we just sum the cost of individual operators to estimate the cost of the graph. And we so we measure the cost of individual operators by measuring the operator on hardware. So we directly run them on hardware to know the cost of the operator.
So the cost, is the cost depend on the hardware?
Yes, the cost depends on hardware.
So how to estimate that?
So we directly run them on hardware.
Okay.
Yeah, maybe you can talk offline. Maybe.
I see.
Thank you.
Okay, thank you.
Hi, I'm Yao from Amazon, and I have a question about Metaflow itself.
Mm-hmm.
You mentioned that you have its own runtime or execution engine for Metaflow.
Yes.
So the number you said that here is up to 1.6 is comparing directly like using Metaflow execution engine with TensorFlow execution engine, or it's just like optimize the graph and you use TensorFlow execution engine to run it and achieve 1.6.
Right. So actually, in the paper, we show numbers for both executions. So we run the optimized graph on our runtime and also on other runtimes. We show all the numbers in the paper. But for this particular figure, the speed up is the comparison is between the original graph in best existing framework and the optimized graph in our Metaflow framework.
Okay. So is it possible that some performance gain comes from the difference of the execution engine,
right?
Instead of
so we found because we directly use cuDNN library and cuBLAS library. So as a result, our Metaflow runtime has almost identical performance as TensorRT.
Okay.
Right.
Okay. Thank you.
Thank you.
By the way, Zhao was participating in artifact evaluation. It was really cool to try your tool. Thank you. Okay, let's thank the speaker. Okay, our last talk is by Adam Lehrer, and he's a research engineer at Facebook AI Research, where he's currently working on multi-agent learning in games and systems for large-scale machine learning. And he was involved in the development of PyTorch, and most recently has developed new methods for learning in strategic games such as poker. And prior to joining Facebook, Adam worked at the Show Research, where he worked on Anton, a special-purpose supercomputer for molecular dynamics simulation. And his talk will be about PyTorch Big Graph, a large-scale graph embedding system. Please.
Thanks. Hello, my name is Adam Lehrer, and I'm going to be talking about PyTorch Big Graph, which is a system for training embeddings of very large graphs. And this is joint work with Lidell Wu, Jiajun Shen, and Abhijit Bose, who are here, as well as some other colleagues at Facebook AI Research. So first, I'm going to talk to you a bit about what graph embeddings are and why you should be interested in training embeddings of very large graphs. And then I'm going to talk about some of the modifications that we make to traditional graph embedding systems in order to scale to very large graphs. And then finally, we'll look at some experimental results about the scaling of this system. So first of all, an embedding is a learned map that maps from some kind of entity to a vector of numbers that encodes some notion of semantic similarity between these entities. So most people who have heard of embeddings would probably have heard of word embeddings like word2vec. And in word2vec, that type of embedding, you learn a vector of numbers for each word such that you can predict a word in a corpus of text from its context. And what happens there is it's this unsupervised method where you just train it on a corpus of text and you learn features for each word that encode the semantics of those words. And you have a similar notion for graph embeddings. And in graph embeddings, what you're trying to learn are vector representations of each node in a graph. And you train them again with stochastic gradient descent on these vectors with the objective that nodes in the graph that are connected have more similar embeddings than nodes that are not connected in the graph. Since actually in this paper we're going to be looking at multi-relation graphs, it's a little bit more complex than that, but essentially you're computing a similarity metric or some score for edges in the graph that should be higher for edges in the graph that exist than potential edges that do not exist. I also want to mention, because I got some questions about this, that graph embeddings are not the same as graph neural networks. Graph neural networks are a parametric supervised learning method on graphs where you have labels for nodes and you're trying to predict them based on features of the nodes. Whereas graph embeddings are actually trying to just take in a graph and learn features for each node that encode this similarity based on the context that these nodes occur in. So the reason that you might be interested in learning graph embeddings is that they're a form of unsupervised learning on graphs, and what you end up with is a set of task-agnostic node representations or features that you can use for a number of downstream tasks. Because like most ML tasks like classification and clustering, you can't operate directly on graphs, but they can operate on features that you can learn from these graphs. And things like nearest neighbors are semantically meaningful, so you can take these features from this graph and say, I know about this node I'm interested in, tell me other nodes that are like this. So this is the only slide that's going to include math, so I just want to give a little bit more of the formalism of these models. I've included references to some of the models that are going to be encompassed by this kind of general class. But what you're basically doing is you're computing some loss between the score for an edge that exists in the graph and a negative sampled edge, some edge that doesn't exist in the graph. So here I'm showing a margin loss, where f of e is the score for an actual edge in the graph, and f of e prime is an edge that doesn't exist in the graph. And here you're just trying to optimize a margin loss that tries to make the score for a real edge higher than the score for a non-existent edge. And the way you compute this score is some similarity metric that combines the source embedding, the embedding of the source node, the embedding of the destination node, and some embedding of the type of relation that you're encoding. So in this example, you look at the cosine similarity between the embedding of the source node and the sum of the relation and the destination embeddings. And the way you construct these negative samples is by taking a real node in the graph and replacing either the source or the destination entity with some other node. So for this node BC, which is in your data set, you're going to construct negative samples like BE and BA, as well as negative samples such as AC and DC. So these multi-relation graph embeddings are studied across a number of different types of data sets. The way it's most commonly studied is in terms of knowledge graphs. So for example, if you considered Freebase as the structured information, or Wikidata is like the structured version of Wikipedia that shows all the connections between the entities of Wikipedia, like Hawaii is a state in the United States, Barack Obama is the president of the United States, and so on. But people are also interested in a similar problem for recommender systems, which is a more supervised task where you have connections between like ratings of movies, and also for social graphs where you're interested in propagating kind of the attributes of people in some social graph based on homophily, based on the fact that people who are connected in a social graph have similar attributes. But the graphs that we're interested in are slightly different. They're somewhat related to this class, but the type of graph that we're more interested in is like, imagine you have a music streaming service. You really have this very large graph where you can think of all the users and all the songs and genres and albums and artists as nodes in this graph, and then you have a number of different types of relations where you can look at an edge in this graph for like every song that a user has listened to or bookmarked or bought, and you also have parts of the graph that for different types of entities that correspond to like an artist that produced a song or how artists collaborated. And if you train a single embedding of all of these different entities in a single space, you can ask really interesting questions like, tell me which genres are similar, even though you don't have any explicit information about the genres, or I have these 5 songs in French, tell me about some more songs that are in French. I want it to predict other songs that fit into the same class. just by using like nearest neighbors, for example, on these embeddings. But the thing about these types of online interaction data sets is that they're really big data. So web companies have data sets like this that could have billions of nodes and trillions of edges. And if you think of a graph that has 2 billion nodes and you just pick an embedding size of 100 dimensions, you now have an 800 gigabyte model, which doesn't fit in even CPU memory, let alone on the GPU. And then when you look at graphs of this size, training speed is also an issue. When I'm trying to like train on a data set of size 1 trillion, training speed is also obviously an issue. So we want to ameliorate both these problems. So the main approach we take with PyTorch Big Graph is, a similar approach to many ways of, speeding up graph algorithms, which is you do a matrix blocking to subdivide the graph. So what you do is you take every node and you pick some way of sharding them into n groups. So you could just say you uniformly assign an index 1 through n for each node. And what this means is that every edge is now divided into one of n squared buckets based on the source and destination node shard. So, if you think of bucket 3.1 here in red, that is the edges that belong in there have their source node in shard 3 and their destination node in shard 1. And what this buys you is that if you, for example, if you want to train on a single machine, you get this temporal locality property where you can train on this whole bucket of edges in 3, 1, and you only need to store part of your model in memory, like the embeddings for shard 3 and shard 1, and everything else can be swapped out to disk. And then it also means that you can do distributed training because different buckets that use different parts of the model can be trained in parallel without having to do any synchronization after every SGD step with a parameter server. You just do them completely, you can do them almost completely in parallel, and you only have to do communication between the machines when a machine starts working on a different bucket, because then it has to transfer that part of the model from one machine to another. So I would point out that this is not a lossless modification to the training objective. There are two ways in which this modifies your training. One is that you're no longer sampling edges independently because you're working on one bucket of edges at a time. And there are theoretical results that say that this kind of non-IID sampling of your data still converges to the same result, but it may converge slower. And second of all, the distribution of negative samples change, because if I'm looking at an edge in one bucket, I can only construct negative edges out of that same bucket. So we do have to validate empirically that these modifications still produce similar quality models. So I'm going to talk a bit about how we do the distributed training in PyTorch Big Graph. Basically, we need to do 3 different types of communication between the machines. And this is all coordinated. When you launch the trainers on the different machines, they all launch sub-process servers that are able to do all these different types of communication. So the first thing is that you have to synchronize which machine is working on which bucket of edges. And this is done with a lock server that assigns buckets to machines. And the way it does it is basically just trying to greedily maximize machine partition affinity. So if a machine has worked on bucket 3, 1, maybe it will next work on bucket 3, 5, so that it only has to exchange one partition of the data instead of 2. The second thing is you actually have to exchange the model partitions. And the way this is done is that when partitions of the model are not in use, they're stored in a sharded partition server that's sharded across the training machines. And finally, there's a very small number of model parameters that can't actually be sharded in this way, specifically the embeddings of the relations. And this is, you don't have very many different relation types, so this is just kilobytes or a couple megabytes of model parameters, and these are handled with your traditional parameter server, and they're just updated asynchronously with a standard parameter server model. But that's just like a megabyte of parameters as opposed to the gigabytes of node embeddings. And this is all implemented with the MPI-like PyTorch distributed primitives that are used that you can construct sort of model parallel training or model parallel structures in PyTorch. And this runs on top of MPI or TCP, whatever you're running on for your distributed architecture. So there's one other thing that we do in PyTorch Big Graph in order to improve training speed. And that is, it's based on the fact that training time is generally dominated by the negative sampling edges. Because for every edge in the real graph, you typically don't just compute one negative sample, you compute 10 or 100 negative samples. And so you're kind of dominated by the time in the random access lookup of those embeddings and the computation of the scores for those embeddings. So what we do is we say, what if we take a sub-batch of 100 real edges and use the same set of random nodes to construct 10,000 negative samples instead of using different random nodes to corrupt each of those 100 edges in the batch. What this does is, first of all, it reduces the random access memory bandwidth by a factor of 100 for negative sampling. And also, you can notice that if the similarity metric is based on a dot product or a cosine similarity, then the batch of negative scores can just be computed as a matrix multiply between the node embeddings of the positive source node embeddings and the negative destination embeddings, which is, ends up being a lot more efficient. And what you find as a result of this is that if you do traditional negative sampling, that your training speed is, and previous work has reported this, your training speed is basically inversely proportional to the number of negative samples you use, whereas with this optimized negative sampling, you get pretty much constant training speed up to about 100 negatives. So the first thing we did, now I'm moving on to the experimental section, the first thing experimentally we looked at is just like this knowledge graph of Freebase, which is basically the standard for looking at these multi-relation graphs. And they typically work on this very small subset of Freebase that has 15,000 entities. And what we find is when we implement different models, including the state-of-the-art complex model, that in PBG we replicate or get higher accuracy on a basically link prediction or knowledge-based completion task as the original papers. The only thing that we're not replicating here is this one paper, which was from a co-author that's just like uses huge embeddings and is really fancy. And so even the co-author said that it's not worth reproducing this because the fact that you can get very high knowledge-based completion doesn't necessarily mean that these embeddings are necessarily useful on a downstream task. We actually can reproduce these, but we don't report them here. But then what we do is we train these embeddings on the full Freebase graph, and I think this is the first, at least reported result of embeddings on the full Freebase graph, which has 51 million nodes and 1 billion edges. So on the right, you see a t-SNE plot of some of the nodes based on the full Freebase embedding, and what you see is you have a clustering at the top of different professions, a clustering of numbers, a clustering of countries. And this is just a very small subset, but you have like basically every entity in Wikipedia embedded in this same space. And what we show is that as you partition the graph more finely, you use less memory down to, with 16 partitions, you use, 8x less memory while achieving the same performance and mean reciprocal rank, which is the metric you use for these tasks. Next, we look at parallel training, and the results here are more mixed on knowledge graphs, because what we find is we get reasonable parallelization up to 4 machines, but then we start to observe model degradation above that. And in general, we found that for knowledge graphs, parallel training is quite finicky for a couple reasons. One of them is that you have a very large number of relations compared to most of the graphs we look at, and so the parameter server has to synchronize all of those. And just the structure of these graphs is quite complex. And so when you actually look in terms of time, the improvements are kind of modest, and I wouldn't necessarily use this on a knowledge graph I wouldn't necessarily use parallel training for knowledge graphs. However, across a number of different data sets that we tried that were more like social graph data sets, for example, Twitter, we find that they're not finicky in the same way, and pretty much like no matter how we train them, we get close to linear speedups with no degradation in model quality with partition and parallel training. We speculate there are several reasons why these graphs are different, but I'm not going to speculate too much on that here, but say that we kind of leave that to future work of untangling the different causes of model degradation in knowledge graphs and maybe ameliorating them. But to be honest, knowledge graphs are not really the purpose of PyTorch Big Graph, and we found in most of the data sets that we're actually interested in that this hasn't been a problem. Some other things that I think are interesting future work. One is looking at how to do parallel training for graphs that have featureized nodes. So like either bag of words, you know, if you have a node that's a description of a song, right, then you would want to do bag of words embedding of that text as part of the graph. And we do actually support this for single node, but thinking about how to parallelize that is an interesting direction for future work, as well as like dense node attributes. And finally, I think that there's a really interesting direction of future work where you can apply the same techniques to also do GPU training, because currently this only runs on the CPU, because GPUs have like another 10x lower memory capacity, but you could do the same kind of matrix blocking hierarchically. And so on each machine, you're then going to subdivide the nodes even further and, you know, do parallel training on multiple GPUs where you swap the different shards across the GPUs to do multi-GPU, multi-machine training. So that's basically the end of my talk. The code and embeddings just got released. The code and embeddings for Wikidata, which is this knowledge graph, were released today, so please check it out. I just want to mention that I think the world is full of big graphs. Things like online interactions, Bitcoin transactions, medical records, purchases, biological networks, and so on. And we really only looked at a couple things here. And so I hope people try this out for other kinds of large graphs. PyTorch Big Graph is really designed for graphs that are quite a bit bigger than even the largest currently available public data sets. So we kind of hope that this spurs people to work on even larger data sets and look at graph embeddings for bigger data. Thank you.
Thank you. Questions?
My name is Sefaridi from Sweden. Just a general question. This graph embedding, I mean, normally people use distributed graph frameworks or graph databases to solve problems on graphs. What these kind of techniques will give more than what's existing today?
Yes, so there are a lot of.
I mean, you can do a lot of things by these distributed general frameworks with graphs or graph databases and so on.
Yeah, that's true. So for a lot of like traditional graph metrics, if I want to find like the min cut of a graph or even an SVD of the graph, which is somewhat similar to what we're doing here, there are existing kind of distributed graph frameworks that do this. But what this is basically providing is, first of all, these kind of multi-relation graphs aren't really handled by any existing system. And it's not clear that they could be. And in general, what we kind of want here is that you can put in any kind of loss function you want for SGD, and you can train kind of generic multi-entity, multi-relation graphs, you know, for where in PyTorch, like you have automatic differentiation. So I pick any model I want, right? Just write down your model, and then what you get here is that you can train kind of generic models via SGD with automatic differentiation and negative sampling. These aren't really capabilities that are built into these other frameworks, even though they might use some of the same kind of distribution methodology.
Hi, I'm Minjie from NYU. Really nice work. So my question is, what's your opinion about those graph embedding algorithms based on random walk and graph sampling, such as deep walk and NoToVec? And can PyTorch Big Graph actually support that very easily, or you think it requires a significantly like different system design?
Yeah, that's a good question, and we do talk a bit about this in the paper. So deep walk, there are kind of two different classes of algorithms for graph embeddings. One of them kind of looks more like word2vec, where you do random walks in the graph and try to construct embeddings based on that, or this one which is more for knowledge graph embeddings. The deep walk stuff has been more used for social graph embeddings, and it's kind of earlier work. And we actually compared on like some of the data sets right out of the deep walk paper, and we found that both on the original task they proposed and for downstream unsupervised tasks that these knowledge graph embedding methods performed as well or better than the deep walk type embeddings. They performed a lot better actually on downstream unsupervised tasks, and we found that they were like orders of magnitude faster. So I actually have some plots here about this. So here we compared a deep walk actually, and we find that the red line is like our graph embeddings, and this is looking at link prediction, which you may not say is necessarily fair because that's what Deep Walk, not necessarily what Deep Walk is made for, but if you look at like the YouTube data set, which is what they actually test on, we also do better than that at like downstream tasks. So I think there are classes where the Deep Walk type embeddings might be better, but for the things we've looked at, they haven't been.
I see. So another small like technical question is when you do negative sampling and when you process one edge block, how can you avoid like get these negative samples that it appears in other edge blocks?
Right, so we don't actually, the negative sampling doesn't explicitly exclude edges that are in the training set. So what you find is that these graphs are very sparse, so it's not usually an issue of just like picking random negatives. It is the case that how you choose your negatives is one of the most important things, and there's stuff we talk about exactly what distribution, just like in Word2Vec, like the distribution of negative examples that you choose ends up being very important for how generalizable these are in downstream tasks. So we talk about that a bit in the paper.
Okay, thank you.
June from UC Berkeley. So the interesting thing about graphs is that I'm particularly interested in how you sharded them. So graphs have a huge number of nodes that have very little information, very little edges, and few nodes that have lots of edges, et cetera. Did you take that into account when determining the sharding? I would love to hear more about what things you tried with the sharding, what worked, what didn't.
Yeah, it's a good question, and it's something that we thought quite a bit about. But actually, there's a bunch of trade-offs in how you do that. What we end up doing is just uniformly sharding nodes. But another thing you could do is like shard by degree, and there's kind of trade-offs there. But for example, you'd think that like sharding, one thing you end up with if you shard not uniformly is that you get load imbalance across your different across the different buckets, which is something you don't want. But one thing that we've thought about might be better about sharding, let's say by degree, is if you first do the high degree edges first, then you might get a better layout of the embedding space. And then you can add in the lower degree edges, which don't affect the final layout as much, and that's something that we're experimenting with.
And that begs a follow-up question. Did you do any pruning on the data set to determine what was eligible for going into the embedding?
That's a good question. It's not something that we explore in the paper, but it's definitely something that we've looked at, internally. And there's a interesting trade-off that I think is an important direction for future work about like where do you cut off, like first of all, where do you cut off kind of, how do you prune what you use for the embedding, and then how do you propagate the embeddings from the part of the graph you do train? It's a little bit more obvious in a single relation graph that you can just sort of average the embeddings of your neighbors to get the embeddings of the things that have low degree. It's less clear for like a multi-relation graph how to do that or what's the optimal strategy for doing that.
Thanks.
But that's a great question. And it's something. Yeah.
Cool. So let's thank the speaker again. And now we'll have a coffee break, and please come back in half an hour for the last session. Thank you.
So you'll have 18 minutes, right? And then you have a timer down there. Okay. And for questions, is an extra 4 minutes. I know. Okay. Perfect. Perfect. So they have both HDMI. Yeah. I'll take this out. Is that okay? Yeah.
I'll just use the microphone and the keyboards,
so
right?
This will be. I will be using that.
Okay.
Yeah.
Perfect.
And just make sure they're gonna be close to the picture. Yes. Oh, okay, got it. Yeah, so I just.
Hi. Hi. Good. How are you? Same. I'll grab first one. Second orphan.
Oh, you mean? I see what you're. So
No,
two speakers.
Michael is not there. He's staying in the UK.
Yes,
Yeah, correct.
Yeah. So that's for the second person. Got it. Awesome. Perfect. Thank you so much. All right, there we are.
Perfect.
It's working.
So you're just HDMI directly?
It's empty. Okay. It's emptying out.
All right, welcome back to our last but not least session of SysML for this year. Just want to let you know, after the session ends at 6 o'clock, our chair, our general chair, Amit, is going to have some short closing remarks, so please stay for that. And we'll have now Sven Mika from RL Core, who's going to kick off this session. He's going to talk about computation graphs for deep RL.
Thank you very much. Good afternoon. Today I'll present our paper on our software system, Python-based, by the name of RL Graph. And it's, with RL Graph, you can build and execute modular computation graphs for deep reinforcement learning. This is a collaboration with Michael and Eiko from the University of Cambridge, as well as Kai from HSU Hamburg. Before we talk about RL Graph, let me quickly recap what reinforcement learning is. In reinforcement learning, we have a dynamic environment which produces state and reward signals. These signals are picked up by our agent, by our reinforcement learning algorithm, which then maps these signals to action outputs, and these actions are applied to the environment, and the environment reacts via its underlying rules and physics based on these actions, and it outputs new state and new reward signals. So this is an ongoing iteration. It can go on for some time, and the goal of the agent is to maximize over its lifetime the total sum of individual reward signals. What are the differences between supervised learning and reinforcement learning with respect to workloads and execution patterns? In reinforcement learning, we have this constant requirement of collecting data while we learn. So this has to happen simultaneously to learning. We cannot collect data first and then learn and we're done with. This has to happen at the same time. One way of doing this, of speeding up this process of data collection, is to parallelize the environment and then to drop special agent copies into these individual environments to collect samples. So this then brings the need of data exchange. So you need to send trajectories, episode trajectories from the individual environments up to the centralized learner or learners. There could be more than one. And on the other hand, you have to send down or synchronize down the neural network weights and parameters to your environment workers from time to time to keep them updated. This is one reason why reinforcement learning workloads are complex. There are a lot of different ways of how to do this. And another important difference between RL and supervised learning is the fact that we don't have labeled data sets. So we have to work with often with very low quality reward signals, could be sparse or delayed. And this leads to instabilities in the learning process. Our loss functions are more bootstrapped than the supervised ones. So all in all, it's reinforcement learning is even more sensitive to hyperparameters than supervised learning. There are a number of existing libraries and reinforcement learning algorithm implementations available. They offer good results on select environments, and of course they provide concise code references on a per algorithm basis. What we did find was that often they're hard to retool to other environment types or to different execution modes. So there's no simple switch that you can flip to make a single-threaded algorithm run in distributed mode or in multi-GPU mode. And this is the part of the reason for that is that there's a lot of implicit dependencies between parts, which then also leads to limited testability. So you cannot take out a component from this code and test it as such, as a single component, or take out two components and test them together in combination. So this leads to limited testability, and also often they're restricted to single backends. So it's either they support TensorFlow or PyTorch. Some of them have a set of algorithms that runs on TensorFlow and a set of different algorithms that runs on PyTorch. You see a list here of the other methods that we mentioned in the paper, and there's actually more. You can go to the paper and check out the discussion on the related work. What does RLGraph do differently to address these issues? We have so this is basically the bottom line of today's talk. We separate concerns. This is our design stack, and we're going to go step by step through each of these layers in the following slides. Just to give you a quick overview, we have a top-level API, and this is the API that the agent uses to step through the algorithm. So it's usually a handful of methods that you can call, and this is what you would use if you just want to use RLGraph to solve your problem with an off-the-shelf algorithm of ours. Underneath that is the what we call the abstract data flow definition layer or the component graph layer. In this layer, you would operate if you would design your own algorithms. And here you define in a very abstract, high-level way how data will flow through your computation graph. So you basically hash out the basics of your algorithm. And separate from that, we have the local backend layer. So we support TensorFlow and PyTorch currently. Meaning both paradigm static graph as well as defined by run. And the TensorFlow and the PyTorch code is nicely encapsulated in special functions, so you can easily in the future add support for a third backend such as TensorFlow 2.0 and others. Again, separate from that, separate from the local backend layer is the distributed execution layer. We support also here different engines, distributed TensorFlow as well as Ray. And of course, RLGraph runs on all hardware. So let's go step by step now through the different design layers. Top-level API, our agent has a root component, and each component has an API. So we define very shallowly 3 methods that the agent will need to step through the algorithm. For example, update to learn something, observe to push data into the memory, and act to step through the environment. And now we're going to create subcomponents, and we're going to place these subcomponents into the root component. So these are the components that we need to execute the algorithm. We need an optimizer. These are simple Python constructor calls. You pass them some configuration parameters as constructor arguments. You create an optimizer, you place it into the root component. You do the same. We also need a neural network. We need a loss function, and we need a memory. Note here that some of these subcomponents that you're placing into the root have their own subcomponents whose API they can use. So each component has an API, and it can use and call its subcomponents' API methods. And again, the agent only has access to the top-level API. So you end up with an arbitrarily nested component tree without so far any connections between the components. The connections we're going to make now in the next layer where we build the component graph. And we do this again in a very abstract way. So this is the step where you abstractly define how data will flow through your algorithm. So let's say we take the update method and we define that it will call the sample method of the memory component. It gets an abstract data record back. It pushes that through the neural network. Again, gets an abstract data record back, pushes it through the loss function, and then we do the optimizer step. So this is how you hash out in a very high-level abstract way using simple Python code, how your algorithm should work. Again, we have no shape data at this moment. We have no idea what our data types are or whether it's batch data or not. The very abstract layout of the algorithm. At this time, if you have multiple GPUs, you can tell our graph to restructure this idea of the algorithm to make the same algorithm run with multiple GPUs. And it will automatically create the GPU towers. It will automatically repipe everything and then make sure that the algorithm that you defined here runs on multiple GPUs. The next layer is the local backend layer, and now we get to the actual, what we call the build process. So here we do have to define input spaces for the first time only for the outermost component. The following steps are all automated, so all you have to do here is call agent.build. And it will basically trickle down in an iterative build process these placeholders, create tensors out of it, and push them through the components in exactly the same way as you have defined before, in the step before when you did this abstract data flow definitions. We have the concept of component readiness. So a component is ready when it knows its input spaces. And when it's ready, we assign explicitly and automatically devices to the entire component. We assign scopes. We create and share variables for the component, sharing, of course, optional. And we call the components computation functions. And while these spaces and tensors are trickling down the components, you get intermediate spaces which are inferred automatically. And eventually you call these computation functions here. So in case of TensorFlow, this means that right now you're building your static end-to-end graph. And in case of PyTorch, this means that right now we're doing test calls with dummy tensors through the defined by run functions to make sure everything is wired correctly. And if it's not, you get meaningful error messages. So you end up with some output for this particular update API method. So this component-wise approach allows us to create really nice visualizations of the computation graph. This is a TensorBoard visualization of our Impala algorithm. And you get this off the bat just by using our graph. So you define your abstract data flow with our graph, and then you say agent.build, and you get this exact TensorBoard graph. So you can see nicely here each component. You can see where it's placed, and you can see the data flow really nicely between the different components. So it's very good for debugging. This is a comparison to when you use direct TensorFlow scripting. This is DeepMind's Impala repository, the reference implementation of Impala, where they're using direct TensorFlow scripting and Sonnet. So you can see it's much more dispersed. You would have to put in a lot of work, manual work, to make it look like ours. Fourth layer, we have the distributed execution engine, and again, it's separate from the local backend layer. So this is a diagram of our build and execution process. What we talked so far about was the first, the yellow section here, and now you can basically plug in your distributed execution engine. We support both Ray and distributed TensorFlow, and you can actually combine. So if you have a local TensorFlow agent, you can run it in distributed mode using Ray, or you can choose distributed TensorFlow. You cannot combine a PyTorch, local PyTorch with distributed TensorFlow, of course. That's the only combination that doesn't work. Quick intermediary summary. Our graph is a programming model to design and execute reinforcement learning algorithms in a backend agnostic fashion. Our graph generates incrementally testable, transparently configurable code through a strict build process. What does incrementally testable mean? It means that you can take very simple components and test them end-to-end as your entire algorithm, basically. And then you take more complex ones, composed of these simple components, test them end-to-end. We have over 300 test cases. We test all our components and abide to very strict software development standards. Our graph offers a high-level API for practitioners, so you can use our algorithms off the shelf and run them right away on your problem domain. And for researchers that want to develop their own algorithms, most of the time you operate in the first two layers, top-level API as well as abstract data flow definition. Evaluation, we ran a couple of experiments to ascertain learning capabilities as well as runtime and build time performance in terms of speed. So this is the first experiment. We measured the build time overhead. So basically, how much time do you add when compiling your graph using our graph versus not using our graph. We tested both backends, TensorFlow and PyTorch. There's two sections here. Dataflow is the second layer where you define your abstract data flow, and build is your the actual build process where you build the static end-to-end graph. DQN is a full-blown algorithm with 60 components. Network had over 1 million weights, so it took less than a second to build this, it took less than a second overhead to build the graph with our graph. Compare this to the execution times of many hours when you run reinforcement learning experiments on a lot of environments. This is really, no real overhead there. Next, we measured the runtime overhead. Here we used the Pong environment, which is an Atari-based, image-based game environment. And in this experiment, we just did stepping. So we wanted to know how fast can our algorithms step through the environment. So there were no learning updates done in this experiment. We measured against different numbers of vectorized environments on a single threaded worker. So it's a single worker that operates on many environments in parallel, gets many state signals. So it's basically the batch size, the state batch size, and it outputs a batch of actions. You can see here that the interesting here is for PyTorch you have a slight overhead, our graph versus the hand-tuned one, which hand-tuned means without our graph. This is due to the fact that for the execution time in PyTorch, there is some overhead because we're doing additional function calls. For TensorFlow, it didn't matter. That's why you only see one curve here, the red one. Because for TensorFlow, after the build process, you end up with a fully qualified end-to-end graph, and there's no difference whatsoever between using our graph and not using our graph. So it performs just as well as direct scripting. Next, we tried to learn the same environment, so we tried to solve it basically. So again, this is the Pong environment. On the y-axis, you have minus 21 means you have not learned. You're basically acting randomly. You lose all the time. And plus 21 means you mastered the environment. You win every single game against the computer player. You can see here, this is with our Apex algorithm, which is a distributed flavor of the DQN algorithm. Our line is the blue one. You can see that we learned the environment in less than 2 hours using 32 workers and 1 GPU. And we compare this to the back then state-of-the-art reference implementation of Ray RLib. The reason why we're faster here, why we're learning faster, is because we found we did a thorough analysis of each component for the entire graph pipeline, and we found that we could save a lot of time on reducing session calls. So we batched together the post-processing data that were collected by the different workers, and we were able to cut down on the number of session calls. That was the main reason. We found many other components that had slight optimization potential, and we exploited that. This is the same experiment using 2 GPUs. So this is basically, the blue line is the same as before, and the green line now shows the same agent, but with 2 GPUs. Using the before-mentioned system for rewiring and creating these GPU towers, which is done automatically for you by the library. So you can see that the speed up is significant. It doesn't quite perform twice as fast, but of course there's always some overhead when you have multiple GPUs. Last experiment, this is using the Impala algorithm on a different environment, DeepMind Lab. It's a three-dimensional environment where you also have images as well as a text stream. So you have to process both, and you have to navigate through this three-dimensional maze and avoid certain items and collect other items. In this experiment, we did acting as well as learning updates, and again, we measured the environment frames per second using different number of parallelized workers. You can see that we couldn't really perform faster than the DeepMind reference implementation. This is mostly due to the fact that this is a fully TensorFlow end-to-end algorithm where even the environment interaction is fused into the graph using a TensorFlow PyFunc operator. Lastly, summary and outlook, reinforcement learning workloads are hard, and we need new programming models. Our graph enforces a strict build process, and it separates concerns. And we focus on data flow composition, not backend specific code. For the future, we will look at integrating autograph, which we'll hear about in a second, in the next talk, I think, or in one of the next talks, as well as for PyTorch JIT tracing. And our code is available as open source under the Apache license on GitHub. Please check it out. Thank you so much.
Please come to the mic if you have any questions.
Hi, Ash Unity. Super cool work. I had a question. So does your framework make any assumptions in terms of the API to the environment?
No.
Okay, so I could possibly have an environment that relies heavily on a GPU but has a GIM interface, for example.
Yeah, correct. We have several adapters implemented that you can use off the shelf. OpenAI GIM, of course, is one of them.
Okay.
Of course, you have to be, some environments have some crazy state space, right? They give you a dictionary, then you have many flows, many streams of data. Like this Impala DeepMind had an image stream and a text stream. So, but in general, the agents and when you create these abstract data flows, it's independent of that.
Okay. Yeah. But I assume that I would have to manage which GPUs the environments run on as opposed to, I guess, allocating some GPUs for RL graph?
You wouldn't, yeah. So far, we've experimented without GPUs in the environment. So our workers run on CPUs, and we use only GPUs for learning. So the experiences, the trajectories are sent to the learner, and then the learner has a GPU, and it takes the experience and learns from them. But for environment interactions, we haven't used GPUs. That's actually an interesting question. You're asking probably because of the game engine, right?
Yeah.
It's an interesting question, and we haven't done any experiments on that.
And I guess one thing I'd be interested in is the kind of thrashing that happens when the game engine wants to use the GPU, and then you're flushing the data out of the buffer back into the CPU memory, and then the learner takes over, and the stuff that happens there. The other question was a technical point on your comparison between RL graph and RL lib. Was the execution engine for RL graph Ray in that case?
Yes, correct. Yeah, correct.
Okay, cool.
So yeah, so basically both use Ray. Yeah, that's right.
All right, awesome. Thank you.
Yeah, sure. Thank you.
Great. Let's thank Sven again.
Thanks, Owen.
And now we'll have Akshay Agrawal from Stanford, who's going to talk about TensorFlow Eager, which is a new multi-stage Python-embedded domain-specific language for machine learning.
Hi, so my name is Akshay Agrawal. I was at Google Brain from 2017 to 2018, and I'm now a PhD student in the convex optimization group here at Stanford. So I'm going to talk about TensorFlow Eager, and TensorFlow Eager is a part of TensorFlow that makes it possible to mix both imperative programming and declarative programming. So the emphasis in machine learning research has recently shifted from building static DNNs to differentiating through complicated programs. And these complicated programs might have data-dependent control flow, they might use complicated data structures, and so on. Because of this shift, libraries for machine learning or for differentiable programming are becoming more and more complicated, and it's come to the point that an argument has been made that these libraries are beginning to resemble domain-specific languages. And these so-called DSLs are usually embedded in a host language, and the language is usually, but it's not always, Python. Most of these Python libraries offer one of two different programming styles. So they're either imperative, like Chainer or Torch, where operations are executed immediately, or they're declarative, like TensorFlow or Theano, where programmers first construct data flow graphs before executing them. There are some exceptions to this dichotomy, like MXNet, JAX, and PyTorch 1.0, which do let you hybridize the two programming models. So imperative programming has many obvious advantages. I mean, the first and foremost, it's really easy to get started with it because it offers a familiar programming model. And it also sort of enables programmer creativity because you can use the full extent of the host language. The main drawback is that if your library is a Python-based library, then your performance can become bottlenecked on the interpreter when the operations you're running are very small. So there is a reason, of course, that TensorFlow was designed around Dataflow graphs. By separating the specification of your program from its execution, you're no longer bottlenecked on the interpreter, the Python interpreter. And so then you can do things like whole program analysis, you can do compiler optimizations, your runtime can exploit inter-op parallelism, it can automatically reuse buffers, and so on. And having graphs as an IR also simplifies deployment, distribution, code generation, and serialization. The main problem with graph-based libraries like TensorFlow is that they have steep learning curves, and because you're limited to using the constructs that the library provides, such as like in-graph control flow, it becomes sort of prohibitively difficult to express certain types of models. So ideally, we'd have an imperative DSL that would let you drop into sort of more performance graph execution when needed. So the solution that TensorFlow Eager proposes is to mix imperative programming and declarative programming, or graphs, in a way that can be interpreted as multi-stage programming. Multi-stage programming is a well-studied technique in programming languages, and it can be discussed in a very formal way, but we're going to keep the discussion at an extremely high level in this talk. Oh, I should say that TensorFlow Eager is not unique in offering this kind of programming model. Again, so MXNet, JAX, PyTorch 1.0, and more recently SNEC plus Autograph all offer sort of similar programming models, but we'll use TensorFlow Eager as the case study here. So by default, in TensorFlow Eager, all operations are executed imperatively or eagerly. For users that want any of the benefits that graphs provide, we provide a decorator at tf.function that will stage Python functions into graph functions. And it does this in a just-in-time way. A graph function is just a TensorFlow graph that has named inputs and outputs. TensorFlow Eager is implemented as an opt-in extension to TensorFlow today, and it's compatible with basically all of our TensorFlow APIs. In 2.0, TensorFlow Eager is always enabled. TensorFlow 2.0, that is. So this is a simple code example that shows what imperative execution looks like in TensorFlow Eager. The second line of code there essentially transforms TensorFlow into TensorFlow Eager, so it's important. And everything else is as you would expect. TF.1s returns a concrete tensor backed by numerical data, and the add operation will execute immediately. By adding that single line at tf.function, transforms the add function into a Python callable that will execute an equivalent Dataflow graph. And you can see that from the programmer's perspective, executing a graph function is syntactically equivalent to executing the corresponding Python function. And you can also see, if you look at the last line of code, that the graph function is polymorphic in the types of its inputs, even though TensorFlow graphs are not polymorphic. So we'll talk a little bit about how we do that in just a minute. And I guess another thing to notice is that there are no TensorFlow sessions in sight anywhere. That's because the decorator abstracts away both the graph construction and also the graph runtime. So at a very high level, this is the multi-stage workflow that we recommend to most users of TensorFlow Eager. The first step is to obviously implement your model or your differentiable program, but to implement it in sort of purely imperative mode, because that will let you use things like Python debuggers and so on. And the second step is if the performance of your program is not to your liking, then you drop in, you use whatever Python profiler you want, you use PDB to find bottlenecks. And then specifically, you find bottlenecks that consist of TensorFlow Eager code. And the third step is to refactor those bottlenecks into functions. Python functions and then add tf.function decorators to stage them into graph functions so you can recover performance. We anticipate that most people won't need to do the second and third steps, especially if they're sticking to our high-level APIs, which are already performant. So I'll provide just a few details on how we've implemented imperative execution, very few. As a recap, in TensorFlow, primitive functions are called operations, and their implementations are called kernels. So basically, in TensorFlow Eager, we execute the exact same set of TensorFlow operations by instantiating the kernels right before they're needed and then executing them. One nice thing about this is that whether the operations are executed as part of a graph function or whether we execute them eagerly, we execute the same code. So this is conceptually simple. The details of sort of making all of our Python API functions safe to run eagerly that was another story, and that was actually a lot of work, but that's not the focus of this talk. When we transform imperative code to graph functions, we try as much as possible to preserve the semantics of the original Python functions. So many of the details that I will show you about graph functions are motivated by this desire. So as I've said, the tf.function decorator is a just-in-time tracer. The first time the Python function is run, the tf.function will execute the wrapped Python function in a graph construction context. And it will generate a graph function that consists of all the TensorFlow ops that were run during the trace. So it's important to note that tf.function is not a compiler for arbitrary Python functions. So specifically, if you have something like for I in range 1 million, that will turn into a TensorFlow graph with 1 million nodes potentially. The object that tf.function returns is polymorphic. And what I mean by that is that it specializes its traces on the d-types and the shapes of tensor inputs and the runtime values of the non-tensor arguments. So essentially when it's called, when a decorated function is called, we'll infer the input signature. And if the input signature doesn't match something that we've seen before, we'll trigger a new trace of the Python function. So that means that multiple concrete graph functions might be generated for a single Python function. And this type of runtime specialization is very similar to what's done in JAX, and it's also sort of conceptually similar to lightweight modular staging. And also to sort of to make it sort of seamless to insert tf.function into existing imperative code, we've made it so that you can lexically close over tensors and tf variables while using the tf function decorator. When TensorFlow variables are used in functions, we do a bit of extra work in order to ensure that the ordering of reads and writes to variables in graph functions matches the Python ordering in the original Python function. So specifically, when tf.function generates graphs, it will automatically insert control dependencies that ensure two things. First, we'll ensure that all stateful operations are run, and that operations which modify, so the second thing is that we'll ensure is that operations that modify the same resource run in program order. And importantly, we try to do this in a way that we insert the minimal amount of control dependencies possible so that the function runtime can still exploit parallelism in the graph. So I said that tf.function was just a Python tracer. I lied a little bit in that we have actually recently added the ability to rewrite a subset of Python control flow to TensorFlow control flow. So specifically, Python control flow that depends upon tensor data will be rewritten to graphed control flow. And this rewriting is done via autograph, which is the subject of the next talk, so make sure you stick around for that. So with respect to how functions are actually run, we instantiate them in per-device runtimes, and the runtime automatically will parallelize and optimize each function before running it. It's essentially very similar to the runtime for classic TensorFlow, for TensorFlow graphs. And functions themselves are executed by operations, just like any other primitive in TensorFlow. And because of this, we get as a consequence that functions are very easy to compose. For one function to call another, all the first function has to do is to have like a literal function call operation embedded inside of its graph. This also has a nice side effect of helping us limit the size of graphs when we are sort of, if you're stamping out multiple subgraphs, you can instead just have n calls to the same function. The fact that functions are executed by operations also means that it's easy to customize the runtime behavior of functions by writing your own special function call operations. So as an example of that, we use a special function call operation to execute functions across multiple devices. And this function call operation essentially replicates a subset of TensorFlow sessions inside the operation. So it reuses technology like the graph placer and partitioner, which will take a TensorFlow function, a TensorFlow graph, and partition it across a set of devices. And we even extended this op to create another special op whose device was configurable at runtime. So that let us retarget where the function was running at runtime, and this was useful for load balancing in production. Of course, TensorFlow Eager would not be a library for machine learning if we did not have automatic differentiation. We support a tracing-based reverse mode automatic differentiation. And in our programming model, we explicitly expose the trace, or as we call it, the tape, to our users so that they can limit the overhead incurred by tracing. And this is a simple code snippet that shows how tracing works, gradients work. So the tf.gradient tape is the main entry point into the gradient API. It's a context manager, and it can be nested in order to compute higher order derivatives. The watch method on tapes marks a tensor as something that we'll need to compute a gradient for or with respect to later. If you use variables, they would be washed automatically. And I should mention that the tape is tightly integrated with functions. So when a function is called under a tape, we'll do what's necessary. So we'll modify the forward pass to output and store intermediate values, and then we'll generate a function that will compute the backward pass. So the gradient tape actually recently acquired the ability to compute Jacobians. And this computation is automatically batched using a parallel for construct that was, I think, recently designed in the past couple of years. This is actually pretty new. This detail is not even in our paper. For the evaluation, I will show two experiments that compare the performance of TensorFlow Eager and graph-based TensorFlow. So this first one shows the examples per second achieved while training a ResNet 50 on ImageNet on a GPU. The y-axis is the examples per second, the x-axis is the batch size, and the red colors correspond to a purely imperative TensorFlow Eager implementation. The blue bars correspond to TensorFlow Eager with judicious use of the tf.function decorator to basically turn the forward and backward passes into graphs. And the orange bar corresponds to pure TensorFlow. So you can see as when the batch size is small, there is a significant difference in examples per second. Functions help a little bit. But as the batch size increases, the difference between imperative Eager and Eager plus functions seems to vanish. And the difference between those two in TensorFlow also becomes much smaller. Where TensorFlow Eager does take a significant hit in performance is when we're running programs that have tons and tons of very small operations. And in this case, the Python overhead incurred while running these operations tends to dominate the actual amount of time spent computing the kernels. So this chart shows the examples per second achieved while training a MCMC method from the generalized Hamiltonian Monte Carlo method L2HMC paper. The y-axis is again examples per second, x-axis is number of samples. The colors are the same as before. So Eager is obviously like 2 or 3 orders of magnitude slower than graph TensorFlow. The promising, sort of the optimistic way to read this chart is to say that by using function judiciously, you will recover essentially all of your performance. But I think this involved basically using function to turn the vast amount of the code into a graph. And okay, one more thing. The data is from September of 2018, so perhaps numbers have improved. Some future work. A lot of it has to do with performance optimization that's easier for graphs than it is for eager execution. So we still have plans to develop a sort of a way to execute eagerly, but also asynchronously. We have a prototype, but that prototype is far from done. It's not clear how to reuse memory buffers for temporaries in Python, whereas we do, again, have some type of solution for that for graphs. And also we're working on getting SPMD working efficiently across multiple devices. And the last thing that we want to do is make it possible to stage more and more code as graphs. And one key thing that this will involve is representing more interesting data structures in the graph. And autograph, again, will probably be quite useful in this task. And that's all I have. Thank you.
Heidi, UIUC. Great talk. I have one question about multi-device support. So in TensorFlow, when there are part of the graph running on the different devices, TensorFlow automatically adds send and receive ops. If this happens inside a function, how your GIT deal with it?
Yeah, so that's a great question. Actually, so we do the exact same thing. So if your function has tf.device annotations, and when we're running the function, the first time the function is run, it'll be we'll partition it and automatically add the sends and receives.
Great, thank you.
Yeah.
Any more questions?
Yes. Simeon Wei from CMU. Yeah, this great talk. My question is, are there things that programmers can do with TensorFlow but cannot do with the TensorFlow eager?
I don't think so, because essentially, like, if you just write your entire program as one function that has tf.function on top, then essentially you can replicate all of what you can do in TensorFlow because you have a graph.
Okay. Okay, thank you.
You're welcome.
Do we have any more questions? All right, let's thank Akshay again. Dan Moldovan from Google is going to talk to us about autograph, imperative style coding with graph-based performance.
Good afternoon, everyone. It's exciting to be here. So this work is a collaboration between Purdue University, Google AI, and the TensorFlow team. So in this paper, we propose a new methodology for expressing machine learning models in Python. We demonstrate this methodology using source code transformation and dynamic dispatch to enable multi-stage programming. We describe Autograph, a system we implemented for this purpose, and we show that it allows writing expressive machine learning code which retains the performance and portability benefits of graph execution. To motivate our work, I would first like to talk about a few of the current challenges in machine learning development. I will focus on the Python language and more specifically on lower level development of writing more complex, newer machine learning algorithms. We can distinguish two major paradigms that are widely in use today, as we've seen in the previous talk as well. One of them is imperative execution, also known as define by run. This paradigm represents the classical way of running a Python program. Operations execute immediately, and results are readily available. This is a very practical way of prototyping new models, and it integrates well with existing tools and APIs. However, programs written for imperative frameworks tend to be seen as more challenging to export and optimize due to the dynamic and interpreted nature of the Python language. Another paradigm is graph-based execution, also known as define then run. Python, in this case, is used as a meta-programming language in which a computation graph is first being built and then executed. Computation graphs, much like compiled programs, tend to benefit from additional optimizations. They are also portable and can typically be deployed to a variety of platforms ranging from embedded devices to large-scale distributed systems. However, graph-based programs tend to be more difficult to write and maintain. For example, they require control flow to be expressed in functional form, which is more verbose and less readable, and it's particularly cumbersome when nested. So given these two paradigms, there appears to be a trade-off between ease of use and performance or portability. With Autograph, we aim to combine the benefits from both. For the majority of this talk, I will focus on the utility of Autograph within TensorFlow, for which we optimized it. But we believe the method can be applied more broadly within the Python language, and we'll demonstrate that towards the end of the talk. Autograph works by converting imperative-style code, as shown here on the left, into graph code, shown on the right. This allows developers to write more expressive code that can still be executed as a graph, thus gaining the benefits that come with it. Now, we just attended a great presentation of TensorFlow Eager in the previous talk. Autograph and TF Eager serve complementary roles towards improving the development experience in TensorFlow. While Eager makes graph execution seamless using the TF function API, Autograph focuses on allowing a more expressive syntax within the TF function. In fact, TF function is now the recommended way to use Autograph in TensorFlow. Here we have an example. If you focus on the body of the function, notice that there is a Python while loop, which is conditioned on a tensor expression. This would normally not be allowed in graph-based code. Autograph will convert this to an actual TF while loop API call. Then the TF function decorator will add the necessary instrumentation to the function so that when called, it will seamlessly be converted, traced, cached, and executed as a graph. Autograph can also operate in a standalone manner if for any reason TF function cannot be used. In this case, which shows the same function as before, Autograph converts it into a new function. This new converted function can be used like regular graph code. Next, I will describe some of the more important techniques that enable this. But first, let us know that Autograph supplements the existing operator overloading mechanism found in Python. This mechanism is already helpful in allowing a more natural expression. For example, because the tensor class defines the necessary overloads, arithmetic expressions on tensor objects can already be written using a natural form. However, the standard operator overloading does not extend to control flow in Python. In other words, we cannot write these kinds of overloads. Autograph fills this gap by replacing control flow, like if and while statements, with equivalent function calls. These function calls serve a role that's very similar to that of overloaded operators. In essence, Autograph is a transpiler. It converts Python source code, typically in the form of a function, into equivalent graph code. This is achieved using source code transformation, a technique we previously applied in Tangent. It consists of parsing the source code of an input function into a Python abstract syntax tree, then incrementally and repeatedly transforming this AST so that ultimately it can be used to construct a new function. All this is done at runtime. Importantly, the Python runtime, the standard Python runtime, provides all the facilities critical for this process. And this allowed us to implement Autograph entirely as a Python library. An important challenge with machine learning code is that it tends to mix effective computation with setup and configuration code. Here's an example. If we focus on the control flow in this example, the for loop and the if statement at the top rather serve a role in describing how the computation should be constructed. And only the for loop at the bottom is part of an actual computation. This pattern bears a strong resemblance with staged programming, which has been previously studied in the context of other programming languages and has been made popular by work such as lightweight modular staging. Traditionally, staged programming identified two stages, compilation and runtime. But we can recognize them here as graph construction and graph execution. During graph construction is when Python code actually runs. During graph execution, control is handed over to a downstream system outside Python, typically the TensorFlow runtime. So in this case, we could state that when an op is being called in graph code, the respective computation is being staged for graph execution. Given that, we now have to make a decision then when transforming code. That decision is whether to stage a particular construct or not. A reasonable heuristic, one that is also consistent with the standard operator overloading, is to do it based on the type of the operands. For example, it is reasonable to consider that a for loop should be staged if it iterates over a tensor. Our type-based dispatch follows this heuristic as well. It will create a TensorFlow op whenever the statement depends on a tensor, and otherwise it will revert to normal Python execution. Now, a further complication arises from the dynamic nature of Python. Inferring the type of a variable cannot be done robustly just by looking at the code. For instance, the return value of this getRange function here could have just about any type. To solve this, we instead use dynamic dispatch. All the autograph will rewrite all the control flow statements with special autograph functions, which will examine the type at runtime when it's actually known. This example shown here is a depiction of autograph's actual handle for its statements. Notice the decision to construct a TensorFlow op based on the type of the condition argument. If the condition is not a tensor, then the transformed code will be functionally no different than the if statement which it originally replaced, although it will execute with a small overhead. But we are not worried about this overhead because it influences the graph construction and it does not impact the graph execution. There are also certain Python statements which cannot be easily rewritten as functions. Examples include non-local control flows such as break, continue, and return. We handle these statements by rewriting them into equivalent lower-level code that relies solely on extra conditionals and signaling variables. This new resulting code is then converted normally. Function calls represent another important idiom. It would be quite impractical for autograph to require that each and every function be explicitly converted. Instead, we rewrite function calls with a special wrapper. This wrapper will typically convert the function at runtime. However, it might also decide to call the function unconverted, for instance, if it's a TensorFlow library function or if it's of an unsupported type. Lastly, statements which autograph does not currently handle, typically because they have no equivalent in TensorFlow, are left unchanged in the code. This allows autograph to accept a very large subset of the Python language as input, including existing TensorFlow graph code. Next, I will show a few of the use cases on which we tested autograph. The first one being an in-graph training loop. And we found this example to be interesting because autograph facilitates the expression of control flow, and the training loop is essentially just that, a loop. Here is shown the most relevant portion of the code. Notice the for loop iterating over a tensor. Also notice calls to standard TensorFlow API like optimizers and iterator. Performance-wise, the autograph version of the training loop is roughly twice as fast as an equivalent training loop written in Eager. But perhaps more interestingly, the in-graph training loop was also faster than the traditional method of training models in TensorFlow, which is using repeated calls to the session API inside the Python loop. We believe that's because the TensorFlow runtime is able to further optimize the loop itself. Another more complex use case is an implementation of the LBFGS algorithm, which is non-trivial even in its simplest form. It makes use of a circular buffer structure as well as nested control flow. In this particular instance, we ran the exact same code twice. First, in eager mode, and then in graph mode via autograph. Once more, the autograph version was about two times faster. A final example which demonstrates how autograph can be applied more broadly. In this case, we replace autograph's code generation of TensorFlow code with an S-expression generator. S-expressions are a grammar useful for representing programming languages. For example, we can use it to represent the reentrant function calls that you typically find in a 3RNN model. And we have here an example of S-expressions on the right. Then we wrote a parser which took the S-expressions and converted them into Scala code targeting the Lantern backend, which in turn can generate C++ code. The net effect is that we have a Python frontend for C++ code. In closing, a few words about possible future directions for Autograph. We are currently working to make the core of Autograph available as a standalone library to be available for other uses. We also plan to add support for more Python constructs as well as more staging patterns. And I would like to mention here that perhaps you've seen the Janus demo yesterday. We are particularly excited about the new features that it proposes. We've also spent a great deal of time and we've dedicated a great deal of effort on testing Autograph, and we continue to improve it. However, a formal proof of correctness remains a topic of future work. We'd also like to make it easier to debug Autograph code, and to that end, we are working on improving things like error reporting. Autograph is currently in beta, but it is stable enough to try out. It is available as part of the TensorFlow library, and the stable version of Autograph, which focuses on control flow, will be available in the TensorFlow 2 release. In conclusion, I presented Autograph, a system which lets you write faster and better machine learning code. It will be available in the TensorFlow 2 release within the TF function API. And although the implementation specializes on TensorFlow, the method could be extended to broader Python applications. If you'd like to learn more, check out the TensorFlow documentation and the examples on GitHub. And we've also loved to hear your feedback. And you can reach us through the TensorFlow community site. Thank you.
All right, we have plenty of time for a few questions. So I'd like to ask, how does the framework integrate with fault tolerance primitives? Like if you run something on like multiple GPUs and one fails, is that accounted for, or is it yeah?
It integrates in the sense that in the same way as regular graph code integrates. Basically, if you add the necessary constructs within the code to account for those scenarios, then it will work properly. Basically, it supports everything that TensorFlow supports, every primitive that TensorFlow has.
Yes, please.
Can we go back to the slide where you converted Python to C++? You went through that quickly. I wanted to look at. So if you had like a TensorFlow up inside the Python function, let's say matml, does it get converted into like another TensorFlow function in C++ as well, or is it getting native code and
That is a good question. I'm not sure whether we have the functionality in there to convert calls to the TensorFlow function into corresponding equivalent C++ calls.
Mm-hmm.
I can follow up afterwards to tell that for sure, but I can definitely say there is no reason not to be able to do that.
Okay. And the second question was like, are you only targeting C++, or are there plans to support other backends in the future?
Can you repeat the last part, please?
Are there any plans to support other backends in the future, or is it just C++?
So this example was more like an example. I'm not sure that autograph in the release version will support targeting C++, but what we intend is to make it generic enough so that if you would like to add your own backend, we want to make it very easy for you to do that.
Okay, thank you.
All right, let's thank Dan again.
Thank you.
And now for the last talk of this session, we'll hear about TensorFlow.js and how we can deploy machine learning for the web and beyond. And this will be by Daniel Smilkov and Nikhil Thorat from Google.
All right, hi everyone. Thanks for coming for the talk. I'm Daniel.
I'm Nikhil.
And today we're going to talk about TensorFlow.js. Before I go into the next slide, I just want to say that this has been a work of many people. As you can see on that slide, we've been going on for a year and a half, maybe 2 years, and and there's a lot more to do. So how many people here are think that they're comfortable doing Python? I'm just curious, writing Python code. Okay, almost everyone. So this is not a surprise, right? Python is synonymous with scientific computing today and doing numerical computations. And as you can see here from this software poll from KD Nuggets, it's the top data science software. How many people here are comfortable writing JavaScript code? All right, I don't see that many, but still quite a few. I'm very glad. So JavaScript, on the other hand, is extremely popular as a language. And this chart here that is from GitHub shows how many open pull requests there were in JavaScript and other languages in 2018. Another thing about JavaScript is that the community is very diverse, and a lot of people don't come necessarily from scientific computing. In fact, in the early days of TensorFlow.js, the early adopters were people that wanted to do creative coding, that wanted to use ML in a creative way. Another thing about JavaScript is that, runs in a browser, and as you know, in a browser, if you build something, if you write a blog post, you share a link, someone can then is click away from seeing your work. It is also highly interactive. Browsers have all the UI. They also run on laptops and cell phones, mobile phones, and all of these devices have sensors such as microphones and cameras and accelerometers, and they're all exposed behind standardized web APIs. All of these interesting, unique things about JavaScript lead to developers being able to build new class of distinct applications that can take advantage of on-device computation, low latency, and privacy and accessibility as well. I wanted to say a little bit more about the JavaScript environment for those of you that are not very familiar. It's supposed to run anywhere. It has a virtual machine that can execute it, except that it ranges all the way from server-side in Node and client-side in browsers. And the APIs don't overlap as much. They overlap within 50%, but when one builds a library, you gotta aim for the intersection of those. Another thing that's tricky about JavaScript is it's an interpreted language. And that means that performance can be tricky because it can run near the speed of C if you write your code carefully so that just-in-time compilation of V8 can execute it as C. But if your code is part of a transpiler that takes ES6 to ES5 code and that transpiler rearranges the variables, it can hurt your performance by a lot. So you have to be careful when you're writing a JavaScript library to account for these effects or to have a backend where you can offload your computation to something that is much more stable and predictable. Another thing when you target browsers, for instance, like we do, is you have Firefox, you have Safari, you have Chrome, and there are all these there's a W3C standard, and there are all these standards that all browsers should implement, but in practice, they all do things slightly differently, and then you have to account for that too. And I'll just end this slide with saying that JavaScript is single-threaded, which makes it easy if you do many things in parallel and not be blocked by all the multi-threaded problems. But the way that they resolve this is with asynchronous programming, which takes a while to wrap your head around. Just a quick mention of related works where we were not the first to do ML in JavaScript. There are a lot of libraries out there. This chart shows us along other libraries, along axes such as whether they use the GPU, whether they're actively maintained. I just want to call out that as of today, we're the only library that's actively maintained and has a full API to write author graphs and to do training and do backpropagation. A few other works that back in the days when we were developing this early on were maintained, and now they are not. A little bit about our design. So we have, performance is very important, and for us, we're going to talk a little bit more about that and how that made our projects basically possible. But when we were conflicted, when there was this struggling force between making it easy to use and performance, we would choose easy to use first because we wanted to, bring ML to a new set of community, and we don't want to, make it extremely hard. At the same time, our library, we wanted to have wide functionality because we wanted, experts that know both Python and JavaScript and that can develop these ML models to be able to come to our platform and then share their work. And we wanted those experts to have access to gradients, to all the ops, to be able to, let's say, build educational content if you're an educator, and so forth. And these two goals of being very easy to use and also have wide functionality are in conflict often. And the way we kind of resolve that is to have multiple layers of abstraction. And what I mean by that is that at the API level, we have 3 layers. So we have the core API where you can write ops like matmul and add and multiply. And they all run in eager mode, just like TensorFlow 2.0. On top of that, we have the layers API, which is modeled after Keras. So you have high-level building blocks such as layers, convolutional. And on top of that, we also have a repository of pre-trained models, so you can use them off the shelf without even knowing about tensors and about multidimensional arrays, where the output can be just a JSON object. On the back-end side, so all of this API bind in the browser utilizes WebGL to actually utilize the GPU and that gives us a significant boost. On the server side in Node, we can bind to anything, so we bind to TensorFlow C, which then can utilize GPU, CPU, TPUs. And lastly, if you have an existing model in Keras or TensorFlow saved model, we have converter tools that can allow you to automatically port your model to the web or server side. Just to give you a little bit of a code example, so we tried to make it extremely easy to use, very JavaScript-like. Unfortunately, the only thing that we couldn't account for in the browser was texture garbage collection of WebGL textures, which browsers don't collect. And for that, we have a tidy construct. And this example here shows that. So if we have here a function on animation, which gets called, let's say, 60 frames per second, and we run the image through our model function, and then we display our result. And here we have to wrap it in a tidy, and tidy is just a scope that we introduce, so it can monitor all the tensors inside and then dispose everything but the result. So that's why Y is the only thing that we need to dispose. So this is for experts. The way to kind of hide that is you can use our high-level API layers model and then call model.predict, and you don't have to do a tidy. The only thing you have to take care of is the output, Y. And even further than that, if you're using one of our off-the-shelf pre-trained models, you pass in an image, you get a JSON object back, and you don't have to take care of any memory management. All right, so a little bit about performance. So the top right chart here compares TensorFlow.js on various backends. One thing to take away from this is that WebGL is what made this project possible to do ML in the browser, because it is 2 orders of magnitude faster than plain JS. And we are actually actively working on making WebGL faster. We have recently added packing. This is after we wrote the paper, which allows us to store values more efficiently in texels, and that can lead to anywhere between 1.4x to 9x speed up on some devices. Another thing I'd like to point out is that there is still a 3 to 10x gap between WebGL and CUDA for large batch sizes. For a batch size of 1, we don't see that. And here, we suspect it's because WebGL doesn't give us shared memory access or worker pools that CUDA does. But new technologies are coming up, and we believe that WebGPU and compute shaders will narrow this gap. And the chart on the bottom right shows TensorFlow.js binding to TensorFlow C server side and Python binding to TensorFlow C server side. And we see that we're on par with Python for inference because we're just a thin shell. For training, though, we're still working on it because training involves a lot of code that needs to be written in JavaScript itself for gradient, and we're making that faster these days. I'm gonna let Nikhil tell you.
All right, thanks a lot. So in the browser, the way we do this is we use a technology called WebGL. Now, WebGL is a way for the web to bind to OpenGL, which is a way to express graphics constructs that run on your GPU. Now, little known fact in the deep learning world, that G in GPU stands for graphics, not something else like gradients. So what we do is we actually store all our tensor data in WebGL textures. These are 2D textures. And we write all of our programs as fragment shaders. Now, what OpenGL is really good at is drawing pixels on a screen, and they'll do that in a very massively parallel way. So we actually kind of take advantage of that parallelism to do linear algebra constructs. So in this example we're looking at is an element-wise addition of 2 matrices, A and B, to compute a C. What you're actually seeing in that box is the implementation of that fragment shader. And the fragment shader is a little mini program that's going to run in each of the output cells of C. And OpenGL will massively parallelize that, so we get really nice speed ups from that. So to jump into an actual fragment shader, this is the matrix multiplication. This is GLSL code. This little main mini program runs again over the context of all the output cells. These little bolded functions here are not raw GLSL. These are TensorFlow.js provided constructs that we've actually assembled together as the program is about to be executed. Now, we actually opted to write real GLSL code rather than write a little compiler on top of that. We did that because we wanted to just make it a lot easier for us to debug, and it's been working out really nice. Okay, so that was the browser. On the Node.js side of things, which is a way to run JavaScript server-side, if people don't know about that, we actually bind, again, as Daniel says, to the TensorFlow C++ API. We do that with the N API. And JavaScript is really, really a fast language, so we actually can see similar or even sometimes faster than Python when we do this, which is pretty nice. One of the amazing things about Node.js is we have finalization for things like that we don't in the browser. So WebGL textures, where we store GPU memory, don't get automatically garbage collected. So we have these tidy constructs, which are kind of unwieldy for JavaScript programmers, put it that way. So in Node, we actually have a hook into finalization because we're kind of unconstrained by the browser environment, which is really nice. And we're actually working right now on headless GL binding. So that means in Node.js, being able to run our OpenGL shaders inside of that headless environment. That enables GPU acceleration on devices that we weren't able to before. So this is on like Macs, on Raspberry Pis, and other IoT devices. So that's pretty cool. We're also really interested in performance. So we're thinking about some new backends for TensorFlow.js. On the CPU acceleration side, there's a standard called WebAssembly. This is a way to take C++ or Rust code, compile it to a little binary that runs and is interpreted in the browser and can run close to C speeds. That in combination with SIMD, which is going to land pretty soon in browsers, and that with worker threads, which you can actually use native C++ P threads, and those will actually run multi-threaded code inside of a browser, which is kind of a new thing. That combination, we think, will get us a little bit closer to WebGL speeds than we're getting today. There's also a new GPU standard called WebGPU that's going to land pretty soon. This has already been spec'd out and is now in implementation stage. This is a general purpose GPU programming construct for the web. So think about CUDA for the web. So we're working pretty closely with Chrome on the implementation of that, and we'll hopefully have a prototype later this year. We're also part of this W3C community group to standardize what we're calling WebNN. This is a way to expose neural network concepts directly to JavaScript, maybe like TF, or not TF, something conv2D in the browser, and under the covers, the browser will be binding to the native hardware acceleration depending on what that device is. Maybe on Android it's NN API, or on Macs it's Metal. So we're actively part of that discussion. Okay, so one of the important things that we wanted to do with this project too is have the ability to move between the Python world, which is this massive rich world of models, and the JavaScript world. Otherwise we would be sort of an orphan. So what we did was we built a model converter. This was a way to take a Python model, a TensorFlow saved model, a Keras model, and port that directly to the browser for inference. And we also built a models repo on top of that. This is off-the-shelf NPM packages that you can just go and install, and they require no tensors and no knowledge of linear algebra. You just kind of point to a video tag and you get JSON objects out, and we host all the weights for you. So one of the cool examples of that is this model called PoseNet. I'll show you a link to that at the end. This takes RGB images and it'll give you poses out as a JSON object, which is pretty nice. Just to jump through a couple things here, one of the really interesting things about the JavaScript environment that I think a lot of people don't know is it runs in a lot of different places. So one of them is the browser, but it runs in tons of other environments as well. So I'm going to quickly talk about a couple examples that people have built. One is Creatability. This is an accessibility experiment done by some Googlers to basically take RGB images from webcam and try to basically control the computer with just your face. Uber has used us as a linear algebra library, not even machine learning, just for forward mode linear algebra in this project called Uber Manifold. Airbnb has actually used TensorFlow.js as well to ship a little mini model to the client that says when you're about to upload a profile picture, don't upload a license, don't upload any government issued photos, and they tell you that right on the device before they get it on their servers, which is pretty nice. So on the Node and desktop side of things, in Node.js there's a program called Clinic Doctor. It lets you take a Node.js application using a TensorFlow.js model and differentiate the CPU usage spikes between the actual CPU program that you wrote, your code, and the Node.js kernel itself. And Magenta Studio, it runs in an Electron app. So this is Electron is a way to run JavaScript as a native application on your device. So this is a tool that lets artists go and generate new types of MIDI files, maybe just spark some creative idea before they move on to the next thing. And on mobile, there's a whole rich ecosystem called WeChat in China. So this is an application that has a whole app store inside of that application with 1 billion users, 1 million developers, a ton of things going on in here, and they run entirely in JavaScript. But they look completely native. So we're working to get OpenGL bindings working with TensorFlow.js as well on that platform. So everything we talked about here is open sourced. If you want to waste some time, go check out our demos on tensorflow.org/js. There's lots of fun stuff there. You'll have lots of fun. All the code is open source here as well, and we want to thank all the people who have worked on this project as well. I think we have some time for questions. Thank you.
All right, if we have any questions, please come up to the mics.
Hi there, congratulations on the really good work. I have a question about the API and how different it is from the Python API.
So in general, we try to stay as true to the Python API as possible. So every op that we support has the same list of arguments in the same order. There are a few differences that we have to deal with in the JavaScript ecosystem. Specifically, memory management is one of the major differences. The way we actually interoperate with browser APIs. So if you want to get a tensor from a video tag, we have to invent something because that doesn't exist in Python. So there's a few things that are different, but mostly we try to stay true to that API. And then the layers API that we provide, that high-level API, is pretty much the Keras API.
Thank you. Are there any more questions? All right, with that, let's thank the speakers of this session. And I guess let's please join me in thanking everybody for all the amazing talks this past 2 days. And our general chair, Amit, is going to give off some closing remarks now.
One sec. Come on. Having some technical difficulties here. So I could try this adapter, maybe it's the adapter. Yeah. All right, cool. All right, hey everybody. So this will just take a few minutes. So first, I want to start by thanking everybody. You know, it's been amazing. I think these last few days, lots of energy, lots of excitement, lots of great work. So I want to thank everyone again for being here. Also wanted to thank all the different people who were involved in sort of putting this program together. So that's the organizing committee, or sorry, the steering committee, the program committee, the artifact evaluation committee, folks at Stanford conferences, and the NERBS Foundation, and of course the organizing committee for working super hard to kind of put this conference together. And finally, of course, our sponsors, who again were very generous and really allowed us to put on what I think was a really well-run, organized conference. Second, while I think the conference went well, we can always do better, and it's a fast-growing community, and we're still sort of figuring out how to make this work. So we put together a survey. It'd be really, really useful and valuable to get your input. We'll also send an email after the conference with this link. So please should just take a few minutes, but we'd love to get your feedback as to what we did well, what we didn't do well, what you'd like to see next year, things like that. And finally, we don't have a venue yet for next year, but I am happy to say that we have some amazing people to run the conference next year. So our general chair is going to be Inderjit Dillon, and our program chairs are going to be Dimitris Papailiopoulos. Did I get that? All right. Hard last name to say. So Dimitris is here, and Vivian C. So if you have questions about next year, they're the right people to ask. We don't, again, know exactly where the venue is going to be. We're targeting early March. But as soon as we know, we will post it on our website and on social media. And again, thank you guys all for coming. Have a safe trip back to wherever you're going, and we'll see you next year.